Look up at the night sky. What do you see? A handful of glittering stars, perhaps the moon, a vast and seemingly peaceful darkness. But that view is an illusion, a quiet curtain hiding the greatest show in the cosmos. Beyond that thin veil lies a reality so immense, so chaotic, and so profoundly mysterious that it defies our everyday understanding. We are living on a tiny, fragile rock, hurtling through a universe filled with forces and phenomena that are, for now, completely beyond our comprehension. This is not just empty space, it is a cosmic ocean swirling with galaxies like islands of light, birthing and dying stars in spectacular explosions, and hiding secrets in the deep, dark void between them. We are about to embark on a journey to the very edge of known science, to confront the questions that keep astronomers and physicists awake at night. We will be counting down the top 50 greatest mysteries of the universe. These are not just simple puzzles, these are the fundamental enigmas that challenge the very core of our reality. What is the true nature of dark matter, the invisible, ghostly substance that holds galaxies together? What is dark energy, the mysterious force tearing the cosmos apart at an ever-increasing rate? Are we alone, or is the silence of the universe a profound statement in itself? From the bizarre quantum behavior of the smallest particles to the ultimate fate of everything that exists, these mysteries represent the frontier of human knowledge. They are the blank spots on our map of existence, and exploring them is perhaps the most exciting adventure our species has ever undertaken. This video is your ticket to that adventure. We will traverse the cosmos from the birth of the first second after the Big Bang to the possibility of parallel universes. We will grapple with concepts that sound like science fiction but are in fact the cutting edge of theoretical physics. This is a journey of wonder and excitement, a chance to stand on the shore of the known world and gaze out into the incredible unknown. So prepare to have your mind expanded and your perspective shifted. The universe is far stranger and more magnificent than you have ever imagined, and we are just beginning to unlock its deepest secrets. Let's begin our descent into the greatest cosmic enigmas, starting with number 50. And so we begin our descent into the cosmic unknown with the very first, and perhaps most fundamental, mystery on our list, the nature of dark matter. Think about the last time you saw a picture of a majestic spiral galaxy, its brilliant arms spinning in a graceful cosmic dance. Our intuition, shaped by the laws of gravity laid down by Isaac Newton and refined by Albert Einstein, tells us that the stars closer to the galaxy's center, where the mass is most concentrated, should orbit much faster than those out on the fringes. Just as Mercury whips around the Sun far more quickly than distant Pluto, but in the 1970s, astronomer Vera Rubin made a startling discovery that shattered this expectation. She found that stars orbiting at the very edge of galaxies move at virtually the same speed as those near the center. It was as if the entire galaxy was spinning like a solid plate, a motion that defied all gravitational logic. The only possible explanation was that galaxies are embedded within vast, massive halos of something we cannot see. This something exerts an immense gravitational pull, preventing the outer stars from flying off into space, yet it emits no light, no radio waves, no form of electromagnetic radiation whatsoever. We call this invisible, ghostly substance dark matter. Further evidence for this mysterious component of the universe comes from a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. The fabric of space-time is warped by mass, and a tremendous amount of mass can act like a cosmic magnifying glass, bending the light from distant galaxies behind it. When astronomers study these distortions, they find that the amount of bending is far greater than what can be accounted for by the visible stars and gas alone. There must be an enormous amount of unseen mass there distorting our view. In fact, when we add up all the matter we can detect, every star, every planet, every speck of cosmic dust, it amounts to less than 5% of the total mass and energy in the universe. Dark matter makes up about 25%. That means roughly 85% of all the matter in the cosmos is completely invisible to us. We know it's there only by its gravitational footprint. So what could it possibly be? Scientists have proposed a zoo of candidate particles. The leading contender for decades has been a class of particles known as WIMP, or weakly interacting massive particles. These are theoretical heavy particles that don't interact with light or normal matter except through gravity and perhaps the weak nuclear force. The hunt for WIMP has involved incredibly sensitive detectors placed deep underground, shielded from cosmic rays, waiting for the elusive bump that would signal a dark matter particle colliding with a normal atom. But despite decades of searching, these detectors have remained silent. Another intriguing candidate is the action, a particle originally proposed to solve a different problem in particle physics. Actions would be incredibly light, almost massless, and would behave more like a pervasive field than discrete particles. New experiments are now being designed to shine a magnetic field through a wall to try and convert these ghostly actions into detectable photons. The profound difficulty in finding dark matter tells us something crucial. It is not just ordinary matter hiding in the dark. It is not black holes, nor is it clouds of cold gas. It is something entirely new, a form of matter that does not fit within our standard model of particle physics. Its existence is a glaring sign that our understanding of the fundamental building blocks of the universe is incomplete. Every failed experiment, every quiet detector brings us closer to a paradigm shift, forcing us to reconsider what matter truly is. This invisible scaffold upon which the visible universe is built remains one of the most pressing and humbling mysteries in all of science. If dark matter is the unseen glue holding the cosmos together, then the next mystery on our list is its terrifying opposite, a force that is actively and relentlessly tearing the universe apart. We have journeyed from the ghostly presence that shapes galaxies to a discovery so shocking it completely rewrote the destiny of the cosmos. For most of the 20th century, astronomers believed they understood the ultimate fate of the universe. After the Big Bang, the fabric of space-time began expanding, flinging galaxies away from one another. The big question was whether the collective gravitational pull of all the matter in the universe would be strong enough to eventually slow this expansion down. Would it slow to a halt and then collapse in a big crunch, or would it just continue to coast outward forever, gradually slowing but never stopping? The answer, discovered in the late 1990s, was neither. The expansion of the universe is not slowing down at all, it is accelerating. This monumental finding came from teams of astronomers who were studying a very specific kind of stellar explosion, Type 1, a supernova. These cosmic blasts are crucial because they always release almost exactly the same amount of light, making them what scientists call standard candles. If you know how bright something truly is, you can measure how bright it appears from Earth and accurately calculate its distance. By looking at extremely distant supernova, which exploded billions of years ago, the researchers were effectively looking back in time. They expected to see that the expansion rate of the universe was slower in the past, but the data revealed the opposite. The ancient supernova were fainter than they should have been, meaning they were farther away than anticipated. The only explanation was that the universe was expanding more slowly in the past than it is today. The expansion is speeding up. This was like tossing a ball into the air and watching it not only fail to fall back down, but instead hurtle away from you faster and faster into the sky. For this paradigm-shattering work, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics in 2011. So what is causing this cosmic acceleration? Physicists gave it a name that reflects our profound ignorance: dark energy. It appears to be a kind of anti-gravity, a repulsive force inherent to the fabric of empty space itself. And just like dark matter, it dominates the composition of our universe. Remember that dark matter makes up about 25% of the cosmos. The ordinary matter we see is a mere 5%. The remaining 70%, that is dark energy. It is the single largest component of the universe, and we have no idea what it is. The leading explanation reaches back to none other than Albert Einstein. When he was formulating his theory of general relativity, Einstein believed the universe was static, neither expanding nor contracting. To counter the attractive force of gravity and achieve this static state, he introduced a cosmological constant, a kind of fixed energy density infused into the vacuum of space that would provide a gentle push to balance gravity's pull. When Edwin Hubble later discovered the universe was indeed expanding, Einstein reportedly called the cosmological constant his greatest blunder. But in a stunning twist of fate, modern observations suggest he may have been right after all, just for the wrong reason. In this model, dark energy is simply the energy of empty space, a constant force that, as the universe expands and creates more space, becomes more and more dominant over gravity. However, the cosmological constant is not the only idea on the table. Another compelling theory proposes that dark energy is not constant, but rather a dynamic energy field that has changed over the history of the universe. This concept, sometimes called quintessence, suggests that the strength of this repulsive force could vary in time and space. If true, this would mean the ultimate fate of the cosmos could be far more dramatic than we currently imagine. Instead of a steady acceleration leading to a cold, dark, and empty universe where galaxies are torn apart, a evolving dark energy could lead to a big rip where the fabric of space-time itself is shredded apart. The fundamental conflict between these ideas represents one of the biggest problems in physics. Is dark energy a simple, constant property of the vacuum, or is it a complex fifth fundamental force that we have yet to understand? To find out, astronomers are mapping the universe in unprecedented detail, using instruments like the Dark Energy Spectroscopic Instrument and the future Euclid Space Telescope to measure the expansion rate across billions of years of cosmic history. The goal is to see if the strength of dark energy has changed over time, which would rule out Einstein's cosmological constant and point toward a more exotic explanation. The identity of dark energy is more than just a puzzle. It is the key to understanding the ultimate fate of everything we see, a fate that is being written by this mysterious, dominant force hidden within the void. Our journey through the cosmos now brings us to a mystery that strikes at the very heart of our existence. We've explored the invisible dark matter that shapes the cosmos and the repulsive dark energy that dictates its ultimate fate. But what about us? What about the stars, the planets, and everything we can actually see and touch? This leads us to a profound question that is arguably the most personal on our list. Why is there anything at all? The answer, or rather the lack of one, lies in a cosmic imperfection so tiny, yet so consequential that our entire reality depends on it. We are diving into the mystery of the matter-antimatter asymmetry. According to our best theories of particle physics, the Big Bang should have been a perfectly symmetrical event. For every particle of matter it created every quark, every electron. It should have created an identical particle of antimatter. Antimatter is the mirror image of normal matter. It has the same mass but the opposite electrical charge. For example, the antimatter partner of the electron is called the positron, which is identical to an electron but with a positive charge. When a particle of matter meets its antimatter counterpart, they annihilate each other in a spectacular flash of pure energy, leaving nothing behind. So, if the Big Bang had created a perfectly balanced universe, all that matter and antimatter would have immediately found each other, annihilated, and transformed the entire cosmos back into a sea of radiation. The universe would be a vast, featureless expanse of light with no atoms, no stars, no planets, and certainly no one to ponder its existence. The fact that you and I are here made of matter is undeniable proof that this perfect symmetry was broken. Somehow, for every billion pairs of matter and antimatter that annihilated in the early universe, a single particle of matter was left over, and that 1 in a billion surplus is everything we see today. So what tipped the scales? Physicists call this necessary break in symmetry, CP violation. The C stands for charge conjugation, which means swapping a particle for its antiparticle. The P stands for parity, which is like looking at the particle in a mirror. For a long time, physicists believed that the laws of physics were symmetric under this combined CP operation. A universe made of antimatter should behave exactly the same as our matter-based universe. But in 1964, an experiment with particles called kaons found a tiny crack in this mirror. These particles and their antiparticles decayed at slightly different rates. This was the first hard evidence that nature has a slight but definite preference for matter over antimatter. It was a monumental discovery, but there was a problem. The amount of CP violation observed in the laboratory is far too small to account for the overwhelming dominance of matter we see in the cosmos. The subtle effects we can create are simply not powerful enough to explain how our entire universe came to be. This forces us to look back to the first fractions of a second after the Big Bang, to conditions of almost unimaginable energy and temperature that we cannot replicate in any particle collider on Earth. Theorists have proposed that during this primordial era, a process called baryogenesis occurred. Baryons are a class of particles that includes the protons and neutrons making up atomic nuclei, and genesis means creation. This process would have required 3 key ingredients, often called the Sakharov conditions, after the physicist who proposed them. First, the universe needed to be out of thermal equilibrium, meaning it was changing so rapidly that processes could not easily reverse themselves. Second, it needed interactions that violate CP symmetry, providing the mechanism to favor matter. And third, it needed interactions that violate baryon number conservation, effectively allowing the total amount of matter to change. While the standard model of particle physics contains some CP violation, it is not nearly enough to satisfy these conditions. This is a clear signal that our current model is incomplete. The search for the source of this cosmic bias is leading physicists to propose exotic new physics beyond the standard model. Some theories suggest that the answer lies with ghostly, ultra-heavy particles that existed only in the first moments of the universe, decaying in a way that preferentially produced matter. Others look to the mysteries of neutrino physics. Neutrinos are ubiquitous but incredibly elusive particles that barely interact with matter. If neutrinos are their own antiparticles, a hypothetical class of particles known as Majorana fermions, then rare decay processes involving them could have generated the matter asymmetry. The ongoing experiments deep underground, designed to detect whether neutrinos double as their own antimatter counterparts, are not just studies of tiny particles. They are investigations into the origin of everything. The matter-antimatter asymmetry is not a minor curiosity. It is the fundamental reason why the universe is filled with galaxies and life, rather than being a blank, empty void. Solving this mystery means understanding why we are here at all. Having established that the universe's expansion is accelerating, we're forced to confront an ultimate, almost philosophical question: where is this all heading? The fate of everything, every galaxy, every star, every atom hinges on the unresolved nature of the very dark energy we just discussed. This isn't just an academic exercise. It's about projecting the life story of our cosmos billions, even trillions of years into the future, and the scenarios are as dramatic as they are bleak. The leading theories present us with 3 distinct endings, each more profound and unsettling than the last. The most widely accepted model, based on our current observations of a constant dark energy, points toward a destiny known as the heat death or the Big Freeze. Imagine the universe as a cosmic engine slowly running out of fuel. Stars are the furnaces that power this engine, converting mass into energy through nuclear fusion. But the supply of hydrogen gas needed to form new stars is finite. Over trillions of years, the last stars will flicker out one by one. The universe will become a vast graveyard of dead stars, black holes, neutron stars, and cold, barren cinders of planets. Even these remnants won't last forever. Thanks to a phenomenon predicted by Stephen Hawking, black holes themselves slowly evaporate, radiating away their mass over unimaginable timescales. In the final stages of the Big Freeze, the universe will approach a state of absolute equilibrium. The temperature will uniformly drop to a fraction of a degree above absolute zero. With no energy gradients, no hot spots or cold spots, no further work can be done. It will be a static, dark, and utterly lifeless cosmos, having reached a maximum state of entropy where nothing ever happens again. This is a quiet, drawn-out, but seemingly inevitable end based on the relentless acceleration driven by a constant dark energy. But what if dark energy is not constant? This brings us to a far more violent and immediate finale, the Big Rip. Suppose that instead of remaining steady, the repulsive force of dark energy actually grows stronger over time. In this scenario, the acceleration of the universe's expansion wouldn't just continue, it would intensify exponentially. First, the force would overcome the gravity that binds clusters of galaxies together. Billions of years before the end, these vast island universes would be torn apart, their individual galaxies flung into the ever-widening void. Then, as the force grows even more powerful, it would target the galaxies themselves. The gravitational glue holding a galaxy like our Milky Way together would be insufficient. Stars would be ripped from their orbits and sent flying off into isolation. In the final moments, the terror would become intimate. The overpowering force would tear apart individual solar systems, then planets from their stars. In the last hour, it would rip apart stars and planets themselves. And in the final, catastrophic instant, the force would be so strong that it would overcome the very bonds holding atoms together, shredding all matter into a diffuse, elementary particle soup. The fabric of space-time itself would be torn asunder. The Big Rip is a truly apocalyptic ending, a definitive and destructive finale to existence. The third scenario, the Big Crunch, is a dramatic reversal of our current understanding and now seems far less likely. This was the favored model for much of the 20th century, proposing that the density of matter in the universe was high enough that gravity would eventually win out over the expansion. The universe would slow its outward flight, stop, and then begin collapsing back in on itself. Galaxies would start rushing toward each other, the background temperature of the universe would rise, and the sky would glow hotter and brighter. In the final moments, the entire cosmos would be compressed into an incredibly hot, dense state similar to the singularity from which it began, a mirror image of the Big Bang. Some theorists have even suggested that this could be part of a cyclic universe, a big bounce, where a new universe is born from the ashes of the old one. However, the discovery of dark energy and the accelerating expansion has severely undermined this idea. For a big crunch to occur, the universe would need to be closed geometrically and dominated by matter's gravity. Our observations strongly point to a flat geometry and a dominance of dark energy, making this cosmic cycle appear to be a closed chapter. So which fate awaits us? The answer lies in a property of dark energy called its equation of state, denoted by the letter W. If W is exactly equal to -1, dark energy is a constant cosmological constant, and the Big Freeze is our future. If W is less than -1, dark energy is a phantom energy that grows stronger, leading to the Big Rip. Our current measurements place W very close to -1, slightly favoring the heat death scenario, but the error bars in our data are still too large to rule out the more dramatic possibilities. The next generation of telescopes, like the Vera C, Rubin Observatory and the Nancy Grace Roman Space Telescope are designed to measure the expansion history of the universe with unprecedented precision, effectively weighing the fate of the cosmos by pinpointing the true nature of dark energy. The question of how the universe ends is therefore not yet settled. It is an active, ongoing investigation, a mystery whose solution is written in the dark energy that fills the void, waiting for us to decipher its ultimate intentions. From the ultimate fate of the cosmos, we now turn our gaze backward to the very beginning of time itself. We have traced the story of the universe from its accelerated expansion today, back through the formation of galaxies to the initial surplus of matter. But this narrative leads us to a precipice, a moment of creation that seems to defy any further inquiry, the Big Bang. The laws of physics, as we understand them, break down at that point of infinite density and temperature, the singularity. This presents us with perhaps the most mind-bending question of all. What happened before the Big Bang? The very phrasing of the question might be a trap, a limitation of our language and our intuition, which are built upon the steady flow of time. To even approach an answer, we must be willing to consider that time, as we know it, may not have always existed. One profound possibility is that the question is simply meaningless. If the Big Bang marked the origin of space and time, then there is no before in any conventional sense. Asking what happened before the Big Bang is like asking what is north of the North Pole. The concept of before requires time to already be flowing. In this view, championed by Stephen Hawking and others, the universe would be like the surface of a sphere. The Big Bang isn't a point in space and time, it is the boundary of space-time. It is the south pole of that cosmic sphere, a point where all lines of longitude converge. There is nothing south of the South Pole, and there was nothing before the beginning of time. This idea, known as the no-boundary proposal, suggests the universe popped into existence from nothing, not in a violent explosion, but as a smooth, geometrical transition where time itself becomes a dimension like space, with no sharp, singular edge. It is an elegant solution, but one that many find deeply unsatisfying, as it seems to close the door on further investigation. Yet, many cosmologists are unwilling to accept that the door is permanently shut. They search for theories that allow us to peer beyond the veil of the initial singularity. The most influential of these is the theory of cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the universe underwent a brief period of exponentially rapid expansion, ballooning from a subatomic speck to something much larger in an unimaginably short time. This idea beautifully explains several observed features of the cosmos, such as its overall flatness and uniformity. But the most intriguing implication of inflation is that it may be eternal. Once inflation starts in a region of space-time, quantum fluctuations can cause it to end in some areas, creating what we call a pocket universe like our own, while continuing eternally in others. In this eternal inflation scenario, our Big Bang was not the absolute beginning, but merely the moment inflation ended in our particular cosmic bubble. The entire multiverse, a vast frothing sea of space-time, would have no beginning or end. Our universe is just one bubble in an infinite, forever inflating cosmic foam. In this picture, the question of before transforms into a question of elsewhere, what is happening in other bubbles beyond our observable horizon. This naturally leads us to cyclic models of the universe, which offer a truly ancient perspective on cosmic history. Perhaps the Big Bang was not a beginning, but a transition, a moment of renewal in an endless cycle. One compelling version of this is the ekpyrotic universe model, inspired by string theory. It suggests our three-dimensional universe exists on a membrane or brane, floating in a higher dimensional space. Another parallel brane could exist a tiny distance away. The Big Bang in this model was the result of a collision between our brane and this other one. The immense energy of this collision flooded our universe with radiation and matter, setting the stage for everything we see. After the collision, the brains move apart, the universe expands and cools, and eventually, the gravitational attraction pulls the brains back together for another cataclysmic collision, starting the cycle anew. In this view, the cosmos has no start and no finish. It is an eternal rhythm of creation and destruction, with each Big Bang preceded by a big crunch from a previous cycle. The challenge in resolving this mystery is that all these ideas, the no-boundary proposal, eternal inflation, cyclic models, currently reside in the realm of theoretical physics. They make predictions, but testing them against observational evidence is incredibly difficult. The key might lie in the faintest whisper from the dawn of time, the cosmic microwave background radiation. This afterglow of the Big Bang is our oldest baby picture of the universe. Some theories predict specific patterns in this radiation that could be imprinted by events that occurred before our Big Bang, like gravitational waves from a previous cosmic cycle or collisions with other universes in the multiverse. While our current technology may not be sensitive enough to detect such subtle signals, future observatories could potentially find these cosmic fingerprints, offering a glimpse beyond the initial singularity. The question of what happened before the Big Bang therefore stands as the ultimate frontier. It forces us to confront the nature of time, reality, and existence itself, pushing the limits of human curiosity to the absolute edge. Moving from the cosmic beginnings of time to the present day, we arrive at a mystery that is profoundly human. We have a universe estimated to be 13.8 billion years old, containing upwards of 200 billion galaxies, each with hundreds of billions of stars. The ingredients for life as we know it, carbon, water, organic molecules, are scattered everywhere, from the hearts of distant nebulae to the icy moons right here in our solar system. The numbers are so staggeringly large, the conditions so seemingly common, that the existence of other intelligent civilizations feels almost like a statistical certainty. And yet, when we train our radio telescopes on the heavens and listen, we are met with an unsettling and profound silence. This is the core of the Fermi Paradox, named for the physicist Enrico Fermi, who, during a casual conversation in the 1950s, famously asked, "But where is everybody?" The paradox is this crushing contradiction between the high probability of extraterrestrial intelligence and the total lack of any observable evidence for it. If even a tiny fraction of stars developed technological civilizations, and if even a small percentage of those began exploring or colonizing the galaxy, the math suggests the Milky Way should be teeming with life. A civilization just a few million years older than ours would have had more than enough time to colonize every habitable world, or at the very least, fill the cosmos with detectable signals from their activities. Our galaxy is 10 billion years old. Why does it seem so untouched? This silence is arguably more frightening than any signal we could receive, because it forces us to consider that there might be something fundamentally wrong with our reasoning. Scientists and thinkers have proposed a spectrum of solutions, ranging from the deeply sobering to the wildly speculative. On one end of this spectrum lies a particularly unsettling class of answers known as the Great Filters. The idea is that the evolution of life from simple chemistry to a spacefaring civilization requires passing through a series of incredibly difficult evolutionary steps. A great filter is a barrier so formidable that it prevents almost every potential civilization from progressing beyond it. The critical question for humanity is, have we already passed through this filter, or does it still lie ahead of us? If the filter is behind us, perhaps the miraculous jump from non-living chemistry to self-replicating life was an astronomically rare fluke. Then we might be among the first and loneliest intelligent species in the galaxy. This is a hopeful, if solitary, scenario. The terrifying alternative is that the filter is still in our future, Perhaps every advanced civilization inevitably discovers a technology that leads to its own destruction, be it nuclear war, engineered pandemics, or a runaway artificial intelligence. In this view, the silence of the cosmos is a graveyard, a warning that no one makes it out of their technological adolescence. The Great Filter hypothesis forces a sobering perspective on our own survival, turning the search for other life into a race to see if we are the exception or the rule. Other solutions are less apocalyptic but equally effective at explaining the silence. Perhaps intelligent life is common, but interstellar travel is physically impossible or so impractical that it's never undertaken. The vast distances between stars, the limitations of light speed, and the immense energy requirements could create a permanent cage, isolating civilizations on their home worlds. Or maybe we are looking for the wrong things. Our searches, like those conducted by SETI, the search for extraterrestrial intelligence, primarily listen for deliberate radio signals. But a civilization only a few centuries more advanced than us might have moved beyond such primitive communication, using technologies like neutrino messaging or quantum entanglement that are completely invisible to our current instruments. Another fascinating idea is the zoo hypothesis or the planetarium hypothesis. This suggests that advanced civilizations are aware of us but have chosen to isolate our solar system in a kind of cosmic wildlife preserve, allowing humanity to develop naturally without interference. They might be observing us, waiting for us to reach a certain level of maturity before making contact, treating our world as we would a protected natural habitat. While this seems like science fiction, it resolves the paradox by suggesting the galaxy isn't empty. It's just that we're in a quiet neighborhood by design. Then there are the possibilities that challenge our very definition of life and intelligence. What if we are alone? What if the specific chain of events that led to us on Earth, the stable star, the right-sized planet, the moon stabilizing our tilt, the extinction of the dinosaurs, was such an improbable series of accidents that we are truly the first and only beings to gaze upon the cosmos with wonder? Or what if intelligence is not an evolutionary inevitability, but a fleeting, self-correcting aberration? Perhaps the default state for complex life is not technological civilization, but something else entirely. The silence might also be a matter of timing. The universe is old, but habitable windows for life might be brief, separated by cosmic catastrophes like gamma-ray bursts that sterilize large regions of the galaxy. We could simply be existing in a quiet gap between the rise and fall of other civilizations, our signals and theirs missing each other by millions of years. Amidst these theories, the scientific search for answers continues with unwavering dedication. Projects like SETI have been systematically scanning the sky for decades, using increasingly sophisticated algorithms to sift through cosmic noise for an artificial signal. The Breakthrough Listen initiative has vastly expanded this effort, committing to survey the 1 million closest stars and the centers of 100 galaxies across a wide range of radio and optical frequencies. Meanwhile, the field of astrobiology is tackling the other side of the equation by searching for biosignatures, chemical signs of life, even simple microbial life, in the atmospheres of exoplanets. The upcoming James Webb Space Telescope is poised to revolutionize this search. Finding even a single instance of life elsewhere, no matter how primitive, would dramatically shift the probabilities and suggest that the universe is indeed fertile ground for biology. The discovery of a second genesis of life would imply that life is not a miracle, but a common cosmic process, making the subsequent silence for intelligent life even more profound and mysterious. The Great Silence, therefore, is not a passive absence of data. It is an active puzzle, a Rorschach test for our own hopes and fears about our place in the cosmos, pushing us to listen more carefully and look more deeply than ever before. Now we move from the vast, philosophical silence of the cosmos to a phenomenon that is anything but quiet, a series of sudden, explosive screams in the radio spectrum that have left astronomers both baffled and exhilarated. Imagine a single, brilliant flash of energy more powerful than 500 million suns, concentrated into a burst that lasts for less than the blink of an eye. This is the essence of a fast radio burst, or FRB. These events are among the most energetic and enigmatic phenomena ever detected, appearing as random, millisecond-long spikes on radio telescopes that then vanish without a trace. For years after their initial discovery, they were the ghosts of the cosmos, here one moment, gone the next, leaving scientists to wonder if they had even seen them at all. The story begins in 2007, when astronomer Duncan Lorimer and his student David Narkevic were sifting through archival data from the Parkes Radio Telescope in Australia. They were looking for new pulsars, the spinning remnants of dead stars, when they stumbled upon a signal unlike any other. It was a burst of radio waves that had occurred 6 years earlier on July 24, 2001. It was incredibly bright, but it lasted a mere 5 milliseconds. The most puzzling aspect was its dispersion. When radio waves travel through space, they interact with free electrons, causing higher frequencies to arrive at our telescopes slightly faster than lower frequencies. By measuring this smear, astronomers can estimate how much material the signal has traveled through, and therefore its approximate distance. The dispersion of this first burst, now known as the Lorimer burst, indicated it had come from far outside our galaxy, from a source billions of light-years away. The energy required to produce such a bright signal from such a distance was staggering, and for years it remained a singular, unexplained curiosity. Skeptics even suggested it might be a local glitch, an artifact from a microwave oven on the observatory grounds. But then more were found. The mystery deepened significantly with a crucial distinction: the discovery of repeaters. Most FRBs detected seem to be one-off events, a single, colossal blast that never happens again. But in 2016, the Arecibo telescope in Puerto Rico detected a series of bursts coming from the same location in the sky. This proved definitively that at least some FRBs are not caused by cataclysmic, self-destructive events. Whatever engine powers them must survive the outburst to fire again. This was a game-changer. It ruled out theories that involved the total annihilation of an object, like two neutron stars merging or a star collapsing into a black hole. The repeater, officially named FRB 121102, became a Rosetta Stone for the field, allowing astronomers to point other telescopes at its location and finally pinpoint its home galaxy, a small, dwarf galaxy over 3 billion light-years away. So what cosmic engine can produce such immense energy in such a short time, and sometimes do it over and over? The leading candidate for at least some FRBs is a type of neutron star with an almost unimaginably powerful magnetic field, a magnetar. Neutron stars themselves are the incredibly dense cores left behind after a massive star goes supernova. A magnetar is a neutron star on steroids, with a magnetic field 1,000 trillion times stronger than Earth. If a magnetar were located halfway between Earth and the Moon, it would wipe the data from every credit card on the planet. These objects are known to produce violent starquakes and flares as their immensely rigid crusts adjust to the intense magnetic forces. A particularly large starquake could release a tremendous amount of energy in a very short time, potentially producing a flash of radio waves that we would see as an FRB. In 2020, a magnetar within our own Milky Way galaxy emitted a burst of radio waves that, while much weaker than an extragalactic FRB, had a similar profile. This provided the first direct observational link between magnetars and these mysterious bursts, strongly suggesting that at least some FRBs originate from these magnetic monsters. However, the incredible power of the most distant FRBs has led some scientists to wonder if magnetars are powerful enough. This has opened the door to more exotic and even speculative explanations. One theory involves an extreme version of a pulsar, a rapidly spinning neutron star that beams radiation like a lighthouse. If a pulsar were surrounded by a thick torus of gas and dust left over from the supernova that created it, occasional interactions with this material could trigger super-powered bursts. Another idea points to the collision of incredibly dense objects like a neutron star and a black hole. While this would be a one-time event, the energy release would be monumental, potentially explaining the non-repeating burst. And then, of course, there is the possibility that captures the public imagination most strongly. Could FRBs be evidence of advanced technology? It's a tantalizing, though highly speculative, thought. A sufficiently advanced civilization might need unimaginable amounts of energy for interstellar travel or communication. A powerful, focused beam used for propelling light sails on interstellar spacecraft could, from a vast distance, appear to us as a fleeting, incredibly bright radio pulse. While there is zero conclusive evidence for this, and natural explanations are far more likely, the sheer power and brevity of FRBs mean we cannot completely rule out an artificial origin. This possibility ensures that every new FRB detection is scrutinized with intense interest. The hunt for FRBs has now become a global scientific endeavor. New, powerful telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are discovering them by the dozens, sometimes even by the hundreds. CHIME, with its wide field of view, is like a surveillance camera for the radio sky, constantly monitoring and catching these fleeting events. Each new detection provides another piece of the puzzle. By measuring their distances and the types of galaxies they come from, astronomers are beginning to see patterns. Some repeaters seem to originate from galaxies that are actively forming new stars, environments where young magnetars would be common. Other one-off bursts have been traced to more massive, older galaxies, suggesting a different progenitor. This diversity implies that FRBs may not have a single cause. They could be a final, common signal produced by several different cosmic catastrophes. As our telescopes become more sensitive and our catalog of these mysterious bursts grows, we are slowly moving from simply detecting them to truly understanding them. Fast radio bursts represent a new and vibrant frontier in astronomy, reminding us that the universe is still full of violent, sudden, and spectacular surprises. While we scan the skies today with automated systems that catch fast radio bursts by the dozen, one of the most enduring mysteries in the search for extraterrestrial intelligence comes from a much simpler time, a single, tantalizing event that has never been equaled. It was a warm summer night in Ohio, August 15, 1977. Volunteer astronomer Jerry Amon was conducting a routine survey for Ohio State University's Big Ear Radio Telescope, part of the ongoing SETI project. The telescope worked by scanning the sky slowly as the Earth rotated, and data was printed out on long, green-lined computer paper. Days later, Amon was reviewing the pages when his eye caught a sequence of numbers and letters so extraordinary that he circled it in red pen and wrote a single, heartfelt exclamation in the margin: "Wow." That simple annotation gave the signal its immortal name, and it remains one of the most famous and unexplained events in scientific history. So what made this particular signal so remarkable? The Big Ear telescope was tuned to listen near the frequency of 1420 MHz, a protected band of the radio spectrum reserved for astronomical research because it is one of the primary emission lines of neutral hydrogen, the most common element in the universe. The logic was that an advanced civilization might use this universal, watering hole frequency to broadcast its presence. The WOW signal was a narrowband signal, meaning it was concentrated on one very specific frequency, just like an artificial transmitter. In contrast, natural cosmic objects like stars or quasars emit radio waves across a broad spectrum. The signal also exhibited a telltale pattern in its intensity, growing stronger and then fading away over a period of exactly 72 seconds. This was the precise amount of time it took for a fixed point in space to pass through the Big Ear telescope's twin beams due to the rotation of the Earth. The signal's rise and fall matched the telescope's reception pattern perfectly, confirming it originated from deep space and not from a passing airplane or a terrestrial source. The content of the signal itself was not a complex message or a sequence of pulses. Its power was in its sheer, unexpected intensity. The alphanumeric printout recorded the signal's strength using a system where numbers 1 through 9 represented increasing intensity, and letters from our onward indicated values even higher. The WOW signal reached an intensity of 6^5, with the U representing a peak strength about 30 times louder than the background noise of deep space. This was an overwhelmingly powerful transmission. Based on its characteristics, astronomers could pinpoint its likely origin in the constellation Sagittarius, near a star group known as Chi Sagittarii. It had all the hallmarks of an engineered beacon, but then, just as suddenly as it appeared, it was gone. Follow-up observations by the Big Ear telescope and later, more sensitive instruments scanned the same region of sky again and again, hoping for a repeat. They listened for decades. The result was an profound and enduring silence. The signal never returned. Over the years, countless natural explanations have been proposed and systematically ruled out. It was not a signal reflected off a piece of space debris or a satellite, as man-made transmissions are prohibited in that frequency band and no known spacecraft were in the area. It wasn't a random burst from a known astronomical object. Its narrowband nature is completely unnatural. Some suggested it could have been a signal from a passing comet, but the comets proposed were not in that region of the sky at the time. The possibility of a military transmission was investigated, but no such activity was confirmed. Each attempted explanation has fallen short, leaving the signal in a category of its own, a perfect candidate for an extraterrestrial transmission that remains stubbornly unique. The legacy of the WOW signal is a mixture of profound excitement and deep frustration. It stands as a ghost in the machine, a single data point that is both too perfect to ignore and too isolated to verify. It fuels the debate about whether we should be listening for deliberate, continuous beacons or brief, targeted pulses. Perhaps the signal was indeed a one-time event, a momentary scanning beam from a distant civilization that swept across our solar system and moved on, completely unaware that it had been noticed by a fledgling technological species on a pale blue dot. Its enduring mystery serves as a powerful reminder of the challenge of searching for intelligence in a galaxy of unimaginable scale and silence, where a single hello might be whispered only once across the cosmic dark. From the fleeting, powerful scream of the WOW signal, we now turn our attention to a mystery that unfolded over years, a star that didn't just flash once but seemed to be fading away in a pattern that defied all logic. In the constellation Cygnus, about 1,500 light-years from Earth, lies a star that looks perfectly ordinary. It's a bit larger and hotter than our Sun, but to the unaided eye it would be unremarkable. However, this star, officially named KIC 8462852, but better known as Tabby's star after its lead investigator, Tabitha Boyajian, holds a secret that shook the world of astronomy and ignited the public's imagination like few other discoveries. The story begins not with a traditional telescope, but with the unblinking eye of NASA Kepler Space Telescope. Kepler's primary mission was to find planets by staring at a single patch of sky, monitoring the brightness of over 150,000 stars, looking for the telltale, periodic dips in light that occur when a planet passes in front of its host star. These transits are usually tiny, predictable, and symmetrical. A Jupiter-sized planet might cause the star to dim by about 1%, and it does so with clockwork regularity every time it completes an orbit. But the data from Tabby's star was something else entirely. It showed dips that were colossal, irregular, and asymmetrical. The star didn't just dim by a fraction of a percent. it plunged in brightness by up to 22% in some episodes, a drop so enormous it would require an object many times the size of the star itself to block that much light. Furthermore, these dimming events lasted for days or even weeks, and they never repeated in a recognizable pattern. It was as if something vast and strangely shaped was drifting erratically in front of the star, something completely unlike a family of neatly orbiting planets. Faced with this bizarre data, Dr. Boyajian and her team had to consider every possible natural explanation. The first and most prominent hypothesis involved a massive swarm of comets. The idea was that a family of exocomets, perhaps disturbed by a passing star, could have been drawn in towards Tabby's star. As they approached, they would break up, creating a huge cloud of dust and debris that could cause the irregular, deep dimming. This was a plausible, if extraordinary, scenario. However, follow-up observations presented a major problem. When a star is obscured by dust, the dust absorbs some starlight and re-emits it as infrared radiation. When astronomers pointed NASA's Spitzer Space Telescope at Tabby's star, they found a distinct lack of this excess infrared heat. Whatever was blocking the light was surprisingly effective at doing so without getting noticeably warm, a property that made simple dust clouds a less convincing culprit. The absence of a clear natural explanation, combined with the sheer scale of the dimming, inevitably led to a more speculative yet fascinating idea: the alien megastructure hypothesis. This concept, popularized by physicist Freeman Dyson, suggests that a sufficiently advanced civilization might eventually need to harness the entire energy output of its star. To do this, they could construct a vast array of solar collectors, a Dyson sphere, encircling the star. Such a structure would not be a solid shell, but rather a loose swarm of orbiting platforms that would capture starlight, causing the irregular, deep dimming patterns exactly like those observed at Tabby's star. The idea captured the public's imagination because it was a testable, if incredible, hypothesis. If aliens were building such a thing, it would be the most monumental discovery in human history. For a time, even the scientists involved, while deeply skeptical, acknowledged that the anomaly was severe enough to warrant checking for such technosignatures. The Breakthrough Listen project even dedicated time on the Green Bank telescope to listen for any artificial radio signals coming from the system, but none were found. The real breakthrough in understanding Tabby's star came from an unprecedented public effort. When traditional observatory time proved insufficient to monitor the star continuously, Dr. Boyajian and her colleagues launched a Kickstarter campaign, raising over $100,000 from more than 1,700 backers to secure dedicated time on a global network of ground-based telescopes. This allowed for round-the-clock coverage, and in 2017, the star entered a major dimming period, and this time astronomers were watching. They were able to capture detailed spectra breaking down the starlight by wavelength as it passed through whatever was causing the dimming. The results were definitive. The spectra showed that the dimming was much more pronounced at blue wavelengths than at red wavelengths. This is a classic signature of light scattering off tiny particles. It's the same reason our sky is blue. Sunlight is scattered more effectively by the tiny molecules in our atmosphere, which preferentially scatter blue light. The data pointed conclusively to dust. Not a solid megastructure, but a cloud of fine particles smaller than a micrometer in size. So the mystery is solved, right, not quite. While the alien megastructure theory has been effectively ruled out, the precise nature of the dust cloud remains an active puzzle. What could create such enormous, irregular clouds of fine dust around a star? The original comet swarm idea is still in the running, but it requires a truly immense number of comets to explain the deepest dips. Other theories suggest that the star might have recently consumed a planet, and the resulting debris is now occulting its light. Or perhaps Tabby's star has a highly variable and unusual dust-producing disk, unlike the smooth rings we see around younger stars. The key lesson from Tabby's star is that it revealed a new type of astrophysical phenomenon. It showed us that stars can behave in ways our textbooks never predicted. It forced astronomers to develop new models and to be humbled by the complexity of the cosmos. The star continues to be monitored, and each new dimming event provides more clues. Tabby's star stands as a powerful testament to the scientific process, a reminder that sometimes the most exciting discoveries are not the ones we go looking for, but the strange, unexpected anomalies that challenge our understanding and push us to ask better questions. Just when we thought we had catalogued the most peculiar objects in our own cosmic backyard, the universe delivered a visitor from a place beyond our sun's influence, an object that challenged our very definitions of what a celestial body can be. In October 2017, astronomers at the Pan-STARRS Observatory in Hawaii detected a faint point of light moving at breathtaking speed. Its trajectory was immediately and profoundly different from anything else we had ever seen. Unlike the countless asteroids and comets that orbit our sun, this object was not bound by its gravity. It was falling from above the plane of our solar system. It swung around the sun, and it was leaving, never to return. This was Oumuamua, a name from Hawaiian meaning a messenger from afar arriving first, and it was the very first confirmed interstellar object ever detected passing through our system. The initial data revealed an object moving so fast that it could only have originated from another star, but as astronomers scrambled to observe it during its brief flyby, the peculiarities began to mount. The first major surprise came when they tried to determine its shape. By measuring how its brightness changed over time, they could infer its rotation. Most asteroids are lumpy and irregular, causing a modest variation in light. Oumuamua, however, exhibited extreme changes in brightness, dimming and brightening by a factor of 10 as it tumbled. This suggested an object that was dramatically elongated, shaped something like a cigar or a pancake, with a length perhaps up to 10 times greater than its width. This was an oddity in itself, as most natural objects in our solar system are not so extremely proportioned. But the real mystery was yet to come. As Oumuamua sped away from the sun, something unexpected happened. Its path could not be explained by gravity alone. Once it passed its closest approach to the sun, its outward velocity was slightly higher than predicted by the gravitational pull of the sun and planets. It was experiencing a tiny but persistent non-gravitational acceleration, as if being gently pushed. For comets, this is a common phenomenon. Heat from the sun vaporizes ice on their surface, creating jets of gas that act like tiny rocket engines. The telltale sign of this outgassing is a coma, a fuzzy envelope of gas and dust that surrounds the comet's nucleus, and often a tail that streams behind it. Astronomers pointed every available telescope at Oumuamua, searching for this coma or any sign of outgassing. They found absolutely nothing: no gas, no dust, no tail. It was as dark and inert as a rock, yet it was accelerating as if it were an active comet. This contradiction lay at the heart of the enigma. Scientists have worked diligently to propose natural explanations for this bizarre behavior. One leading idea posits that Oumuamua could have been a hydrogen iceberg. In the coldest, densest cores of giant molecular clouds, temperatures can be so low that hydrogen gas freezes solid. A chunk of solid hydrogen, when approached by a star like our Sun, would begin to sublimate, turn directly from a solid to a gas. Because hydrogen is so light and transparent, this outgassing would be virtually invisible to our telescopes, yet it could provide the precise kind of gentle push needed to explain the acceleration. The problem is that such an object would be incredibly fragile. It's debated whether a hydrogen iceberg could survive a journey through interstellar space, constantly bombarded by cosmic rays and starlight, long enough to reach our solar system. Another compelling theory suggests Oumuamua was a fragment of a nitrogen ice shell, similar to the surface of Pluto or Neptune's moon Triton. A chunk of nitrogen ice breaking off from a distant Pluto-like planet would also sublimate in sunlight, producing an invisible jet of nitrogen gas that could account for the acceleration. This nitrogen iceberg model also offers an explanation for the object's strange shape. As the nitrogen ice eroded away over millions of years, it could have worn down into a flattened, pancake-like slab, which aligns with some interpretations of the light curve data. While this is a more robust material than hydrogen, the theory requires that a vast amount of nitrogen ice was somehow blasted off its parent body, which is a dramatic event in itself. The combination of Oumuamua's unusual shape, its complete lack of a visible coma, and its mysterious non-gravitational acceleration led some scientists, most notably Harvard astronomer Avi Loeb, to propose a more extraordinary hypothesis that Oumuamua could be a piece of advanced alien technology. Specifically, Loeb suggested it might be a light sail, a vast, thin sheet designed to be pushed by the radiation pressure of starlight. A light sail of the right thickness and size could account for the observed acceleration without needing any outgassing at all. Its flattened, pancake-like shape would be a perfect design for such a vessel. In this scenario, Oumuamua would not be a directed probe, but perhaps a discarded piece of a larger craft, a kind of cosmic buoy or a defunct solar sail drifting aimlessly through the galaxy. This idea, while highly speculative and considered unlikely by most astronomers, is technically testable. If there are more objects like Oumuamua, and if they show similar anomalous properties, it might point toward a manufactured origin. The fundamental challenge is that Oumuamua is now gone, far beyond the reach of our telescopes, its secrets receding into the darkness. We only had a few weeks of frantic observations, a fleeting glimpse of a stranger passing through town. The ultimate lesson of Oumuamua may not be a definitive answer about its nature, but a profound shift in perspective. Its visit told us that interstellar objects are not merely theoretical, they are real, and they are passing through our solar system with some frequency. This realization has spurred plans for new missions, like the European Space Agency's Comet Interceptor, which could be redirected to study such an object if another is discovered on an approachable trajectory. Oumuamua was a messenger, all right. It delivered a clear message that our solar system is not an isolated island, but part of a dynamic and interconnected galactic community, and that future visitors from the depths of space will undoubtedly bring new mysteries for us to solve. As our spacecraft venture deeper into the void, they sometimes send back data that doesn't quite fit our expectations, revealing subtle forces at work in the seemingly empty expanse of space. A perfect example of this emerged not from a distant star, but from two of our own robotic explorers, Pioneer 10 and Pioneer 11. Launched in the early 1970s, these pioneering craft were the first to journey through the asteroid belt, the first to make close observations of Jupiter and Saturn, and the first human-made objects destined to leave our solar system entirely. For decades after their primary missions were complete, scientists continued to track their trajectories with exquisite precision, using their radio signals to measure their speed and position. And that is when they noticed something deeply puzzling. Both spacecraft were experiencing a tiny but persistent and completely unaccounted for deceleration. It was as if a faint phantom force was ever so gently tapping the brakes, pulling them back toward the sun. This deviation was minuscule, a drift of just a few thousand miles over the course of a decade, an effect about 10 billion times weaker than the gravity we feel on Earth's surface. But in the precise world of orbital mechanics, where calculations must account for the gravitational pull of every planet, moon, and large asteroid, this tiny anomaly was a glaring inconsistency. It became known as the Pioneer Anomaly. For years, it lingered as an unsolved mystery on the fringes of physics. Could it be evidence of a flaw in our understanding of gravity itself? Some theorists proposed that perhaps Newton's law of universal gravitation needed a slight modification over very large distances, an idea that would have revolutionary implications for all of cosmology. Others wondered if it was a sign of something more exotic, like the gravitational pull of unseen dark matter clustered around our solar system. The anomaly was a classic scientific mystery, a small, stubborn data point that refused to go away, challenging the prevailing models. The key to solving the puzzle, however, lay not in rewriting the laws of physics, but in a far more mundane and ingenious direction: heat. The Pioneer spacecraft were powered by radioisotope thermoelectric generators, or RTG. These devices create electricity from the heat generated by the natural decay of plutonium. While incredibly reliable for long-duration missions, they also make the spacecraft quite warm. A team of scientists led by Slava Turishev began a monumental effort to recover and analyze decades-old data, including even original blueprints and design documents, to create a highly detailed thermal model of the Pioneer probes. They realized that the heat from the RTGs and the onboard electronics was not radiating away from the spacecraft uniformly. Most of this thermal radiation was emitted from the sides of the craft. However, a small but significant fraction was being reflected off the back of the spacecraft's main antenna dish. Think of it like this: if you were in space and you turned on a flashlight, the light photons leaving the flashlight would impart a tiny amount of thrust in the opposite direction. This is the basic principle of a photon rocket. Now, imagine that flashlight is pointing away from the direction you want to go. The photons push you backward. This is exactly what was happening to the Pioneer spacecraft. The heat radiating from the electrical systems was acting like a very weak photon rocket. The asymmetric design of the craft meant that more of this thermal radiation was being emitted in the direction opposite to their motion toward the sun than was being emitted forward. This created a constant, tiny pressure that very slowly bled off their outward velocity. It was an effect so small that it had been overlooked in the original mission planning, but over billions of miles of travel, it added up to a detectable discrepancy. The solution was a triumph of meticulous, long-term scientific detective work. When the team finally completed their painstaking analysis, accounting for every watt of heat and its direction of emission, the predicted deceleration matched the observed anomaly almost perfectly. The phantom force had been identified. It wasn't dark matter or new physics. It was the gentle, relentless push of their own body heat. The case of the Pioneer anomaly was officially closed. But its legacy is profoundly important. It serves as a powerful reminder of the necessity of extreme precision in our exploration of the cosmos. It shows that even the most well-understood systems, like the simple radiation of heat, can produce unexpected consequences in the unforgiving environment of space, where there is no atmosphere to dampen such subtle effects. This lesson is now directly applied to missions like New Horizons, which flew by Pluto, where engineers carefully modeled the spacecraft's thermal radiation to ensure its trajectory remained perfectly on course. The Pioneer anomaly, though solved, stands as a testament to the fact that sometimes the biggest mysteries have the most ordinary explanations, hiding in plain sight all along. Leaving behind the subtle phantom force that nudged our Pioneer probes, we journey much further out into the solar system, to a region of twilight and ice where the sun is just a particularly bright star. Beyond the orbit of Neptune lies a vast, donut-shaped expanse known as the Kuiper Belt, a cosmic junkyard filled with frozen remnants from the solar system's birth. For decades, astronomers theorized this belt was immense, stretching far into the darkness, a gradated collection of icy worlds that would slowly diminish in number the farther out you went. But when they finally gained the technology to survey this distant realm, they found something profoundly unexpected. Instead of a gradual fade, the Kuiper Belt comes to a screeching, inexplicable halt. It's as if you were walking through a forest that suddenly ends at a sharp, straight edge, with nothing but empty plains beyond. This dramatic drop-off is known as the Kuiper Belt Cliff, and its existence challenges our most fundamental ideas about how our planetary system was built. The discovery of this cliff was a gradual process that came into focus as our telescopes grew more powerful. The Kuiper Belt is home to dwarf planets like Pluto, Haumea, and Makemake, but it also contains countless smaller icy bodies, often called Kuiper Belt objects. By carefully mapping the orbits of these objects, astronomers could build a census of the belt's population. They expected to find a smooth distribution, with the number of objects decreasing steadily as they moved away from the Sun, governed by the thinning density of the primordial disk from which they formed. But the data revealed a starkly different picture. At a distance of about 50 astronomical units from the Sun, 10 being the distance from Earth to the Sun, the population of these icy bodies plummets. Beyond this boundary, the vast reservoir of objects we anticipate simply isn't there. It's not a gentle slope, it's a cliff edge, and we are left staring into an emptiness that, according to our models, should be teeming with frozen fossils. This presents a classic scientific puzzle. When observations violently disagree with theory, it usually means the theory is missing a crucial piece of the story. The leading explanation for the cliff invokes a gravitational architect, a massive unseen object whose pull has sculpted the outer solar system. This is the Planet 9 hypothesis. The idea is that a planet, perhaps 5 to 10 times the mass of Earth, orbits the Sun on a highly elongated path far beyond the Kuiper Belt. As this hypothetical world swings through its multi-thousand-year orbit, its immense gravity would act like a shepherd clearing out a vast swath of space. It would gravitationally scatter smaller objects, flinging some inward and ejecting others from the solar system entirely, creating a sharp boundary at the edge of its influence. The Kuiper Belt cliff would be the permanent scar left by this distant giant, a testament to its gravitational power. This theory is bolstered by other orbital oddities, like the fact that a group of the most distant Kuiper Belt objects have orbits that are mysteriously clustered, as if they are all being herded by the same unseen force. However, not all scientists are convinced that a new planet is the only answer. An alternative line of thinking suggests that the cliff might be a primordial feature, a frozen snapshot of the conditions in the infant solar system. Our planetary system formed from a swirling disk of gas and dust surrounding the young Sun. In the outer reaches, where temperatures were cold enough for ices to form, this disk likely had its own inherent structure. It might have possessed a natural drop in density, perhaps caused by a pressure wave or a resonance from the disk's interaction with the newborn gas giants like Jupiter and Saturn. In this scenario, the Kuiper Belt cliff marks the original outer edge of the planet-forming disk itself. The material beyond that point was simply too sparse to coalesce into many sizable objects, leaving the dramatic cutoff we see today. This explanation is more parsimonious, as it doesn't require the existence of an undiscovered world, but it struggles to explain the other gravitational anomalies, like the orbital clustering, as neatly as the Planet 9 hypothesis does. There is also a third, more dramatic possibility that the cliff is evidence of a cosmic theft. Early in the Sun's life, it was born in a crowded stellar nursery alongside thousands of other baby stars. These stars would have passed much closer to each other than they do today in the relatively empty galactic neighborhood. A close flyby from a sibling star could have gravitationally ripped away the outer portion of our Kuiper Belt, stripping away countless icy bodies and carrying them off into interstellar space. This stellar encounter would have sheared off the outer disk, leaving behind the sharp edge we observe. If true, our solar system's frozen frontier was violently pruned by a passing star billions of years ago, and the cliff is the remaining stump. The search for a definitive answer is ongoing. Astronomers are conducting ever more sensitive surveys of the sky, hoping to directly image Planet 9 if it exists. At the same time, they are refining models of protoplanetary disks to see if they can naturally produce such a sharp density drop, the Vera C. Rubin Observatory, set to begin operations soon, will scan the entire sky with unprecedented depth and could finally settle the debate by either discovering the hypothetical planet or by mapping the orbital distribution of distant Kuiper Belt objects with such precision that we can rule out certain formation scenarios. The Kuiper Belt cliff is more than just a curious feature on a map. It is a profound clue about the dramatic events that shaped our cosmic home, whether by the hand of a hidden giant planet, the quiet conditions of its birth, or a long-ago stellar encounter that robbed us of our outer riches. While the Kuiper Belt cliff presents a boundary shaped by immense gravitational forces, our next mystery takes us to a world where the atmosphere itself has been sculpted into a shape of breathtaking geometric perfection. At Saturn's North Pole, a feature exists that looks less like a natural weather pattern and more like a piece of cosmic art. A massive, six-sided hexagon with each side longer than the diameter of Earth. This is not a static structure of rock or ice, but a persistent high-speed jet stream, a swirling storm of unimaginable scale that has maintained its precise shape for decades and possibly even centuries. Discovered by the Voyager spacecraft in the 1980s and later studied in stunning detail by the Cassini mission, the Saturn hexagon is a phenomenon without parallel in our solar system, a puzzle written in clouds and wind that challenges our understanding of planetary weather. The sheer scale of this feature is difficult to comprehend. Each side of the hexagon stretches nearly 9,000 miles, and the entire structure rotates with a period of about 10 hours and 30 minutes, which appears to be tied to the rotation of Saturn's deep interior. Inside this gargantuan geometric border, chaotic storms brew, including a central vortex that resembles a vast, swirling eye. What makes the hexagon so perplexing is its stability. Hurricane systems on Earth form and dissipate over days or weeks, their shapes constantly shifting with the turbulent atmosphere. The Great Red Spot on Jupiter is a long-lived storm, but it is a simple, albeit gigantic, oval. Saturn's hexagon, by contrast, has retained its sharp, six-sided form across multiple decades of continuous observation, resisting the natural tendency of fluids to dissolve into chaos. It is a monument of order within a tempest. To understand how such a shape could arise, scientists have turned not to telescopes but to laboratory experiments. Researchers at Oxford University created a simple but elegant model, a circular tank filled with water representing a planet's atmosphere. They placed this tank on a rotating table to simulate the planet's spin. At the center of the tank, a small ring circulated the water, creating a flow that mimicked the jet stream on a gas giant. When they sped up the rotation and adjusted the flow rate, something remarkable happened. The circular flow began to distort, not into a random shape but into stable polygons. They observed not only hexagons but also triangles, squares, and octagons. The key ingredient was the speed difference between the rotating fluid and the central jet stream. At certain shear velocities, the flow naturally organized itself into these geometric patterns. This demonstrated that the hexagon isn't necessarily a sign of alien engineering, but a potential emergent property of fluid dynamics under specific conditions. The laboratory experiments point toward an explanation rooted in the physics of wave propagation. The hexagon is likely a standing wave pattern, a kind of Rossby wave, frozen in place by Saturn's rapid rotation. On Earth, Rossby waves are massive meanders in high-altitude jet streams that influence our weather patterns. On Saturn, the conditions are far more extreme. The planet's rotation is incredibly fast. A day on Saturn is only about 10.5 hours long, and its atmosphere is composed primarily of hydrogen and helium, creating a fluid system of immense depth and scale. Theorists suggest that deep within Saturn's atmosphere, smaller disturbances or shear instabilities generate waves that travel upward. As these waves rise, Saturn's rapid rotation and the specific wind shear at certain latitudes can cause these waves to refract and reinforce each other, locking into a stable, polygonal pattern. The hexagon shape may simply be the one that fits most naturally within the specific speed and density parameters of Saturn's polar atmosphere. Yet, even with this plausible explanation, profound questions remain. Why a hexagon? Why is this shape so stable over such long periods when the laboratory analogues are often more transient? And most intriguingly, why don't we see similar features on other gas giants? Jupiter has powerful jet streams and polar vortices, but nothing with the geometric regularity of Saturn's hexagon. This suggests that Saturn possesses a unique combination of factors. Perhaps its internal heat flow, the precise depth of its jet streams, or the composition of its upper atmosphere that make it a special factory for this kind of ordered chaos. The hexagon is a natural laboratory for fluid dynamics on a scale we could never replicate on Earth, offering a glimpse into the fundamental behaviors of fluids under the influence of rapid rotation. Its enduring presence reminds us that the laws of physics can produce patterns of stunning beauty and complexity, a six-sided signature written in the clouds of a distant world. From the ordered geometric storm on Saturn, we plunge into the thick, toxic atmosphere of our planetary neighbor, Venus, a world that presents a mystery not of physics but of potential biology. In September 2020, a team of astronomers made an announcement that sent shockwaves through the scientific community and captured the global imagination. They reported the detection of phosphine gas in the cloud decks of Venus. Now, on its own, phosphine might not sound particularly exciting, but in the context of a planet like Venus, it is a gas that should not be there. On Earth, phosphine is primarily associated with life. It is produced by anaerobic bacteria in environments like swamps and the guts of animals, and it can be manufactured industrially. Crucially, in an oxygen-rich atmosphere like ours, phosphine is unstable and breaks down quickly. The same is true for the hellish surface of Venus with its scorching temperatures and crushing pressure. But the researchers found the phosphine signature not on the surface, but about 50 kilometers up, in a temperate layer of the Venusian clouds where the pressure and temperature are surprisingly similar to those on Earth. In this hostile environment, all known geological and chemical processes should destroy phosphine rapidly. The tantalizing implication was that something, perhaps microbial life floating in the clouds, must be constantly producing it. The initial discovery was the result of meticulous work. The team, led by Jane Greaves of Cardiff University, used two of the world's most powerful radio telescopes, the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array, or ALMA, in Chile. These instruments are not like optical telescopes that see visible light. They detect radio waves emitted by molecules in space. Every molecule has a unique fingerprint, a specific frequency at which it absorbs or emits light. The team identified a dip in the radio spectrum coming from Venus's clouds that matched the precise signature of phosphine. After painstakingly ruling out other possible molecules, they calculated that the concentration of phosphine was about 20 parts per billion. That may seem tiny, but given the expected destruction rates, it was a significant amount that demanded an explanation. The announcement was made with cautious excitement, framed not as a discovery of life, but as an anomalous and unexplained chemical signature that was consistent with a potential biosignature. The scientific response was immediate, intense, and deeply critical, exactly how the process of science is supposed to work. Other research groups around the world began to independently reanalyze the same data. The first major challenge came from a team that questioned the data processing itself. They argued that the signal processing technique used by the original team, which involved subtracting a complex background to isolate the phosphine signal, might have inadvertently created a false signal or amplified noise to look like a real one. When they applied a different method of analysis, the phosphine signal became much weaker, or in some cases vanished entirely. This sparked a technical debate over which data reduction process was more reliable, a classic example of how challenging it can be to extract a faint signal from a noisy dataset, especially when observing a bright, complex object like a planet. Beyond the data processing, other scientists attacked the problem from a different angle. Were there any non-biological or abiotic ways to produce phosphine on Venus that we simply hadn't thought of? The search was on for a purely geological or chemical explanation. Could volcanic eruptions spew gases high into the atmosphere that could then react to form phosphine? Venus is known to be volcanically active, but the amounts of phosphine detected would require an immense, sustained level of volcanic activity far beyond what we currently observe. Could sunlight interacting with Venusian surface minerals or atmospheric compounds create it? Laboratory experiments and new atmospheric models were run, but so far, no proposed abiotic mechanism has convincingly reproduced the claimed phosphine levels without requiring assumptions that seem improbable given our current understanding of Venus. The debate raged back and forth in scientific journals, with papers being published that supported the detection, followed by others that refuted it, creating a public perception of a scientific roller coaster. The case of Venusian phosphine serves as a profound and necessary lesson in the scientific search for extraterrestrial life. It highlights the immense difficulty of remote sensing. We are trying to detect the faintest whispers of specific molecules from tens of millions of miles away, using incredibly complex instruments and data analysis techniques. What seems like a clear signal at first can often dissolve under more rigorous scrutiny. This process, while sometimes frustrating, is essential to avoid false positives and to build a robust case for a discovery as monumental as life beyond Earth. The phosphine story also underscores the importance of fully understanding a planet's environment before interpreting a biosignature. A gas that is a clear sign of life on one world could be produced by a strange, unknown geochemical process on another. We cannot assume that life elsewhere will follow the exact same rules as life on Earth. Ultimately, the controversy has not been definitively settled, but the initial excitement has certainly been tempered by healthy skepticism. Subsequent observations, including a re-examination by the SOFIA Airborne Telescope, failed to confirm the detection. The original Oumuamua data was also reprocessed by the observatory itself, and the team acknowledged that the signal was weaker than first reported, though they maintained that it is still present. The quest for answers continues, driving a renewed interest in Venus exploration. Several new missions like NASA Da Vinci and Veritas and the European Space Agency's Envision are planned for the coming decade. These spacecraft will study Venus's atmosphere and geology in unprecedented detail, and they may finally be able to either confirm the presence of phosphine or put the mystery to rest. Regardless of the outcome, the Venus phosphine episode was a watershed moment. It reminded us that our closest planetary neighbor, long dismissed as a sterile hellscape, might still hold profound secrets. It galvanized a new generation of scientists to look at Venus not as a dead end, but as a world worthy of exploration in the ongoing search for life in the universe. While the debate over Venusian phosphine highlights the challenges of searching for life's chemical signatures in a hostile environment, our search for life beyond Earth has a much longer and equally perplexing focus: the planet Mars. For centuries, we've looked at our rusty neighbor with a mix of hope and scientific curiosity, and in recent decades, one particular molecule has emerged as the central character in this cosmic detective story: methane. On Earth, the vast majority of methane in our atmosphere is produced by biological processes. It's a waste product from microbes in wetlands, the digestive systems of livestock, and even the decomposition of organic matter in landfills. So, when our robotic explorers on Mars started sniffing out traces of this gas, the immediate and thrilling question was, could this be a sign of Martian life? The story of Martian methane is one of sporadic and contradictory clues, beginning with tantalizing hints from orbit. In 2004, scientists analyzing data from the European Space Agency's Mars Express orbiter reported the first definitive detection of methane in the Martian atmosphere. But this wasn't a constant, steady presence. The methane seemed to appear in localized plumes and then it would vanish. This transient nature is a critical part of the mystery. Methane molecules in the Martian atmosphere should be broken down by ultraviolet radiation from the sun within a few hundred years. The fact that we see it at all means it must have been released relatively recently. And the fact that it appears in sudden bursts suggests an ongoing, episodic source, rather than a slow, constant leak from some ancient reservoir. This initial discovery was followed by a series of ground-level confirmations that added even more layers of intrigue. NASA Curiosity rover, which has been exploring Gale crater since 2012, is equipped with a sophisticated onboard chemistry lab called the Sample Analysis at Mars, or SAM. SAM has repeatedly detected low background levels of methane, around 0.41 parts per billion on average, but it has also recorded several dramatic spikes where methane concentrations soared to levels around 10 times higher, lasting for only a few weeks before dissipating. These spikes are like sudden, faint puffs of smoke, and their origin is a complete enigma. Even more puzzling is the fact that the European-Russian Trace Gas Orbiter, a spacecraft specifically designed to conduct a precise inventory of the Martian atmosphere with superior instruments, has consistently failed to detect any methane at all in the global atmosphere. This contradiction isn't necessarily a sign that one team is wrong and another is right. It likely points to the incredibly localized and fleeting nature of the releases. The orbiter might be looking at the wrong place at the wrong time, or averaging out the tiny plumes over the entire planet, while the rover is sitting right next to the source of a temporary leak. So, if methane is indeed being released on Mars, where is it coming from? Scientists have two primary lines of investigation, one geological and one biological. The leading geological explanation involves a process called serpentinization. This occurs when certain iron and magnesium-rich rocks, like olivine, come into contact with water in a chemical reaction that produces methane as a byproduct. This process doesn't require life. It's simple abiotic chemistry that occurs deep underground. On Mars, if there are still pockets of liquid water interacting with the planet's subsurface geology, serpentinization could be producing these methane burps. This is a perfectly plausible explanation, especially given the evidence for vast underground reservoirs of water ice and the possibility of briny, liquid water aquifers. The challenge is that we haven't yet directly observed active serpentinization on Mars. The other possibility, of course, is the one that captures our imagination: subsurface life. Mars was once a much warmer and wetter world, with rivers, lakes, and possibly even a vast ocean. It's conceivable that microbial life could have arisen billions of years ago. If it did, some organisms might have retreated deep underground as the surface became cold and irradiated, finding refuge in deep aquifers where liquid water might still persist. In these isolated pockets, a community of methanogenic microbes could be thriving, producing methane just as their counterparts do on Earth in deep-sea vents or underground caves. The sporadic nature of the releases could be explained by geological activity. A small marsquark or a shift in the ground could temporarily open a vent, allowing the built-up gas to escape into the atmosphere above Curiosity's location. The difficulty in distinguishing between these two sources lies in the fact that a methane molecule produced by a microbe is chemically identical to one produced by a rock. To tell them apart, scientists would need to look for other clues. One powerful method is to examine the carbon isotopes within the methane. Life on Earth has a preference for lighter isotopes of carbon, carbon-12, over the heavier carbon-13. If Martian methane were found to be significantly enriched in carbon-12, it would be a strong, though not conclusive, indicator of a biological origin. The instruments on current missions are not quite sensitive enough to make this measurement with the precision required, but it is a key goal for future rovers and sample return missions. The mystery of Martian methane is far from solved. It's a puzzle of timing, location, and chemistry. Each new detection and non-detection adds another piece, forcing us to refine our models of the Martian subsurface and its potential for habitability. The quest to find the source is driving the next generation of exploration, with missions designed to drill deeper, analyze more precisely, and perhaps even bring a sample of the Martian regolith back to Earth for definitive analysis. The faint whiffs of methane are like a siren's call, drawing us closer to answering one of humanity's oldest questions. Are we truly alone in the solar system, or is there, hidden beneath the red sands of Mars, a silent, subterranean whisper of life? Turning from the fleeting chemical whispers of Mars, we arrive at a mystery written in the very rock beneath our feet and the brilliant companion that lights our night sky. The origin of our moon is a question that has captivated humanity for millennia, and for much of that time, the leading theories were elegant but deeply flawed. One early idea suggested that the moon was a world once independent, captured by Earth's gravity as it wandered too close. But the physics of such a gentle capture in a stable, circular orbit is incredibly unlikely. Another proposed that the Earth and Moon formed together as a double planet from the same primordial cloud of dust and gas. While this sounds plausible, it ran into a major problem revealed by the Apollo missions. The Moon is far less dense than Earth, possessing a tiny iron core compared to our planet's massive metal heart. If they were twins born of the same material, their internal structures should be much more similar. These dead ends set the stage for a theory that is both violent and beautiful, a catastrophic birth that may have been the essential precondition for our own existence, the giant impact hypothesis. Picture the solar system in its infancy, a chaotic construction zone filled with hundreds of fledgling planets, called planetesimals, colliding and merging in a violent gravitational dance. About 4.5 billion years ago, the proto-Earth was nearly fully formed when a cataclysm of almost unimaginable scale occurred. A Mars-sized planet, which scientists have named Theia after the mythological Greek Titan who was the mother of the moon goddess Selene, slammed into the young Earth. This was not a simple sideswipe, it was a colossal, glancing blow. The impact was so energetic that it completely obliterated Theia and vaporized a significant portion of Earth's mantle, hurling a colossal cloud of superheated rock and metal vapor into orbit around our wounded planet. In a remarkably short time, perhaps only a century, this incandescent disk of debris began to cool and accrete, clumping together under its own gravity to form what we now see as the Moon. This single event explains so much. The Moon's low density is a direct result of it forming primarily from the mantles of both worlds, while the heavier iron cores of Theia and Earth merged, sinking to the center of our newly enlarged planet. The evidence for this dramatic origin story is compelling, and much of it was brought back by the Apollo astronauts. The lunar rocks they returned were found to be surprisingly dry, lacking the volatile elements that boil away at low temperatures. This is exactly what you would expect from material that was vaporized in a high-energy impact and then cooled in the vacuum of space. Furthermore, the Moon's core is small and contains a lower proportion of heavy, siderophile or iron-loving elements compared to Earth. These elements, like gold and platinum, should have been dragged into Earth's core during the impact when the metals from both bodies mixed and sank. The fact that the Moon is depleted in them strongly suggests it formed from the mantle material that was flung into orbit after the metallic cores had already merged. However, this elegant theory has recently been challenged by a discovery that has sent planetary scientists back to the drawing board. When researchers analyzed the chemical fingerprints of rocks specifically, the ratios of different isotopes of elements like oxygen, titanium, and tungsten, they find that the Earth and the Moon are astonishingly similar, almost like twins. This is a major problem. The giant impact hypothesis predicts that the Moon should be composed mostly of Theia. Since Theia formed in a different part of the solar system, it should have had a distinct isotopic signature different from Earth. The Moon, therefore, should carry the chemical ghost of this alien world, but the analyses show virtually no difference. It's as if Theia and Earth were isotopic clones, which is statistically nearly impossible for two independent planets. This isotopic crisis has forced scientists to propose new, even more dramatic versions of the impact scenario. One possibility is that the impact was far more extreme than originally thought. Instead of a glancing blow, Theia might have struck the early Earth with such force that the two planets completely vaporized and merged into a seething, spinning cloud of rock vapor called a synestia. Within this donut-shaped inferno, the material from both bodies would have been thoroughly mixed for a prolonged period before the Moon and Earth condensed out separately. This would have homogenized their isotopic compositions, creating the similarity we see today. Another theory suggests that Theia was not a stranger at all, but formed at the same orbital distance from the Sun as Earth, a sibling world from the very beginning, which would explain their chemical kinship. Both of these ideas push the boundaries of our simulations and demand a rethinking of the dynamics of the early solar system. The origin of the Moon is more than just a historical curiosity. It is intimately linked to the potential for life on Earth. The colossal impact likely gave Earth its rapid 24-hour rotation and its tilted axis, which gives us our seasons. Some scientists even argue that the addition of material from Theia delivered essential volatile elements to our planet, or that the Moon's stable gravitational influence has helped to stabilize Earth's climate over billions of years, creating a more hospitable environment for evolution. The violent birth of our celestial companion may have been the very event that made our world a living world. Solving the remaining puzzles of the Moon's formation is not just about understanding a rock in the sky. It is about uncovering the pivotal chapter in our own planet's story, a cataclysm that set the stage for everything that was to come. Yet even after solving the puzzle of our Moon's violent birth, we find that the very earliest moments of the universe hold their own enduring mysteries, written not in rock but in the primordial elements forged in the cosmic fireball itself. Our journey now takes us back to the first 3 minutes of existence, to a problem so fundamental it challenges the very model of the Big Bang. This is the cosmic lithium problem, and it begins with one of the most triumphant successes in all of science: Big Bang nucleosynthesis. Imagine the universe as a seething, unimaginably hot and dense soup of fundamental particles. Within the first second, protons and neutrons begin to form. For a brief window, between about 1 second and 20 minutes after the Big Bang, the entire cosmos was hot enough to act as a nuclear fusion reactor. But it was expanding and cooling so rapidly that this window slammed shut almost immediately. In that frantic, fleeting moment, the first atomic nuclei were forged. Protons and neutrons collided to form deuterium, the heavy isotope of hydrogen. These deuterium nuclei then fused with more particles to create helium and trace amounts of the next element, lithium. The brilliant insight of physicists like George Gamow, Ralph Alpher, and Robert Herman was to realize that the relative amounts of these primordial elements, hydrogen, helium, deuterium, and lithium, depend critically on just one number: the density of ordinary matter, or baryons, in the early universe. This makes Big Bang nucleosynthesis a precise cosmological probe. If we can measure the amount of primordial deuterium or helium in the universe today, we can calculate the baryon density, and this prediction should perfectly match the density we measure from other methods, like mapping the cosmic microwave background. For the most part, this agreement is spectacularly good. The predicted and observed abundances of deuterium and helium-4 align beautifully, providing one of the strongest pillars of evidence for the Big Bang theory. But there is one glaring exception. When it comes to lithium-7, the most common isotope of lithium, the theory and observations are in violent disagreement. The models predict that the Big Bang should have produced about 3 to 4 times more lithium than what we actually find in the oldest stars in our galaxy. These ancient stellar relics, known as population 3 and 2 stars, formed from nearly pristine gas that had not been polluted by later generations of star formation. They act as cosmic time capsules, preserving the chemical composition of the early universe, and when we analyze their atmospheres, the amount of lithium is consistently and puzzlingly low. It's as if a master chef followed a recipe perfectly, but one key ingredient consistently came up short, suggesting a fundamental flaw in our understanding of the kitchen itself. So where did the lithium go, or was it never made in the predicted amounts to begin with? Scientists have pursued two main paths to solve this inconsistency, one looking inward at the stars themselves and the other looking outward to new physics. The stellar solution proposes that the lithium isn't missing from the universe, it's just missing from the stellar atmospheres we observe. These ancient stars are not simple, inert containers. They have complex internal structures and mixing processes. One possibility is that the lithium in their outer layers slowly sinks or diffuses down into the hotter interior over billions of years. Once it reaches a region hot enough for nuclear fusion, the fragile lithium nuclei are destroyed, fused into heavier elements like helium. This would explain why we see less lithium on the surface today. Another idea involves these stars having unusually thick outer convective zones. If the surface gas circulates deep enough to reach temperatures where lithium burns, it could be systematically destroyed. While these are plausible mechanisms, the problem is that they require a fine-tuning of stellar physics that seems to apply to nearly every single ancient star we observe, which is a difficult assumption to maintain. The more radical solution is to question the nuclear physics of the first 3 minutes. Perhaps our understanding of the nuclear reaction rates during Big Bang nucleosynthesis is incomplete. The chain of reactions that creates lithium-7 is delicate. It primarily forms from the decay of beryllium-7. If there was an unknown nuclear reaction path that destroyed beryllium-7 before it could decay into lithium, or if the cross-sections, the probabilities of certain key reactions are slightly different than what we've measured in laboratories on Earth, it could resolve the discrepancy. However, laboratory measurements of these nuclear processes have become incredibly precise, and no major adjustments have been found that could account for the full factor of 3 difference without throwing off the excellent agreement we have with deuterium and helium. This leads to the most exciting, albeit speculative, possibility that the lithium problem is a hint of physics beyond the standard model. What if, in the seething heat of the early universe, there existed unknown particles that interacted with the nuclear soup? Certain hypothetical particles, like some types of dark matter, could have been present and decayed during those first few minutes. The energy released from such decays could have altered the neutron-to-proton ratio or provided new pathways for destroying the fragile beryllium-7 nuclei, effectively reducing the final yield of lithium. If this is true, then the missing lithium is not an error but a clue, a cosmic fossil pointing toward the existence of new particles that played a role in shaping the infant universe. The lithium discrepancy, therefore, becomes a bridge connecting the world of atomic nuclei to the invisible realm of dark matter, suggesting that the solution to one cosmic puzzle might lie hidden within the secrets of another. Leaving behind the chemical puzzles of the early universe, we now confront a mystery that strikes at Earth from the deepest voids of space, not with a gentle whisper, but with a subatomic punch of almost unimaginable power. We are constantly being bombarded by cosmic rays, streams of high-energy particles, mostly protons, that race across the galaxy. Most of these are relatively low energy, but a tiny fraction of them are in a class of their own. These are the ultra-high-energy cosmic rays, and they carry so much energy that it borders on the absurd. Imagine a single proton, a fundamental particle smaller than an atom, traveling with the kinetic energy of a professionally thrown baseball. That is the scale we are talking about, a particle accelerated to energies of over 100 exa-electron volts, millions of times more powerful than what we can create in our most advanced particle accelerators like the Large Hadron Collider. The existence of these particles presents physics with a monumental challenge, famously known as the GZK cutoff paradox, named for physicists Greisen, Zatsepin, and Kuzmin. They realized that any proton traveling across the vast distances of the universe with such incredible energy should not be able to reach us at all. That's because the cosmos is not empty. It's filled with the faint afterglow of the Big Bang, the cosmic microwave background radiation. For a proton with ultra-high energy, these background photons are no longer harmless whispers. They appear as a relentless wall of high-energy gamma rays. When the proton smashes into one of these photons, the collision is so violent that it creates new particles like pions, which siphon off the proton's energy. Over a distance of about 150 million light-years, this process should sap the energy of any ultra-high-energy cosmic ray down below the extreme levels we detect. The fact that we see them at all means they cannot have come from too far away. They must be relatively local, cosmically speaking, originating from within our own cosmic backyard, a sphere of galaxies centered on the Milky Way. This, however, only deepens the mystery because it leads to the great cosmic ray detective story, the challenge of tracing their origin. Unlike light, which travels in a straight line, cosmic rays are charged particles. As they journey through space, they are whipped and spun by the Milky Way's tangled magnetic fields. It's as if you were trying to find the source of a downpour by studying a single raindrop that had been blown and tossed by a hurricane. By the time one of these particles slams into Earth's atmosphere, its path is completely scrambled. It provides no direct pointer back to its source. We can detect the particle, but we cannot simply look back along its trajectory to see where it came from. This forces astronomers to become forensic scientists, using indirect methods to hunt for the culprits capable of such immense acceleration. So what cosmic engines in our local universe could possibly be responsible? The suspects must be objects of almost unimaginable violence, capable of wielding energies that dwarf supernova. The prime candidate is a class of galaxies known as active galactic nuclei, or AN. At the heart of these galaxies lies a supermassive black hole that is actively feeding on surrounding gas, dust, and stars. As matter spirals into the black hole's gravitational well, it forms an incredibly hot, bright accretion disk, but in some AGN, not all the matter falls in. Powerful magnetic fields can funnel some of the infalling material into colossal jets that shoot out from the poles of the black hole at nearly the speed of light. These jets are nature's ultimate particle accelerators, stretching for thousands of light-years. It is within these relativistic jets that physicists believe protons could be accelerated to the energies we observe, surfing on colossal shockwaves like a surfer on an interstellar tidal wave. Another compelling suspect is the shockwaves from gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. These brief, cataclysmic events, thought to be caused by the collapse of massive stars or the merger of neutron stars, release more energy in a few seconds than our Sun will in its entire 10 billion-year lifetime. The expanding blast wave from such an explosion could easily serve as a particle accelerator on a cosmic scale. Other potential sources include violent processes in galaxy clusters, where the turbulent motion of million-degree gas could generate immense shock waves, or even the giant lobes of radio galaxies, where particles might be reaccelerated over vast distances. The hunt for proof involves a unique form of astronomy that doesn't use traditional telescopes. Instead, scientists use the Earth's own atmosphere as a detector. When an ultra-high-energy cosmic ray hits the atmosphere, it creates a cascade of secondary particles, an expanding shower that can cover dozens of square kilometers on the ground. Massive observatories like the Pierre Auger Observatory in Argentina consist of thousands of water tanks spread over an area the size of Rhode Island, waiting to detect the faint flash of light produced when these secondary particles zip through the water. By measuring the timing and intensity of the shower across this vast array, scientists can reconstruct the energy and, crucially, the rough incoming direction of the original cosmic ray. While the magnetic fields prevent a precise pinpoint, observing multiple events from the same general patch of sky can build a statistical case against a particular source. Indeed, the Auger collaboration has reported a correlation between the arrival directions of the highest energy cosmic rays and the locations of nearby active galactic nuclei, providing tantalizing, though not yet conclusive, evidence that these monstrous black holes are indeed the culprits. Yet, even with these correlations, puzzles remain. Not every ultra-high-energy cosmic ray points back to a known AGN, leaving room for other, perhaps even more exotic sources. Some theorists have proposed the decay of hypothetical super-heavy dark matter particles lurking in the halo of our galaxy. If such particles existed, their decay could produce protons with the requisite energy, and since they would originate within our own galaxy, they would easily avoid the GZK cutoff. This idea elegantly ties one cosmic mystery to another, suggesting that the most energetic particles in the universe might be a signature of its most elusive substance. The enigma of ultra-high-energy cosmic rays is a testament to the universe's capacity for violence on scales we are only beginning to comprehend. A constant, invisible rain of messengers from the most powerful engines in the cosmos, challenging us to decipher their origins. While the grand mysteries of dark energy and cosmic rays challenge our understanding of the universe's fundamental forces, sometimes the most unsettling clues are not about what is missing, but what is strangely, unexpectedly present. This brings us to a finding so peculiar that astronomers gave it a name fit for a cosmic supervillain, the axis of evil. The story begins with our most pristine snapshot of the infant universe, the cosmic microwave background radiation. This is the leftover heat from the Big Bang, a nearly uniform glow that fills the entire sky, a bath of microwaves that has been traveling for 13.8 billion years to reach us. For decades, this radiation has been the bedrock of modern cosmology, and its extreme uniformity, varying by less than 1 part in 10,000, has powerfully supported a foundational idea called the cosmological principle. This principle states that, on the largest scales, the universe is isotropic and homogeneous. In simpler terms, it should look the same in every direction and have no special place or preferred axis. There should be no up or down in the cosmos, but the axis of evil suggests there might be. The first hints of this anomaly emerged from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, in the early 2000s. When scientists meticulously mapped the tiny temperature fluctuations in the cosmic microwave background, the seeds that would one day grow into galaxies and clusters, they expected to find a random, patternless distribution like static on an old television set. Instead, they noticed something bizarre. The fluctuations appeared to be aligned along a particular axis that slices across the sky, a preferred direction that seems to divide the universe into 2 hemispheres. Even more strangely, this axis appears to be curiously aligned with our own solar system. The plane of Earth's orbit around the Sun, known as the ecliptic, and the geometry of our solar system itself seem to have an unlikely correlation with this cosmic structure. It's as if the universe's largest-scale blueprint has a faint arrow pointing back at us, a notion that makes physicists deeply uncomfortable because it threatens the very idea that we do not occupy a privileged position in the cosmos. The plot thickened with the arrival of even more precise data from the European Space Agency's Planck satellite. If the WMAP result was a statistical fluke or an artifact of the instrument, Planck's superior sensitivity should have washed it away. It did not. The Planck mission confirmed the existence of this large-scale asymmetry and other associated anomalies, such as a mysterious cold spot and a curious deficit of fluctuations on the very largest scales. The existence of these patterns is not really in dispute. The data is clear. The heated debate is over what causes them. The most conservative and therefore most desired explanation is that it's all a grand illusion. Perhaps it's a subtle systematic error in how the data is processed. The cosmic microwave background is incredibly faint, and teasing its signal out from the foreground glare of our own Milky Way galaxy is a monumental task. Even the tiniest miscalibration or unaccounted for emission from interstellar dust could potentially imprint a false pattern that looks like a cosmic axis. Researchers have spent years searching for such an error, but so far no smoking gun has been found. If the effect is real, the implications are profound. It could mean that the universe is not isotropic on its very largest scales. Perhaps it has a crystalline-like structure, or it's shaped like a vast cosmic knot, with a preferred direction woven into the fabric of space-time from the very beginning. Some theorists have explored mind-bending ideas, such as the universe being caught in a giant, universe-sized magnetic field that influenced the plasma of the Big Bang, or that our cosmos is not infinite but has a finite, topologically complex shape, like a hall of mirrors where light wraps around and creates apparent patterns. The most radical interpretation is that the axis of evil is evidence of a pre-Big Bang universe, a relic of some asymmetrical process that occurred before the birth of our space and time, leaving a fingerprint on the very first light. Whatever the true explanation, the axis of evil stands as a stubborn anomaly, a crack in the elegant facade of our standard cosmological model. It reminds us that our most cherished principles are always subject to the ruthless scrutiny of data, and that the universe may still hold surprises that force us to rethink everything we thought we knew about its true nature. But perhaps the most precise and elegant tool for measuring the expansion rate comes from looking back to the very beginning, to the cosmic microwave background radiation. The Planck satellite mapped this ancient afterglow with incredible detail, capturing the tiny temperature fluctuations that are the frozen sound waves of the infant universe. The size of these fluctuations acts as a cosmic ruler. By understanding the physics of the primordial plasma, a well-tested mix of particle physics and general relativity scientists can calculate exactly how far these waves could have traveled before the universe became transparent. This gives us a precise measurement of the universe's geometry and its expansion history. From this single, pristine snapshot, we can run the cosmic film forward to predict what the Hubble constant should be today. The result from Planck is unequivocal: 67.4 kilometers per second per megaparsec. This value is exquisitely consistent with our model of the universe, known as the lambda cold dark matter model. But it is in stark and growing disagreement with the local measurements. The difference is now significant to a level of about 5 sigma, meaning there is only a 1 in a million chance that this discrepancy is a random fluke. This isn't a minor accounting error, it is a fundamental tension at the heart of modern cosmology, so we are left with a critical choice. Is there an unknown collective error plaguing all our local distance measurements, or all our early universe measurements? Or is the universe itself telling us that our cherished standard model of cosmology is incomplete? The first option is what many scientists initially hoped for. Perhaps the Cepheid period luminosity relationship has a subtle flaw we haven't accounted for. Maybe there is an unrecognized source of dust in other galaxies that is dimming the supernova. Teams have checked and rechecked the data, looking for these systematic errors. The SH0E's collaboration, for instance, has cross-calibrated multiple distance indicators, building a cosmic distance ladder with extraordinary care, and the tension persists. On the other side, the Planck data has been scrutinized for any possible contamination from foreground sources within our own galaxy, but the anomaly remains robust. With each passing year and each new, more precise measurement, the possibility of a simple mistake grows increasingly unlikely. This leads us to the thrilling possibility that the Hubble tension is a crack in the foundation, a glimpse of new physics beyond our current understanding. The most exciting explanations involve tweaking the ingredients of our cosmic recipe. Our standard model includes ordinary matter, and dark energy. What if dark energy is not constant, as Einstein's cosmological constant assumes? If dark energy's strength increased slightly over the history of the universe, it could have provided an extra push, making the local expansion faster than predicted from the early universe's data. This dynamic dark energy, often called quintessence, could resolve the tension. Another compelling idea involves early dark energy. This proposes that a new form of energy field existed for a brief period in the very early universe before the cosmic microwave background was emitted. This extra component would have altered the physics of the primordial plasma, changing the size of the sound waves imprinted on the CMB. If this were the case, then our interpretation of the Planck data would be off, and the true expansion rate predicted from the early universe would be higher, closer to the local value. Other theories look beyond dark energy to the dark sector itself. Perhaps dark matter has properties we don't understand. Could it interact with itself or with dark energy in a way that subtly changes the expansion history? Or what if there are additional, yet undiscovered, types of neutrinos, often called sterile neutrinos, that flooded the early universe? These extra relativistic particles would have affected the rate at which structures formed, again altering the calibration of our cosmic ruler from the CMB. The Hubble tension, therefore, is more than just a debate over a number. It is a catalyst for innovation, forcing cosmologists to consider models of the universe that are more complex, more dynamic, and ultimately, more interesting than the standard one we have relied on for decades. The resolution of this mystery will likely require a next-generation observatory, like the Nancy Grace Roman Space Telescope or the Vera C. Rubin Observatory, which will measure the expansion rate with even greater precision. The Hubble tension is a testament to the fact that science progresses not when all the pieces fit neatly together, but when a stubborn, inconvenient piece refuses to fit, compelling us to see the entire puzzle in a brilliant new light. Deep within the faint, uniform glow of the cosmic microwave background, that primordial echo of the Big Bang, lies a feature so peculiar it has been called the universe's first cold case. This is the CMB cold spot, a vast and chilling anomaly that has sparked debate stretching from the structure of our own cosmos to the radical possibility of a reality beyond it. Discovered in 2004 by NASA's a Wilkinson microwave anisotropy probe, and later confirmed with stunning clarity by the Planck satellite, the cold spot isn't just a slightly cooler patch. It is a colossal region of space about 0.1 degrees across in the sky, which translates to a diameter of nearly 2 billion light-years. Within this enormous area, the temperature of the microwave background is about 70 microkelvins colder than the surrounding average. While that might sound like a trivial difference, the statistical probability of such a large and cold region appearing randomly in the otherwise smooth CMB is incredibly low, less than 2%. It is an outlier, a cosmic bruise that demands an explanation. One of the leading and most straightforward theories proposed to explain this chill is the concept of a supervoid. Imagine space not as a uniform container, but as having a texture, with dense clusters of galaxies and vast, empty deserts in between. A supervoid is the ultimate cosmic desert, and region of space with a drastically lower density of galaxies and matter than average. According to a phenomenon in cosmology called the integrated Sachs-Wolf effect, light traveling through such an underdense region behaves in a specific way. As a photon from the cosmic microwave background enters a void, it must climb out of the gravitational well created by the lack of mass. In a universe whose expansion is accelerating due to dark energy, this well actually becomes shallower while the photon is traveling through it. The photon gains a tiny amount of energy climbing out of a potential that is less deep than when it entered, but because it gained energy, it appears to have a lower frequency. It appears cooler to our detectors. A sufficiently large supervoid between us and the cold spot could, in theory, produce the observed temperature dip. The hunt for this hypothetical supervoid began in earnest. Astronomers pointed telescopes at the cold spot, conducting deep galaxy surveys to map the distribution of matter in that direction. The results have been ambiguous, adding another layer of intrigue. Some surveys did find evidence of a large underdense region, but it appears to be far too small and not empty enough to account for the entire temperature anomaly. The void that was found might explain a part of the cold signal, but not all of it. This discrepancy has led some researchers to question whether the supervoid explanation is sufficient, opening the door for far more exotic possibilities. It's as if a detective found a small puddle at the scene of a flood. It's related to the water, but it doesn't explain the deluge. This failure of a simple explanation is what gives weight to one of the most mind-bending hypotheses ever proposed, that the CMB cold spot is evidence of a collision with another universe. This idea springs from the theory of eternal inflation and the multiverse. In this model, our universe is just one bubble in a vast, ever-expanding cosmic foam, where new universes are constantly budding off. Sometimes these budding universes might not fully separate. They could collide with our own cosmic bubble. The physics of such a collision would be unimaginably violent, an event occurring in the higher dimensional bulk space outside our familiar 4 dimensions. The energy released by such an impact would, according to theoretical models, leave a distinct imprint on the surface of our universe, a circular pattern of temperature variation in the cosmic microwave background. The cold spot, with its specific size and temperature profile, matches the predicted signature of such a cosmic crash. In this scenario, the chill we detect is not from a void within our universe, but the lingering scar from a traumatic encounter with a separate reality at the dawn of time. Naturally, such a radical claim is met with intense skepticism, as it should be. The scientific method demands that extraordinary claims be backed by extraordinary evidence, and the collision hypothesis is about as extraordinary as it gets. Critics point out that the statistical significance of the cold spot, while low, is not impossible. In a universe as vast as ours, unlikely things can and do happen by pure chance. This could simply be the 1 in 50 fluctuation that we happen to observe. Furthermore, the search for the supervoid is not over. More sensitive surveys may yet discover a larger, emptier void that can fully account for the temperature drop without needing to invoke parallel universes. The challenge for the collision theory is that it is currently untestable in a conventional sense. We cannot rerun the universe to see if the collision happens again, nor can we peer beyond the boundaries of our cosmos to look for the culprit. Its power lies in its ability to explain an observation that more conventional models struggle with, making it a tantalizing, if speculative, avenue of research. The enduring mystery of the CMB cold spot perfectly encapsulates the frontier of modern cosmology. It sits at the crossroads of careful observation and daring theoretical speculation. On one hand, it pushes us to better understand the large-scale structure of our own universe, to map the cosmic web of galaxies and voids with ever greater precision. On the other, it beckons us to consider possibilities that redefine the very nature of reality. Whether it is ultimately explained by a vast nothingness or a shattering collision with another cosmos, the cold spot serves as a powerful reminder that the oldest light we can see still holds profound secrets, challenging us to decipher its faint, cold whisper from the beginning of everything. But this journey into the invisible architecture of the cosmos now brings us to a mystery that strikes at the very laws governing reality itself, a paradox born from the marriage of 2 of our most successful but incompatible theories. This is the black hole information paradox, and it begins with one of Stephen Hawking's most astonishing discoveries, that black holes are not entirely black. We are accustomed to thinking of them as the ultimate cosmic vacuums, from which nothing, not even light, can escape. But Hawking applied the strange rules of quantum mechanics to the edge of a black hole, the event horizon, and realized that even this point of no return is not immune to quantum uncertainty. The vacuum of space, according to quantum theory, is not truly empty. It is a seething foam of virtual particles, pairs of particles and antiparticles that constantly pop into existence out of nothing, borrowing energy from the universe for an infinitesimally brief moment before they collide and annihilate each other, paying back the energy loan. Normally, this process is perfectly balanced and invisible, but Hawking imagined this happening right at the event horizon. What if, he asked, one of these virtual particles falls across the horizon while its partner escapes into space? The particle that falls in has negative energy, and in a wonderfully subtle piece of physics, this causes the black hole to lose a tiny amount of mass. The particle that escapes, however, becomes real, carrying away a small amount of the black hole's energy. This stream of escaping particles is what we call Hawking radiation. Over unimaginable eons, this process causes the black hole to slowly evaporate, shrinking until it eventually vanishes in a final burst of energy. The staggering implication is that black holes have a temperature and a finite lifespan. They are not eternal prisons. This brilliant insight, however, created a catastrophic problem. The Hawking radiation that leaks out is purely thermal. Its properties depend only on the black hole's mass, charge, and spin. It is random and featureless, like the heat radiating from a bonfire. It contains no information whatsoever about the specific things that fell in to create the black hole in the first place. Was it a star made mostly of hydrogen? Was it a spaceship built of iron, silicon, and carbon? Was it an encyclopedia containing the complete works of Shakespeare? According to Hawking's original calculation, all of these distinct objects would produce identical black holes of the same mass, and those black holes would then emit identical Hawking radiation. When the black hole finally evaporates, all the detailed information about what fell into it seems to be irretrievably lost, and this violates a fundamental tenet of quantum mechanics, the principle of unitarity. This principle states that information is never destroyed. The universe, according to quantum law, is like a perfect cosmic librarian. It never loses a book, it only changes the way the information in that book is stored. The state of a system at one time should, in principle, allow you to calculate its state at any other time, forward or backward. If you could rewind the universe, you should see the burned ashes of the encyclopedia reassemble into the original book. The information paradox suggests that black holes are cosmic arsonists, burning the books of reality beyond any possible recovery. This sets up a direct conflict between the two pillars of modern physics. General relativity, which describes gravity and the large-scale structure of the universe, seems perfectly content with information being lost down a black hole. Einstein's theory is deterministic but not reversible in the quantum sense. It doesn't care about preserving information. Quantum mechanics, which describes the world of the very small, insists that information must be preserved. Both theories cannot be correct in this instance. One of them must break down when pushed to the extreme environment of a black hole's evaporation. For decades, this was the stalemate, with most physicists siding with quantum mechanics and believing that Hawking must have missed something. The prevailing belief became known as the black hole conservation of information dogma. The information is not lost, it must somehow be encoded in the Hawking radiation, even if we cannot see how. This is where the plot thickens dramatically, leading to a fascinating potential resolution that radically changes our picture of a black hole. The key might lie not in the radiation itself, but on the surface where the drama unfolds, the event horizon. Imagine the event horizon not as a sharp, one-way door, but as a layer of incredible complexity. When an object falls into a black hole, according to this new way of thinking, it doesn't simply vanish. Instead, its information is scrambled and smeared across the event horizon, a process often compared to a hologram. A hologram is a two-dimensional surface that encodes all the information needed to project a three-dimensional image. Similarly, the idea is that all the information about the three-dimensional volume of the black hole is actually encoded on its two-dimensional boundary. This is the famous holographic principle, and it suggests that the universe might fundamentally operate like a cosmic hologram. If this is true, then as the black hole evaporates via Hawking radiation, this scrambled information on the horizon is slowly and chaotically released back into the universe, imprinted onto the radiation itself. The problem is that this encoding is so complex and chaotic that it appears completely random to any observer. It would be like trying to reconstruct a Shakespearean sonnet from the ashes of a burned book by studying the precise pattern of the smoke particles. The information is theoretically there, but it is hopelessly scrambled and inaccessible in practice. This leads to another bizarre puzzle. If information is preserved but irretrievably scrambled, does that truly satisfy the demands of quantum mechanics? The debate continues to rage, with some physicists proposing even more radical solutions, such as firewalls, a blistering wall of energy at the event horizon that would incinerate anything falling in, preserving information but violating the core principle of general relativity that an astronaut crossing the horizon should notice nothing special. The resolution of the black hole information paradox is about more than just the fate of stars and encyclopedias. It is a crucial stepping stone to a deeper theory of quantum gravity, a framework that would successfully unite general relativity with quantum mechanics. Understanding how space, time, and information behave under the most extreme conditions is the key to unlocking the secrets of the universe's very first moments, and perhaps its ultimate fate. The paradox forces us to confront the nature of reality itself. Is the universe a system that forever remembers every detail of its history, or are there truly places, like the heart of a vanishing black hole, where the past is erased forever? The answer, when we find it, will undoubtedly rewrite our understanding of the cosmos. While Hawking radiation presents a profound paradox at the boundary of a black hole, the true heart of the mystery lies even deeper, at the very center where our understanding of physics reaches its ultimate breaking point. We are drawn inward past the event horizon, beyond the point of no return, to confront the most baffling prediction of general relativity, the gravitational singularity. This is the final destination for anything that falls into a black hole, a place where the very concepts of space and time as we know them cease to have any meaning. According to Einstein's theory, the immense gravitational pull of a black hole is unstoppable. It crushes all the infalling matter, a star, a planet, a spaceship, into a single point of infinite density. At this singularity, the curvature of space-time becomes infinite, and the laws of physics simply give up. The equations of general relativity, which so elegantly describe the orbits of planets and the bending of light, return a result that is physically nonsensical. An infinity in nature is a sign that our theory is incomplete, that we have pushed it beyond its limits and into a domain where a new, deeper theory must take over. The problem is one of extremes. General relativity is a masterpiece of classical physics, brilliantly describing the universe on the largest scales, where gravity is the dominant force. But it completely ignores the quantum world, the bizarre and probabilistic rules that govern the behavior of atoms and subatomic particles. At the unimaginable densities and energies present in a singularity, quantum effects must become paramount. It's like using the rules of fluid dynamics to describe a single molecule of water. The model simply isn't equipped for the task. The singularity is therefore a scream from the universe, a glaring signal that we need a theory of quantum gravity. a framework that can seamlessly blend the cosmic rulebook of Einstein with the subatomic rulebook of quantum mechanics. Without it, the center of a black hole remains a permanent blind spot in our map of reality. This quest for a unified theory is one of the great adventures of modern physics, and it has led to several fascinating candidates, each offering a different way to resolve the problem of the singularity. String theory, for instance, proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. At the incredibly small scales of the Planck length, these strings would smooth out the sharp, point-like singularity, replacing it with a fuzzball, a tangled, vibrating knot of strings that has a finite size and a complex structure. In this view, there is no infinite density because the matter is smeared out across this fuzzball, preventing the catastrophic collapse predicted by classical relativity. It's an elegant solution, but one that is, for now, exceedingly difficult to test experimentally. Another compelling approach is loop quantum gravity, which takes a more direct geometric view of space-time itself. This theory suggests that space is not a smooth, continuous fabric, but is instead woven from tiny, discrete loops, a kind of atomic structure of space itself. Just as a material like cloth appears smooth from a distance but is revealed to be a network of threads up close, space-time has a fundamental granularity. When matter collapses under its own gravity in loop quantum gravity, it reaches a point where this granular nature of space pushes back. Instead of collapsing to a point of infinite density, the matter experiences a quantum bounce. The immense gravitational squeeze is counteracted by a powerful repulsive force generated by the quantum geometry of space, potentially causing the black hole to transform into a white hole, spewing the captured matter back out into the universe. This idea turns the black hole inside out, suggesting that a singularity might not be an ultimate end, but a gateway to a new beginning. The challenge, of course, is that we cannot peer inside a black hole to see which, if any, of these theories is correct. The event horizon shrouds the interior in absolute secrecy. However, physicists are not without tools. By studying the properties of black holes from the outside, their mass, spin, and the way they vibrate when they merge, creating gravitational waves, we can look for indirect fingerprints of what's happening within. The detailed pattern of gravitational waves rippling out from a collision could, in principle, contain subtle clues about the nature of the object's interior, potentially revealing whether it holds a true singularity or some quantum gravitational structure. The mystery of the singularity is therefore not just a theoretical curiosity. It is a driving force behind our attempts to listen to the universe in a whole new way, using the fabric of space-time itself as a medium to uncover its deepest secrets. Yet if the crushing finality of a black hole's singularity represents one end of the gravitational spectrum, then the equations of general relativity hold out a tantalizing possibility for an opposite extreme. We now venture into the domain of pure theoretical physics, to concepts that sound like they're lifted from the pages of science fiction, but are, in fact, legitimate mathematical solutions to Einstein's field equations. These are the cosmic escape artists, white holes and wormholes. Imagine a black hole in reverse. Instead of an object from which nothing can escape, a white hole would be a region of space-time from which nothing can enter. It would be a cosmic fountain perpetually spewing out matter and energy into the universe, but completely impervious to any influence from the outside. If you were to try and fly your spaceship into a white hole, it would be like trying to swim up the outflow of a waterfall of unimaginable power. You would be violently repelled. Mathematically, a white hole is simply the time reversal of a black hole. If we were to take the film of a star collapsing into a black hole and run it backward, we would see a white hole, a burst of light and matter exploding into existence from a singular point. The mathematics is perfectly symmetric, but the physics of our universe seems to have a profound preference for one direction of time, the one where entropy increases and things become more disordered. While black holes are a natural consequence of gravitational collapse, a white hole would require a miraculous decrease in entropy, a spontaneous organization of energy that violates the second law of thermodynamics. For this reason, most physicists consider white holes to be mathematically possible but physically improbable. They are the unbirths of the cosmos, fascinating ghosts in the machine of general relativity. But what if we could somehow connect the two? This leads us to one of the most captivating ideas in all of theoretical physics, the wormhole. Also known as an Einstein-Rosen bridge, a wormhole is theorized to be a shortcut, a tunnel through the fabric of space-time that connects two distant points. Imagine space-time as a vast two-dimensional sheet of paper. If you wanted to get from a point on the left side to a point on the right, the normal route would be to travel the long way across the surface. But if you could fold the paper so the 2 points touched, and then punch a hole through the contact point, you would have created a wormhole, a bridge that reduces a journey of millions of light years to a simple step. The concept was first explored in detail by Albert Einstein and Nathan Rosen in 1935, as they sought to model particles as tiny tunnels in space-time. A simple, non-traversable wormhole can be thought of as connecting a black hole to a white hole. Something falls into the black hole and, in theory, could emerge from the white hole, potentially in another time or another universe entirely. It's a breathtaking idea, offering the potential for instantaneous travel across cosmic distances and, even more fantastically, travel through time. However, the dream of a stable, traversable wormhole, one you could actually send a ship through, runs into several universe-sized obstacles. The first and most formidable problem is stability. The kind of wormhole that emerges naturally from Einstein's equations is often referred to as a Schwarzschild wormhole. It is incredibly unstable. The throat of the tunnel would pinch shut faster than the speed of light, effectively closing the doorway before any information or matter could possibly get through. It would be like a drawbridge that retracts the instant someone sets foot on it. To keep a wormhole open long enough for anything to traverse it, you would need a substance with very peculiar properties to act as a scaffolding, propping the throat open against the relentless force of gravity. This hypothetical substance is known as exotic matter. Exotic matter isn't just rare or unknown. It is defined by having a negative energy density or negative pressure. According to general relativity, gravity is the curvature of space-time caused by mass and energy. Normal matter and energy, which have positive density, always curve space-time in a way that attracts, creating the gravitational pull we're familiar with. Exotic matter with negative energy density would produce a gravitational repulsion. It would push space-time apart, acting as a kind of anti-gravity that could counteract the natural tendency of a wormhole to collapse. The question is, does such matter exist? There are hints in the strange world of quantum mechanics. The Casimir effect, for instance, demonstrates that in a vacuum between two closely spaced metal plates, the energy density can be lower than the surrounding space, effectively creating a negative pressure region. While this is a real quantum phenomenon, the amounts of negative energy involved are infinitesimally small. To stabilize a wormhole large enough for a person, let alone a spaceship, you would need astronomical quantities of this exotic material, assembled and controlled with technology far beyond our current comprehension. Beyond the staggering engineering challenge, wormholes introduce profound paradoxes, most famously the potential for violating causality, the principle that cause must always precede effect. If you could use a wormhole to travel between 2 points in space faster than light could travel the normal route, and if one end of the wormhole was then moved relative to the other, special relativity tells us that the two ends could become misaligned in time. This could create a scenario where the exit of the wormhole exists in the past relative to the entrance. You could then potentially travel back in time and, in a classic paradox, prevent your own grandparents from meeting. Physicists are divided on whether the laws of physics would inherently prevent such a scenario, perhaps through some yet unknown mechanism, or if time travel to the past is simply impossible, placing a fundamental constraint on the existence of traversable wormholes. The study of white holes and wormholes, while currently confined to the blackboards of theorists, is far from a mere intellectual exercise. It pushes our understanding of gravity, quantum mechanics, and the very nature of reality to its absolute limits. These cosmic shortcuts represent a frontier where the line between established science and speculative dream blurs, reminding us that the universe described by mathematics may be far stranger and more interconnected than we have yet dared to imagine. Having charted the bizarre orbits of objects at the edge of our solar system, we now set our sights on a force operating on a scale so vast it defies easy comprehension, a gravitational pull so immense that it is dragging our entire galaxy and countless others on a mysterious journey through the cosmos. We are being pulled toward a specific point in the void, a destination we cannot see, by a phenomenon astronomers call the Great Attractor. For centuries, we viewed our Milky Way as the center of our celestial neighborhood, with nearby galaxies like Andromeda as our primary companions. But in the 1970s, as we began to map the large-scale motions of galaxies with greater precision, a disturbing pattern emerged. It wasn't just that the universe was expanding, it was that our local cluster of galaxies, including the Milky Way, was drifting in a specific direction against that universal flow, like a leaf caught in a cosmic river current. This peculiar motion, known as the dipole anisotropy, indicated that something massive was tugging on us from the depths of intergalactic space. The sheer power required to influence the motion of thousands of galaxies is staggering. Calculations suggest the Great Attractor has a mass equivalent to tens of thousands of Milky Way galaxies, concentrated in a region of space about 300 million light-years across. This isn't a gentle nudge, it's a gravitational summons from a colossal concentration of mass. Our galaxy, along with the entire local group, is racing toward this point at a velocity of over 600 kilometers per second. But here lies the central mystery. When astronomers point their telescopes toward the direction of this pull, located in the constellation Centaurus, they are met with a significant obstacle. The center of our own galaxy, with its dense clouds of stars, gas, and dust, lies directly in the line of sight. This region is known as the zone of avoidance because the thick band of the Milky Way's disk blocks our view of the universe beyond, like trying to see a distant mountain range through a dense, blinding fog. This cosmic blind spot has made direct observation of the Great Attractor incredibly challenging. For decades, it remained a ghost, its presence inferred only by its gravitational influence on everything around it. The first major breakthrough came from mapping the universe in a spectrum of light that can pierce through the galactic dust, radio waves. Using radio telescopes, astronomers were able to peer through the zone of avoidance and discovered that the Great Attractor is not a lone, monolithic object, but rather the heart of a much larger structure, a supercluster of galaxies now known as the Laniakea supercluster. Laniakea, a Hawaiian word meaning immeasurable heaven, is the cosmic continent to which our Milky Way belongs. It is a vast filamentary web of hundreds of thousands of galaxies, all flowing toward a gravitational center of mass, the Great Attractor. So what is this gravitational epicenter? The most likely candidate is a massive cluster of galaxies known as the Norma cluster, which sits right at the core of the Great Attractor region. The Norma cluster is an immensely dense knot of galaxies containing a huge amount of visible mass in the form of stars, gas, and dust. However, there's a problem. Even when we add up all the visible matter in the Norma cluster and the surrounding Laniakea supercluster, it still doesn't account for the full gravitational strength needed to explain our observed motion. This suggests that the true nature of the Great Attractor is a combination of two profound cosmic mysteries. First, there is the immense concentration of visible galaxies in the Norma cluster. But second, and perhaps more importantly, there is a titanic amount of dark matter associated with this region. The Great Attractor, therefore, appears to be the gravitational focal point of one of the largest known dark matter halos in the universe, a place where the invisible scaffolding of the cosmos has gathered on a truly monumental scale. But the story doesn't end there. In fact, the plot has recently thickened with the discovery of an even larger and more distant gravitational influence. Beyond the Great Attractor, at a distance of over 600 million light-years, lies a structure of almost unimaginable size called the Shapley Attractor. This is the largest known concentration of mass in our observable universe, a supercluster containing dozens of massive galaxy clusters. It appears that the Great Attractor itself, and our entire Laniakea supercluster, is being pulled toward this even more massive gravitational sink. We are caught in a cosmic hierarchy of flows. Our local group is falling toward the Virgo cluster, which is part of the larger flow toward the Great Attractor, which is in turn part of the immense drift toward the Shapley Attractor. This reveals a universe not of random expansion, but of intricate gravitational currents, where galaxies move like water droplets in a vast cosmic watershed, drawn toward the deepest gravitational wells. The ongoing investigation into the Great Attractor showcases a fundamental shift in how we understand our place in the cosmos. We are not stationary observers in an evenly expanding universe. We are participants in a dynamic, flowing system of matter and energy on the grandest scales. New observatories and sky surveys, like those conducted by the Parkes Radio Telescope and future missions, continue to map the hidden galaxies behind the zone of avoidance, slowly revealing the full structure of this mysterious region. The Great Attractor is no longer just a hypothetical anomaly. It is a defined location, a gravitational landmark in the immense geography of the universe. Yet, its true power continues to remind us that most of the universe's mass remains unseen, its invisible hand guiding the motion of the stars and galaxies we can see, forever pulling us toward a destination we are only just beginning to map. But if the Great Attractor represents an immense concentration of mass, a gravitational sink pulling entire superclusters toward it, then our next mystery presents the precise opposite, a staggering, almost terrifying emptiness. Imagine a sphere of space so vast it could contain thousands of galaxies like our Milky Way, and yet when you peer inside, you find it to be profoundly, unnervingly dark. This is the Boötes Void, one of the largest known caverns in the observable universe, a cosmic desert on a scale that challenges our understanding of how the cosmos organizes itself. Discovered in the 1980s by astronomer Robert Kirshner and his colleagues, the void is named for the constellation Boötes, the herdsman, where it lies about 700 million light-years from Earth. Its dimensions are almost incomprehensible. With a diameter of roughly 330 million light-years, if you were to place our Milky Way galaxy at the center of this void, the nearest edge of empty space would be over 160 million light-years away in every direction. In a universe we often picture as a crowded web of galaxies, the Boötes Void is a bubble of near-nothingness. The existence of such a void wasn't entirely unexpected. The prevailing model of the universe's large-scale structure is known as the cosmic web. In this picture, dark matter acts as an invisible scaffolding. Gravity pulls this dark matter into vast, interconnected filaments, and at the intersections of these filaments, galaxies and galaxy clusters form, creating brilliant nodes of light. Between these filaments are the voids, the empty spaces where matter is scarce. We see this pattern everywhere we look. The universe has a frothy, bubble-like structure. But the Boötes Void is an extreme outlier. While typical voids might be 50 to 100 million light-years across, the Boötes Void is 3 to 6 times larger. It's not just a gap in the cosmic web. It's a chasm so enormous that it seems to defy the statistical predictions of how matter should have clustered after the Big Bang. Based on our standard models, a void of this size should be exceedingly rare, perhaps even impossible. So what could have created such an immense emptiness? Astronomers have proposed several theories, ranging from the straightforward to the wildly speculative. The most conservative explanation is that the Boötes void is exactly what it appears to be, a statistical fluke. In an infinite or near-infinite universe, even the most unlikely events must occur somewhere. Perhaps we are simply living in a part of the cosmos that, by pure chance, contains an exceptionally large bubble. This is sometimes called the theorist's last resort, attributing an anomaly to random chance. While this is possible, the sheer scale of the void makes many scientists uncomfortable with this answer, prompting a search for a more dynamic origin story. A more compelling theory involves the merging of smaller voids. Imagine the cosmic web as a structure made of soap bubbles. Over billions of years, the walls between adjacent, smaller voids could have thinned and eventually ruptured, allowing the bubbles to coalesce into one giant supervoid. This process would have been driven by the expansion of the universe and the gravitational dynamics of the surrounding filaments. As smaller voids merged, the galaxies that were once isolated in the walls between them would have been swept toward the denser filaments on the outskirts, evacuating the central region and leaving behind the colossal empty space we see today. This idea is plausible and fits within our understanding of cosmic evolution, but it requires a specific and somewhat rare series of events to create a void as large as the one in Boötes. Then there are the more exotic possibilities. Could the Boötes void be evidence of an ancient, universe-shaking event? Some have suggested, albeit controversially, that it could be the imprint of a collision with a parallel universe in the multiverse scenario. The idea is that the interaction between our universe and another could have literally pushed matter out of a vast region of space, leaving behind a void. While this is a fascinating concept that captures the imagination, it currently resides firmly in the realm of speculation, as there is no direct observational evidence to support it. It serves more as a reminder of how profound cosmic mysteries can push us to consider the limits of known physics. The true scientific value of the Boötes void lies not in proving far-out theories, but in what it reveals about the limits of our current models. Its existence forces us to ask critical questions about the initial conditions of the universe. The patterns we see in the cosmic microwave background, the seeds of all structure, are very smooth. The models that use these seeds to grow the cosmic web we see today have a difficult time producing voids as large as Boötes without tweaking the parameters. Studying this void is like taking a core sample of the cosmos. Its size and emptiness provide a unique constraint on how gravity and dark energy have shaped the universe over billions of years. It is a laboratory for testing the very rules of cosmic architecture, and contrary to its name as a void, the Boötes void is not completely empty. Painstaking surveys have managed to locate a few dozen galaxies within its immense volume, where a typical region of space that size would be expected to contain thousands. These lonely galaxies, sometimes called void galaxies, are themselves fascinating objects. Isolated from the crowded environments of clusters, they evolve in unusual ways, often forming stars at a different pace than their counterparts in denser regions. They are the hermits of the cosmos, living in profound solitude, and studying them helps us understand how a galaxy's environment dictates its life story. The Boötes void, therefore, is more than just an absence. It is an active participant in the cosmic narrative, a dominant feature that influences the evolution of the few galaxies that call it home, and a permanent reminder that the universe reserves its greatest surprises not only in what is present, but in what is astonishingly, profoundly missing. After exploring the vast cosmic voids and the immense gravitational currents that shape our universe, we now turn to a discovery that strikes at the very foundation of our understanding of how galaxies are built. For decades, the existence of dark matter has been the cornerstone of cosmology. the essential, invisible glue that holds galaxies together and explains their very existence. But what if we found a galaxy that played by a completely different set of rules? This brings us to the profoundly puzzling case of a galaxy that seems to defy the universe's most fundamental recipe, a galaxy apparently without dark matter. The story begins with a faint, ghostly galaxy known as NGC 1052 DF2, or DF2 for short, discovered by a team led by astronomer Pieter van Dokkum. DF2 is a unique type of galaxy called an ultra-diffuse galaxy. It's about the same size as our Milky Way but contains only about 1% of the stars, making it incredibly sparse and transparent like a cosmic wisp. When Van Dokkum's team used the Hubble Space Telescope and the Keck Observatory to study this celestial ghost, they focused on 10 bright star clusters within it called globular clusters. By measuring the speeds at which these clusters were orbiting the galaxy's center, they could calculate the galaxy's total mass. The faster the clusters move, the more mass, both visible and dark, must be present to provide the gravitational pull keeping them from flying away. To their astonishment, the clusters were moving surprisingly slowly. The calculated mass based on their motion was almost exactly equal to the mass of all the visible stars and gas in the galaxy. There was simply no room left for dark matter. This was a finding that turned established theory on its head. If dark matter is the essential scaffold upon which all galaxies form, then a galaxy without it is like a building standing without a foundation. It simply shouldn't be possible. The implications of this discovery were seismic. For the standard model of galaxy formation, dark matter is the protagonist. The narrative goes like this. After the Big Bang, dark matter, with its gravitational pull, collapsed first into vast halos. These halos then acted as gravitational traps, pulling in normal gas, which eventually cooled and condensed to form the first stars and the galaxies we see. In this story, every galaxy should be embedded within a massive halo of dark matter. It is the primary component, the unseen engine of creation. Finding a galaxy like DF2, which appears to have formed with little to no dark matter, is akin to finding a car that runs without an engine. It challenges the very sequence of events we believe is responsible for building the cosmos. It suggests that there might be other, unknown pathways for galaxy formation, processes that can create stellar islands without the gravitational help of the universe's dominant form of matter. Naturally, a claim this extraordinary sparked intense debate and scrutiny, with the controversy centering on one critical piece of data: the galaxy's distance from us. The entire calculation of mass rests on knowing exactly how far away DF2 is. Think of it like judging the speed of a car. If a car is far away, it might appear to be moving slowly, when in fact it is nearby and moving very fast. In the case of DF2, if the galaxy is actually much closer to us than initially measured, then the motions of its star clusters would correspond to much slower real velocities, requiring less total mass and making the dark matter deficiency less extreme or even non-existent. Van Dokkum's team initially placed DF2 at a distance of about 65 million light-years, which supported the no dark matter conclusion. However, a separate team of astronomers, using a different method involving the brightness of red giant stars, a well-established cosmic distance marker, argued that the galaxy is significantly closer at around 42 million light-years. At this shorter distance, the galaxy's dynamics would be perfectly normal, requiring a hefty dark matter halo to explain the observed motions. The debate over these few million light-years is not a minor technicality. It is the difference between a galaxy that shatters a paradigm and one that simply conforms to it. The controversy deepened with the discovery of a second candidate, NGC 1052 DF4, which also showed signs of a dark matter deficit. This suggested that DF2 might not be a lone fluke but part of a new class of galaxies. Proponents of the original finding argue that the existence of such galaxies, far from destroying the dark matter theory, actually provides it with powerful, indirect support. Their reasoning is clever. If we can observe phenomena that can be explained by the absence of dark matter, it strengthens the case for its existence everywhere else. It demonstrates that dark matter is a distinct, separable component from normal matter. In most galaxies, the two are entangled, but if a galaxy can somehow lose its dark matter, it proves that dark matter is a real, physical substance that can be stripped away, not just a misunderstanding of the laws of gravity. How could a galaxy lose its dark matter? One provocative theory involves a violent galactic encounter. Perhaps DF2 was once a satellite of a larger galaxy. As it orbited, the immense tidal forces could have ripped away its diffused dark matter halo, which, being more spread out, is more easily stripped, while leaving the more concentrated central stars relatively intact. The resolution of this mystery lies in the painstaking work of obtaining ever more precise measurements. New observations from the Hubble Space Telescope have recently provided a more accurate distance to DF2, using the subtle flickering of old red giant stars. This latest data strongly supports the original farther distance of 65 million light-years, bolstering the case for its missing dark matter. Yet, the scientific process continues, with each new data point refining our understanding. The quest to understand galaxies like DF2 is driving a new era of detailed galactic archaeology, where we study the motions of individual star clusters to weigh the invisible components of the universe. Whether these galaxies are ultimately confirmed as dark matter-free anomalies or explained away by measurement uncertainties, their very discovery has forced a crucial and healthy re-examination of our most fundamental assumptions. They stand as a testament to the fact that the universe always has surprises in store, reminding us that our cosmic models are living frameworks, constantly being tested and refined by the stubborn, enigmatic light from the depths of space. From the ghostly galaxies that seem to defy the dark matter paradigm, we now turn our gaze to a celestial wonder of such stunning symmetry it almost looks engineered. Nestled within the constellation of Serpens, 600 million light-years away, lies a galaxy that could have been drawn with a cosmic compass. This is Hoag's object, a rare and breathtaking example of a ring galaxy. At its heart is a compact, brilliant core of old yellow stars, glowing with the warm light of a stellar retirement community. Surrounding this core is a perfect, luminous circle of young, hot blue stars, shining with the energetic blue of stellar nurseries. And between them lies a gap, a dark, seemingly empty band of space that cleanly separates the two populations. It's a structure so precise and balanced that when astronomer Art Hoag discovered it in 1950, he initially wondered if he was seeing a peculiar planetary nebula or even some kind of gravitational lensing effect. But Hoag's object is a full-fledged galaxy, and its existence presents a beautiful puzzle. How does nature create something that looks so perfectly designed? The most intuitive and widely accepted explanation for this cosmic bull's-eye involves a dramatic and violent galactic collision, a process known as a resonance ring. Imagine a small, dense companion galaxy, what astronomers call a dwarf galaxy, plunging directly through the center of a larger, disc-shaped spiral galaxy, much like our own Milky Way. If this intruder passes straight through the heart of the target galaxy, its gravitational influence would send a powerful density wave rippling outward through the galactic disk. This wave acts like a cosmic shockwave, compressing the gas and dust that resides between the stars. Just as a shockwave traveling through Earth's atmosphere can compress air into a thunderclap, this galactic density wave triggers a burst of star formation in its wake. The wave propagates outward, leaving behind a brilliant circle of newborn blue stars. The central regions of the galaxy, having been violently disturbed but not completely disrupted, would settle back into a tight, spherical core of older stars. The intruder galaxy, having delivered its disruptive blow, would continue on its way, leaving behind this perfect ring as the only evidence of its ancient trespass. This scenario elegantly explains the clear distinction between the old core and the young ring. However, the collision hypothesis, while compelling, faces a significant challenge. Where is the intruder? Searches around Hoag's object have failed to find a clear culprit, a smaller galaxy that could be identified as the one that caused the disruption. This has led astronomers to consider an alternative, more internal mechanism. Perhaps the ring is the result of a phenomenon known as a Lindblad resonance, a process driven by the galaxy's own gravitational field. In a rotating galactic disk, certain orbital paths can resonate with the overall motion, much like how pushing a child on a swing at the right rhythm makes them go higher. A central bar of stars, a common feature in spiral galaxies, can create such resonances. As the bar rotates, it can shepherd gas and dust into specific circular orbits, effectively creating a ring where star formation is concentrated. Over time, the central bar itself could theoretically dissolve, leaving behind the ring and core we see today. This internal instability model avoids the need for an external impactor, suggesting the galaxy could have crafted its own beautiful structure from within. Yet, even among ring galaxies, Hoag's object is an extreme outlier. It is remarkably symmetrical, with a near-perfect circular ring and a core that sits almost exactly at the center. This level of perfection is rare. Other known ring galaxies, like the famous Cartwheel Galaxy, often show more obvious signs of a recent collision, with spokes, distortions, or a clearly visible companion galaxy. The pristine quality of Hoag's object suggests that if a collision did occur, it must have happened billions of years ago, giving the galaxy ample time to settle into its current serene equilibrium. This timescale makes the search for the responsible companion even more difficult, as it would have long since moved far away, blending into the background of thousands of other galaxies in the same region of space. The true rarity of objects like this underscores the specific conditions required for their formation. A galactic collision must be a very precise, bullseye impact to create such a symmetrical ring, rather than simply tearing the galaxy apart or creating a messy, irregular structure. This makes Hoag's object a precious cosmic laboratory. By studying its dynamics and the composition of its stars, astronomers can learn more about the violent interactions that shape galactic evolution and the delicate processes that govern star formation on a colossal scale. Its serene beauty is a frozen moment in a cosmic history filled with chaos, a testament to the fact that from immense violence can sometimes emerge a structure of breathtaking order and grace. While the ghostly galaxy DF2 challenged the idea that dark matter is essential for all galaxies, our next mystery presents a different kind of cosmic fossil, one that seems to have been frozen in time just after its own creation. This is the story of NGC 1277, a galaxy that has earned the dramatic nickname the Cannibal Galaxy, not for what it has consumed, but for what it appears to have refused. Located about 220 million light-years away in the constellation Perseus, NGC 1277 is a compact, massive galaxy that should, by all accounts, be a mature giant similar to our own Milky Way. Instead, it is a relic, a living snapshot of the universe as it was over 10 billion years ago, and its stubborn refusal to evolve challenges our timeline for how massive galaxies are built. To understand why NGC 1277 is so peculiar, we need to consider the standard life cycle of a large galaxy like our own. Galaxies are not static islands. They are dynamic systems that grow and change over billions of years through a process of cosmic cannibalism. A large galaxy's gravitational pull attracts smaller satellite galaxies, which it eventually merges with and absorbs. It also pulls in vast streams of fresh, pristine gas from intergalactic space. This gas is the lifeblood of a galaxy, fueling the birth of new generations of stars. A mature, massive galaxy like the Milky Way is therefore a composite object, a melting pot of stars of all different ages. Its outer halo is populated with ancient stars, some of which were stolen from smaller galaxies it consumed, while its disk is constantly being replenished with younger, bluer stars born from newly acquired gas. This ongoing process of accretion and star formation is what keeps a galaxy evolving. NGC 1277 defies this entire narrative. When astronomers analyzed its starlight, they made a startling discovery. Virtually all of its stars are incredibly old, dating back to a short, furious burst of star formation that lasted only about 100 million years when the universe was just a billion years old. And then it simply stopped. For the last 10 billion years, NGC 1277 has been in a state of suspended animation. It has not formed any significant number of new stars. It shows no evidence of having merged with other galaxies or accreted fresh gas. It is a closed box, a cosmic time capsule preserving the conditions of the early universe. The term relic galaxy is perfectly apt. It's as if we've discovered a living dinosaur, a creature from a bygone era that has somehow survived unchanged into the present day. This leads to the central question: why? What allowed NGC 1277 to avoid the universal dance of galactic evolution that has affected every other massive galaxy we observe? The answer appears to be its location and its incredible speed. NGC 1277 resides near the center of the massive Perseus cluster, a dense gathering of over 1,000 galaxies. At the heart of such a cluster, hot, ionized gas fills the space between galaxies, creating a toxic, high-pressure environment known as the intracluster medium. For a galaxy to form new stars, it needs a reservoir of cool, neutral hydrogen gas. But NGC 1277 is moving through this cluster at the breathtaking speed of about 3 million kilometers per hour. As it plows through the intracluster medium, the effect is like driving a car through a torrential downpour. The incoming pressure strips away any loose gas, a process called ram pressure stripping. Any gas that NGC 1277 might have had, or any new gas it tried to acquire, was violently ripped away by its own rapid motion, starving it of the fuel needed to make new stars and effectively freezing it in its infant state. But the surprises with NGC 1277 don't end there. Like the mysterious DF2, this relic galaxy also presents a puzzle regarding dark matter. By measuring the velocities of its stars, astronomers can weigh the galaxy. Given its large mass and compact size, scientists expected to find a signature of a massive, extended dark matter halo, the kind that surrounds all other galaxies of its size. Yet the data revealed something startlingly different. The mass of NGC 1277 seems to be accounted for almost entirely by its visible stars. There is little to no evidence of the invisible dark matter scaffolding that should, according to our standard models, dominate its mass. This finding is even more perplexing than the case of DF2, because NGC 1277 is a much larger and more massive galaxy. How could a galaxy that formed so early, at a time when dark matter was thought to be the primary gravitational architect, have managed to assemble itself without accumulating a significant dark matter halo? One provocative explanation is that NGC 1277 was born in a unique way. In the early universe, the first massive galaxies may have formed through the direct, rapid collapse of enormous clouds of gas, without the need for the slow, hierarchical merging of smaller dark matter clumps that we believe built most galaxies. In this monolithic collapse scenario, the stars form so quickly and efficiently that the resulting galaxy is incredibly dense and compact, with the visible stars themselves providing most of the gravitational binding. The dark matter, while present in the general region, might not have had time to settle into a concentrated halo around the galaxy before the violent star formation ceased and the galaxy was launched on its high-speed trajectory through the cluster. It's a theory that suggests there might have been multiple pathways to building a galaxy in the young cosmos, and NGC 1277 is the sole surviving example of a road not taken. The immense value of studying a relic like NGC 1277 is that it provides a crucial benchmark for our theories of galaxy formation. It serves as a control sample, a pristine example of what the first massive galaxies looked like before the messy processes of mergers and accretion began to reshape them. By comparing it to modern galaxies, we can better understand how the universe has evolved over cosmic time. Its existence tells us that the early universe was capable of producing fully formed, massive galaxies with astonishing speed, and that the environment a galaxy finds itself in can have a profound and lasting impact on its entire future. The Cannibal Galaxy, ironically, is a galaxy that never got to feast, a celestial hermit preserved by its own tumultuous journey, offering us a direct glimpse into the ancient past and challenging our assumptions about the invisible forces that shape the cosmos. After the serene, geometric perfection of Hoag's object, our journey into cosmic mysteries takes us to a structure of equal beauty but far greater intimacy. A dying star's final performance staged with such bizarre precision it looks like a set piece from a supernatural thriller. Drifting through the constellation Monoceros about 2,300 light-years away is an object so uniquely structured that astronomers simply named it for its appearance, the Red Rectangle Nebula. Unlike the vast, chaotic clouds of most nebulae, this one is defined by its sharp, angular form. It appears as a nearly perfect X-shape, or perhaps a vast cosmic hourglass, with a series of startlingly straight, ladder-like rungs connecting its sides. These rungs are the nebula's most puzzling feature, giving it the distinct appearance of a red, glowing spiderweb or a celestial Jacob's ladder reaching into the void. This is not the gentle fade of a typical star's death throes. It is a structure of breathtaking symmetry, a farewell note written in geometry. The secret to this remarkable shape lies in the dynamic duo at its heart. The red rectangle is not powered by a single dying star, but by a binary star system. One of these stars is a post-asymptotic giant branch star, a sun-like star in the final, dramatic stages of its life. Having exhausted the nuclear fuel in its core, it has puffed up and is now shedding its outer layers into space in a series of intense, episodic outbursts. This expelled gas and dust would normally form a spherical shell around the star, creating a classic, round planetary nebula. But the presence of the second star, a close orbiting companion, completely disrupts this peaceful expansion. The gravitational pull and orbital motion of this companion star confine the outflowing material, funneling it into two opposing cones that shoot out from the poles of the dying star. From our vantage point on Earth, we are looking directly at the side of this double cone structure, which creates the striking X-shaped pattern we see. However, the cones alone don't explain the ladder, the rungs, those equally spaced horizontal bars present the true enigma. The leading theory to explain this extraordinary detail involves a process that is both delicate and violent, episodic pinching. Imagine the central binary system not as a steady beacon, but as a cosmic bellows puffing out material in rhythmic bursts. Each time the dying star experiences a significant pulse, it ejects a new shell of gas. As this shell expands outward, it is immediately shaped by the binary system's gravitational influence and by the pressure of the stellar wind from the stars. Theorists suggest that these ejected shells are not smooth. They are subject to instabilities that cause them to collapse or pinch at regular intervals as they travel down the conical outflow. This creates a series of denser, brighter rings within the cone, which we see as the rungs of the ladder. The spacing of these rungs acts as a fossil record of the star's pulsations, a timeline of its final, feverish activity. But this explanation, while plausible, is far from complete. The precise regularity of the rungs is what continues to baffle scientists. What mechanism ensures that the pinching occurs at such perfect intervals? It may be tied to the exact orbital period of the binary stars. Every time the stars complete an orbit, their gravitational dance could give a rhythmic kick to the outflow, triggering a new pulse and subsequent pinch at a specific distance. Alternatively, the rungs might be shaped by a series of standing shock waves. As the high-speed stellar wind from the central stars rams into the slower-moving gas that was ejected earlier, it could create a series of colliding fronts that glow brightly, much like the sonic booms created by an aircraft breaking the sound barrier. In this scenario, the ladder is a permanent feature of the outflow's dynamics, a staircase of continuous collisions frozen in the expanding nebula. The red rectangle offers more than just a visual puzzle, it is a chemical factory. Its distinctive red glow comes primarily from a class of molecules known as polycyclic aromatic hydrocarbons, or PAH. These are complex carbon-based molecules that fluoresce in red light when illuminated by the intense ultraviolet radiation from the hot central stars. The discovery of these and other complex organic molecules in the nebula is profoundly significant. It demonstrates that the chaotic environment around a dying star is capable of forging the intricate chemical building blocks of life. The red rectangle, in its stunning depth, may be seeding the interstellar medium with the raw materials for future planets and potentially biology. Its beauty is not just skin deep. It is a glimpse into the cosmic cycle of death and rebirth, where the end of one star provides the ingredients for new beginnings. This nebula, a temporary structure that will dissipate into the galaxy in a mere blink of cosmic time, stands as a magnificent and unsolved monument to the complex, dynamical forces that govern even the most final of stellar acts. While the alien megastructure hypothesis captured the world's imagination, the true scientific process is one of relentless, careful investigation, a journey that has now taken us from thrilling speculation to a far more complex and intriguing reality. The key to solving the mystery of Tabby's star was not a single moment of discovery, but a campaign of continuous observation, spearheaded by dedicated astronomers and an army of citizen scientists. The breakthrough came when the star entered another major dimming event in 2017, and this time, thanks to a wildly successful Kickstarter campaign, a global network of telescopes was locked onto it, ready to capture its light in unprecedented detail. What they found was a definitive spectral signature. As the star dimmed, the light that passed through whatever was blocking it showed a clear color dependence. The dimming was much more pronounced in blue light than in red light. This is a classic fingerprint of light scattering off tiny particles, the same reason our sky is blue. This finding was the death knell for the solid megastructure idea. A solid object, like a giant alien solar panel, would block all colors of light equally, creating a neutral dimming. The data pointed conclusively to dust-fine, microscopic grains smaller than a micrometer in size. This pivot from alien engineering to cosmic dust might sound like a letdown, but in reality, it opened a door to a much richer astrophysical puzzle. The question is no longer, is it aliens, but what created these immense, asymmetric, and ever-changing dust clouds? The original hypothesis of a giant swarm of comets remains on the table, but it requires an almost unimaginable number of them, perhaps the fragmented remains of an entire planet-sized icy body, to explain the deepest observed dips. Another compelling theory suggests that Tabby's star might have recently devoured a planet. The gravitational tides from such a catastrophic event could have torn the world apart, creating a massive, short-lived debris disk that now orbits the star, occasionally passing in front of it and causing the erratic dimming. A third idea proposes that the star possesses a highly unusual and dynamic circumstellar disk, not like the smooth rings of Saturn, but a clumpy, warped structure of dust and gas, perhaps tilted at a strange angle to our line of sight. The irregular shape and timing of the dimming events could then be explained by the complex orbital dynamics of material within this disk. the role of modern space telescopes has been indispensable in this detective story. While NASA Kepler mission discovered the star's bizarre behavior, its successor, the Transiting Exoplanet Survey Satellite, or TESS, has provided crucial follow-up observations. TESS has monitored Tabby's star for extended periods, capturing additional dimming events with its sensitive instruments. This continuous monitoring has allowed scientists to build a more detailed timeline of the star's activity, revealing that the dimming is not completely random but follows complex, overlapping patterns. The data from TESS has further reinforced the dust hypothesis by showing how the dips evolve over time, with finer particles being blown away by the star's radiation pressure while larger grains persist, a dynamic process that would be impossible for a rigid megastructure. Each new observation adds another piece to the puzzle, helping astronomers model the precise size, composition, and distribution of the dust. So, the legacy of Tabby's star is not a faded dream of contact, but a profound lesson in cosmic humility and the power of curiosity. It taught us that the universe is capable of producing phenomena far stranger than our textbooks predicted. It demonstrated the importance of public engagement in science, showing how thousands of people can come together to fund critical research. And most importantly, it revealed a new class of variable star, one where the processes of planetary formation or destruction are playing out on a grand, observable scale. The mystery has evolved from a simple question to a deep exploration of the chaotic environments around young or unstable stars, reminding us that sometimes the most exciting scientific discoveries are not the answers we hope for, but the new, better questions we learn to ask. Imagine a star suffering a death so violent that it obliterates any planetary system that might have once encircled it. A supernova explosion is one of the most energetic events in the universe, capable of vaporizing worlds and scattering their atoms across light years of space. In the wake of such a cataclysm, all that remains is a bizarre, ultra-dense stellar corpse called a neutron star, spinning with dizzying speed and blasting its surroundings with intense radiation. It is the last place anyone would ever think to look for planets, and yet, in 1992, astronomers made a discovery that defied all expectations. They found the very first exoplanets ever confirmed orbiting a pulsar, a type of neutron star thousands of light years from Earth. This was not just a surprise, it was a revolution, proving that planets could form in the most hostile environments imaginable. The story begins with a pulsar known as PSRB 1257+12. Pulsars are the lighthouses of the cosmos. As a neutron star spins, beams of radiation shoot from its magnetic poles. If these beams sweep across Earth, we detect a pulse of energy with metronomic regularity, often hundreds of times per second. Astronomers Alexander Wolskson and Dale Frail were timing the pulses from this particular pulsar when they noticed something extraordinary. The pulses were arriving slightly early or late in a repeating pattern. This wasn't a glitch, it was a gravitational signature. The minuscule variations were caused by the pulsar wobbling ever so slightly as it was gently tugged by the gravity of orbiting objects. By meticulously analyzing the timing of these pulses, they deduced the presence of not one, but 3 worlds orbiting the dead star. These were the first pulsar planets ever found, a discovery that opened an entirely new chapter in planetary science. The immediate and profound question was, how on Earth, or rather, how not on Earth did these planets get there? A supernova explosion is thought to be utterly destructive. Any planets that existed around the star before its death would have been utterly annihilated. So, the existence of these worlds implies a story of cosmic rebirth. The leading theory is that the planets are second-generation worlds born from the ashes of the star's destruction. When the original massive star went supernova, it did not expel all of its material into space. A significant amount of debris, rich in heavy elements forged in the stellar explosion and its final moments, would have remained bound to the neutron star, forming a vast, swirling disk of gas and dust around it. This debris disk, similar to the protoplanetary disks from which planets form around young stars, then provided the raw material for a new round of planet formation. In this scenario, the death of one star literally gave birth to new worlds, a phoenix-like emergence of planets from the stellar grave. But what must it be like on such a world? The conditions would be unlike anything in our own solar system. Firstly, there is the radiation. A pulsar emits a deadly torrent of X-rays and gamma rays. Any atmosphere these planets might have had would have been stripped away eons ago, leaving behind barren, blasted rock. Secondly, the planets are likely bathed in a constant stream of high-energy particles from the pulsar's wind, creating a permanent, planet-wide radiation storm. And then there is the light. There is no warm, yellow sunrise. Instead, the primary source of light would be the pulsar itself, a pinprick of insane intensity, flickering on and off hundreds of times every second. The landscape would be illuminated in a rapid, strobing effect, with shadows dancing to the rhythm of a dead star's spin. The very definition of a day would be meaningless under such a relentless, flashing sky. The discovery of pulsar planets fundamentally challenged our ideas about the tenacity of planetary systems. It demonstrated that planet formation is an incredibly robust process, capable of occurring not just in the serene nurseries around young stars, but also in the chaotic aftermath of stellar death. This expands the potential habitats for life in the universe, though it stretches the concept to its absolute limit. Could life survive on a world orbiting a pulsar? It seems almost unthinkable. Without an atmosphere to shield against radiation and to regulate temperature, the surface would be completely inhospitable. However, if one of these planets were a large, gaseous world, it might possess a moon with a subsurface ocean like Jupiter's Europa. The moon's icy crust could potentially provide a shield against the worst of the radiation, and tidal heating from the gravitational pull of the pulsar, and the planet could keep the water liquid. While this remains highly speculative, it underscores a key lesson from pulsar planets. Life, if it exists, may be far more ingenious and resilient than we can possibly imagine, finding a way in the most unforgiving corners of the cosmos. But if the idea of planets born from the ashes of a dead star stretches our imagination, then our next mystery presents a vision of worlds that have experienced an even more profound exile. We are about to enter the realm of the ultimate orphans, planets cast adrift from their stellar families to wander the eternal night of interstellar space. These are rogue planets, and their existence forces us to reconsider what a planet even is, painting a picture of a galaxy that may be teeming with more unseen, wandering worlds than stars that light the sky. The very concept of a rogue planet challenges our Earth-centric perspective. We are conditioned to think of planets as objects in neat, elliptical orbits around a parent star, basking in its warmth and light. A rogue planet knows no such comfort. It is a world untethered, flung from its native solar system, or perhaps even forming on its own in the cold, dark collapses of gas clouds that failed to ignite into stars. These solitary voyagers do not experience day or night as we know it. Their surfaces are plunged into a perpetual, deep freeze darkness, with the galaxy providing only a faint, milky glow. Their sunrises are non-existent, their years are infinite, and their temperatures hover just a few degrees above absolute zero. A rogue planet is a permanent testament to the chaos inherent in cosmic evolution, a ghost ship sailing the void between the stars. So how does a planet become an orphan? The primary mechanism is as dramatic as it is simple: gravitational chaos. Young planetary systems are often violent and unstable places. In their infancy, multiple giant planets may form, their gravitational influences pulling and tugging at one another in a delicate dance. Sometimes this dance turns into a brawl. A close gravitational encounter between two gas giants can act like a cosmic slingshot, flinging one of the worlds out of the system entirely, its velocity exceeding the star's escape velocity. This ejected planet is then condemned to an eternal journey through the galactic void. Another possibility involves a stellar flyby. Our sun now resides in a relatively quiet neighborhood, but in its youth it was born in a dense stellar cluster. A passing star venturing too close to our early solar system could have gravitationally perturbed the outer planets, plucking one or more from the sun's grasp and sending them careening into the darkness. In this view, rogue planets are the casualties of gravitational warfare, the lost soldiers of cosmic battles fought long ago. Yet, ejection might not be the only path to solitude. Some rogue planets could be born that way. When a large cloud of gas and dust collapses to form a star, it can sometimes fragment into multiple clumps. Most of these clumps will gather enough mass to ignite fusion and become stars, but some fragments may be too small to ever become stars. These are known as sub-brown dwarfs. These objects form like stars through the direct collapse of a gas cloud, but they end up with planetary masses. They are, in essence, planets that never had a sun. Distinguishing between a planet ejected from a system and one that formed in isolation is a major challenge for astronomers, as their final state, a lonely world in deep space, looks identical from our vantage point. Detecting something that emits no light of its own and floats in the absolute darkness between stars is unsurprisingly one of the most difficult tasks in astronomy. We cannot see them directly. Instead, we must rely on a clever trick of gravity itself, a phenomenon predicted by Einstein's general relativity called gravitational microlensing. Imagine a rogue planet drifting silently through space. From our viewpoint on Earth, it may one day pass directly in front of a distant background star. As it does, its gravity acts as a tiny lens, bending and focusing the light from that faraway star. For a brief period, perhaps only a few hours or days, the background star appears to brighten significantly before fading back to its normal luminosity as the planet moves out of alignment. This temporary flash of light is the only signature of the invisible world's presence. It is a fleeting, incredibly rare event, requiring a perfect alignment between the source, the lens, and the observer. Hunting for these events is a painstaking statistical game, involving the continuous monitoring of millions of stars in the crowded central bulge of our galaxy, where the chances of such an alignment are highest. The results of these microlensing surveys have been nothing short of revolutionary. They suggest that the number of rogue planets in our galaxy is staggering, potentially numbering in the billions or even trillions. Some studies imply there could be hundreds of rogue planets for every star in the Milky Way. If true, this means the dark, empty spaces between stars are not empty at all, but are in fact crowded with these dark, nomadic worlds. They would be the true silent majority of our galaxy, the unseen backbone of the cosmic population, far outnumbering the stellar-bound planets we are familiar with. This revelation completely transforms our understanding of galactic architecture, suggesting that the classic image of a galaxy as a collection of stellar systems with orbiting planets is only a small part of the story. The vast majority of planetary mass objects may be drifting alone in the cold, immense darkness. This abundance of orphaned worlds naturally leads to a tantalizing question: could any of them harbor life? The prospect seems bleak at first glance. Without the steady warmth of a star, their surfaces are frozen wastelands. However, life on Earth has shown an incredible ability to thrive in the most unexpected places, drawing energy not from sunlight but from geological processes. A rogue planet with a thick, insulating ice shell could potentially hide a vast subsurface ocean, kept liquid by the internal heat left over from its formation or by the decay of radioactive elements in its core. On such a world, life could exist around hydrothermal vents on the ocean floor, much like the ecosystems found in the deepest, darkest parts of Earth's oceans, completely independent of any sun. In this scenario, a rogue planet would be a sealed aquatic biosphere, a lone arc of life traveling between the stars, completely isolated from the rest of the universe. While the chances are slim, the sheer number of these worlds makes the possibility that at least one could be a life-bearing vessel a profound and haunting thought. The silent wanderers of the galaxy may not just be frozen rocks, they could be the dark, secret carriers of biology on journeys that last for eternity. But if the idea of planets forged from stellar ash or exiled to the cold dark stretches our imagination, then our next destination presents a world of such extreme and paradoxical luxury that it seems ripped from the pages of a cosmic fairy tale. Imagine a planet where mountains might glitter with crystalline carbon, where rivers of lava flow over a crust that could be worth quadrillions. This is not science fiction. This is the best current model for 55 Cancri, a world so bizarre it has earned the nickname the Diamond Planet. Located a mere 40 light-years away in the constellation Cancer, this exoplanet orbits a sun-like star so close that a single year, one complete orbit, takes less than 18 hours. The proximity to its star is the first clue to its hellish nature, but it's the planet's unique composition that truly sets it apart and sparks a fascinating scientific debate about what its surface is actually like. The journey to this astonishing conclusion began with a fundamental question: what is this planet made of? To answer that, astronomers didn't need to travel there. They used the planet itself as a scale. By measuring the subtle wobble it induces in its host star, they could calculate its mass. Then, by observing the tiny dip in the star's brightness as the planet passed in front of it, they could determine its size. Combining these two pieces of data gives us the planet's density. 55 Cancri is about twice the size of Earth but has nearly 9 times its mass, making it incredibly dense. This high density immediately ruled out a gaseous world like Jupiter or a predominantly watery world. The planet had to be rocky but composed of elements much heavier than those that make up Earth. The crucial breakthrough came when astronomers studied the chemical composition of its host star. They found that the star is rich in carbon and has a higher ratio of carbon to oxygen than our Sun. Since planets form from the same primordial cloud of material as their star, it stood to reason that 55 Cancri would also be carbon-rich. This is where the cosmic alchemy begins. On a carbon-rich world under immense pressure, the conditions are perfect for creating diamond. Think about the chemistry of our own Earth. Our planet is oxygen-rich, which is why the most common rocks are silicates, compounds of silicon and oxygen. But on a world dominated by carbon, the story is different. Deep beneath the surface, where pressures are millions of times greater than what we experience at sea level, carbon atoms would be forced into a rigid crystalline structure, diamond. Scientists modeling the interior of 55 Cancri suggest that a significant portion of its interior, perhaps up to a third of its entire mass, could have crystallized into a vast layer of diamond surrounding a core of molten iron. This isn't a thin crust, it's a planetary-scale gemstone. The sheer volume of diamond hypothetically present would dwarf all the known reserves on Earth, but of course, its value is purely scientific, as retrieving it is an impossibility. However, the story of this world's surface is far less clear-cut and much more volatile. The same intense heat that bathes the planet, with estimated surface temperatures soaring past 2,500 degrees Celsius, creates a terrifying paradox. How can you have a solid diamond surface when the temperature is high enough to melt rock? This has led to a fierce debate, with two compelling but opposing models vying for dominance. The first, and perhaps more dramatic, scenario is that of a global lava ocean. In this view, the surface of 55 Cancri is a perpetual, roiling sea of molten silicate rock and carbon. The extreme heat from the nearby star simply keeps the entire surface liquid, with perhaps occasional solid continents of graphite, a different form of carbon floating on the magma like dark, scorched icebergs. Observations from the Spitzer Space Telescope seem to support this idea, showing wild swings in the planet's temperature. This suggested a dynamic surface where volcanic activity might be constantly resurfacing the planet, with fresh lava flows cooling and then rapidly reheating, explaining the temperature variations. The second and more recent theory is even stranger. It proposes that the planet is tidally locked, meaning one side permanently faces the star in scorching eternal daylight, while the other is locked in perpetual frigid night. New data from the James Webb Space Telescope has revealed a surprising lack of heat being distributed from the day side to the night side. This suggests that the planet may not have a substantial atmosphere to transfer heat. But the most astonishing finding was a distinct dip in the day side's thermal emission at specific wavelengths, a signature that could be explained by the presence of an atmosphere, but not one made of oxygen or nitrogen. The data suggests a thin, secondary atmosphere constantly being replenished by the planet itself, likely composed of carbon monoxide or carbon dioxide. This has led to a radical new hypothesis that the immense heat and pressure on the day side are somehow vaporizing rock, creating a tenuous but detectable gaseous envelope. The surface in this model could still be solid in places, but it would be a surface unlike any other, possibly shimmering with a faint gaseous haze born from vaporized minerals. So, is 55 Cancri E a glittering diamond orb or a hellish lava world? The truth may be a complex combination of both, a testament to the incredible diversity of planetary environments. It might feature a diamond-rich interior beneath a surface that is partially molten, with a thin, vaporized rock atmosphere struggling to exist against the stellar onslaught. The ongoing study of this world is a perfect example of how exoplanet science evolves. Each new observation, especially from powerful tools like the James Webb Telescope, refines our models, forcing us to replace simple, evocative ideas like a diamond planet with more nuanced and often even more fascinating realities. 55 Cancri E stands as a reminder that the universe is capable of creating worlds that defy easy categorization, places where the line between precious gem and apocalyptic inferno is blurred by the unforgiving laws of physics. After exploring the bizarre diamond and lava world of 55 Cancri E, our search for cosmic companions takes a logical next step. We've found thousands of planets, but what about their moons? Within our own solar system, moons like Europa and Enceladus are considered prime targets in the search for life. The question naturally arises, do exoplanets have exomoons? This leads us to a tantalizing and deeply controversial candidate known as Kepler 1625b, a potential discovery that pushed the limits of our detection methods and ignited a fierce debate about what constitutes proof in the challenging frontier of exomoon hunting. The quest to find a moon light years away relies on a delicate and indirect technique, watching for shadows. The primary method for discovering exoplanets is the transit method, where a planet passes in front of its host star, causing a tiny, periodic dip in the star's brightness. Finding an exomoon using this same technique is exponentially more difficult. You are now looking for a dip within a dip. The ideal scenario involves a giant planet, like a Jupiter analog, transiting its star. As the planet begins its passage, it causes the main drop in light. But if a large moon is orbiting that planet, it might transit the star either slightly before or after the planet itself. This would create a smaller, secondary dip in the light curve, a faint echo of the main event. Alternatively, the moon's gravitational tug could cause the planet to wobble slightly, making the planet's transit start a little earlier or later than expected, a phenomenon known as transit timing variations. It was precisely this combination of clues that astronomers were looking for when they pointed the Kepler Space Telescope at a star called Kepler 1625, over 8,000 light-years away. The initial hints emerged from a meticulous analysis of Kepler's archival data. A team led by astronomers David Kipping and Alex Tichy of Columbia University noticed something peculiar about the gas giant planet Kepler 1625b. This planet is a behemoth several times the mass of Jupiter, and it transits its sun-like star every 287 days. When the team examined the light curve of these transits, they identified tantalizing anomalies. There appeared to be a second, much smaller dip in brightness following the main planetary transit. Furthermore, the planet itself seemed to be starting its transit about 75 minutes earlier than predicted. These two signals together pointed toward a compelling explanation: the gravitational influence of a large moon. The excitement grew when the team secured precious time on the most powerful space telescope available at the time, the Hubble Space Telescope, to conduct a dedicated, high-precision observation of the next predicted transit. The Hubble data they announced in 2018 seemed to confirm their suspicions. Not only did they observe the transit timing variation, but they also detected a pronounced second dip in brightness after the planet had moved away from the star's disk. The implications were staggering. Based on their analysis, the Moon, designated Kepler 1625b, would be a true giant, a Neptune-sized world orbiting a planet larger than Jupiter. The very concept challenged our solar system-centric view, where moons are typically much smaller than their parent planets. However, in science, extraordinary claims require extraordinary evidence, and the Oumuamua candidate was immediately met with intense skepticism. The central problem is the faintness of the signal. The dip attributed to the Moon was incredibly subtle, buried in the inherent noise of the starlight measurements. Other research groups independently reanalyzed the same Hubble data, applying different statistical models and data processing techniques. Several of these studies concluded that the alleged Moon signal could be explained by systematic noise in the telescope's instruments or by subtle stellar activity, such as the dimming caused by a large sunspot on the star's surface rotating out of view. The transit timing variation, while intriguing, was also questioned. Some argued it was not statistically significant enough to rule out random chance. The controversy highlighted the immense difficulty of this kind of detective work. We are trying to detect the shadow of a moon around a planet we cannot see, from a distance so vast it defies comprehension, using instruments that are operating at the very edge of their sensitivity. The debate over Kepler 1625b is far more than an academic argument about a single data point. It is a crucial learning experience that is shaping the entire future of Oumuamua research. This first candidate taught astronomers that they need to be even more rigorous. It emphasized the necessity of observing multiple transits to see if the anomalies repeat with clockwork regularity, which is the gold standard for confirmation. A single event, no matter how promising, can always be a fluke. The case also underscored the importance of understanding the host star's behavior in exquisite detail, as starspots and other phenomena can perfectly mimic the signal of an orbiting moon. Most importantly, the pursuit of Oumuamuas like this one forces us to expand our imagination. If a Neptune-sized Oumuamua is possible, what other lunar configurations exist in the galaxy? Could there be Earth-sized moons orbiting gas giants in the habitable zone, so-called eyeball planets where a moon is tidally locked to its planet with a permanent dayside facing the star? The search for Oumuamua is ultimately a search for new kinds of worlds, and even the ambiguous result of Kepler 1625b has proven that the universe is likely filled with lunar systems that dwarf the diversity of anything we have yet conceived. But if the discovery of pulsar planets revealed worlds born from stellar destruction, our next mystery takes us back to the very origins of the very first stars, to a celestial relic that seems to defy the very physics of its own birth. In the constellation Leo, a humble and ancient star holds a secret so profound it has been nicknamed the Impossible Star. Officially catalogued as SDSS J 102915, plus 172,927. This faint speck of light is a time machine, a window into the universe's chemical infancy. Its composition is staggeringly primitive, consisting almost entirely of hydrogen and helium, the two elements forged in the Big Bang itself. When astronomers measured its metal content, a term they use for any element heavier than helium, they found it to be over 20,000 times poorer in metals than our Sun. This extreme purity is the heart of the mystery. According to our most detailed models of star formation, a star with such a minuscule amount of heavy elements should never have been able to form in the first place. To understand why this star is so baffling, we need to journey back to the universe's dark ages, a time before the first stars ignited. In the immediate aftermath of the Big Bang, the cosmos was a hot, expanding soup of hydrogen, helium, and a trace amount of lithium. There were no carbon atoms, no oxygen, no silicon, and no iron. The universe was chemically simple but physically unable to form stars. That's because the first step in star formation requires a cloud of gas to cool down. As the gas cools, it loses pressure, allowing gravity to overcome it and cause the cloud to collapse into a dense core. In today's universe, this cooling process is incredibly efficient. Tiny grains of dust silicates and carbon compounds act as miniature radiators. They absorb the cloud's heat and re-emit it as infrared radiation, which easily escapes into space, chilling the cloud from within. Furthermore, elements like carbon and oxygen can form molecules like carbon monoxide, which also cool the gas through their rotational and vibrational motions. These cooling mechanisms are the essential catalysts for star birth. Without them, the gas would remain too hot and too diffuse, and gravity would never be able to pull it together. This is precisely the problem with the impossible star. It formed from gas that contained virtually none of these crucial ingredients. There was no dust to radiate heat away and no heavy elements to form cooling molecules. The primordial gas cloud from which it was born should have been unable to shed its heat, remaining puffed up and resistant to gravitational collapse. It's like trying to form an ice cube in a perfectly insulated thermos. The water simply cannot lose its heat. Our simulations of early star formation have long suggested that there must be a critical threshold of metal content, a metallicity floor, below which gas clouds cannot fragment and collapse to form low-mass stars like the one we see. SDSS-J 102,915 plus 172,927 sits far, far below that theoretical floor. Its very existence is a direct challenge to our understanding of the physics that built the first generation of stellar lights in the cosmos. So how did the impossible star defy the odds? Astronomers have proposed several fascinating solutions to this cosmic conundrum. One leading idea is that the star did not form in isolation, but was instead a smaller sibling in a cluster dominated by a true behemoth. The first stars in the universe, known as population 3 stars, are thought to have been colossal, weighing hundreds of times the mass of our Sun. These giants would have had tremendous gravitational pull. In this scenario, the powerful shockwaves and radiation from a nearby massive star could have compressed the surrounding pristine gas, triggering a secondary wave of star formation even in the absence of efficient cooling. The sheer force of the environment might have provided the extra push needed to overcome the thermal pressure, allowing a few smaller stars like SDSS-J 102,915 plus 172,927 to condense in the wake of a celestial titan. It would be a case of cosmic teamwork where the death throes of one star create the conditions for the birth of another. Another possibility involves a different cooling pathway that might have been available in the early universe. While heavy elements were absent, there was one molecule that could form even in pristine gas, molecular hydrogen, or H2. Two hydrogen atoms can weakly bond together, and this molecule can cool gas, though it is thousands of times less efficient than the dust and metals we have today. Perhaps under just the right conditions of density and temperature, this feeble molecular hydrogen cooling was somehow enhanced, allowing the gas to cross the critical threshold for collapse. This process would have been incredibly slow and fragile, only capable of producing stars under a very narrow set of perfect circumstances. The impossible star would then be the rare survivor of an inefficient and mostly unsuccessful mode of star formation, a testament to a time when the universe was still figuring out how to turn on its lights. The significance of this star extends far beyond its own improbable existence. It serves as a crucial benchmark, a single data point that anchors our models of the universe's chemical evolution. By studying its composition, we gain a direct measurement of the conditions in the galactic gas cloud that existed over 13 billion years ago. It tells us that the early universe was not a monolithic environment. It must have had pockets where star formation could proceed in unexpected ways, perhaps leaving behind a population of these small, incredibly ancient stars that we are only now beginning to discover. Finding more stars like SDSS-J 102,915 plus 172,927 is a primary goal for next-generation telescopes like the James Webb Space Telescope, which will be able to peer back to the era of the very first galaxies. Each new primordial star we find adds another piece to the puzzle of how our universe transitioned from a simple, dark expanse of hydrogen and helium into the complex, star-filled cosmos we inhabit today. The impossible star is not an error in the cosmic code. It is a clue, a whisper from a time when the rules of creation were being written, challenging us to listen more carefully to the story it has to tell. We are accustomed to thinking of a supernova as the ultimate finale, a star's grand, self-destructive exit that leaves behind either a super-dense neutron star or a black hole. It is the definitive end of a stellar life. But what if some stars don't quite get the script right? What if, instead of a complete annihilation, they experience a failed detonation, a partial explosion that leaves a scarred and mangled remnant behind to linger in a sort of cosmic undeath? This is the bizarre reality behind a class of stellar explosions known as Type IX supernova, events so peculiar they have earned the chilling and fitting nickname of zombie stars. To understand why these events are so strange, we first need to look at the standard model for a particular kind of supernova. A Type Ia supernova is one of the most important phenomena in astronomy. It occurs in a binary star system where one star is a white dwarf, the Earth-sized, super-dense core of a star like our Sun that has run out of fuel. If this white dwarf has a companion star, it can slowly siphon material, primarily hydrogen, from its partner. As the white dwarf greedily accretes this matter, its mass increases. There is a critical threshold known as the Chandrasekhar limit at about 1.4 times the mass of our Sun. When the white dwarf reaches this limit, the pressure and temperature in its core become so extreme that it triggers a runaway nuclear fusion reaction. This fusion ignites carbon and oxygen almost instantaneously, and the entire white dwarf is obliterated in a titanic thermonuclear explosion so uniform and predictable that it always reaches the same peak brightness. This consistency makes Type Ia supernova invaluable standard candles for measuring cosmic distances, and it was their study that led to the Nobel Prize-winning discovery of dark energy. Type IX supernova are the weird, weaker cousins of these standard explosions. They share many of the same spectral signatures, indicating they also involve a white dwarf and the fusion of carbon and oxygen. But the comparison ends there. A typical Type IX supernova is far less energetic, only about 1% as bright as a full-fledged Type Ia. It's like the difference between a nuclear bomb and a stick of dynamite. Both are explosive, but one is vastly more powerful. Furthermore, the light from a Type IX event fades much more quickly, but the most jaw-dropping difference is what happens to the white dwarf itself. While a Type Ia explosion leaves absolutely nothing behind, scattering the white dwarf's atoms across space, evidence is mounting that in many Type Ix events, the white dwarf somehow survives the blast. It is not destroyed, but rather severely damaged, hurling a portion of its mass into space while the wounded remnant is kicked away from the explosion site. This stellar survivor is the zombie star, a dead star that experienced a partial resurrection through a failed suicide. So how does a star fail to explode properly? The leading theory is that the thermonuclear fusion that ignites inside the white dwarf does not propagate outward as a supersonic shockwave, which would tear the entire star apart. Instead, it may be a subsonic deflagration, a slower, churning burn that is more like a simmer than a detonation. Imagine lighting a firework that fizzles and sparks violently but doesn't actually explode. In this model, the fusion flame flickers and dances through the white dwarf's interior, ejecting a significant amount of material and releasing a tremendous amount of energy, enough to qualify as a supernova, but it fails to consume the entire star. The result is a battered remnant, a white dwarf that has lost a substantial part of its mass and is now hurtling through space, possibly at high speed, bearing the scars of its traumatic partial eruption. This zombie star would be incredibly hot and bright initially, but it would gradually cool over millions of years, returning to its quiet, undead state. The existence of these events forces a major revision of our understanding of stellar death. It tells us that the process of triggering a thermonuclear supernova is not always an all-or-nothing affair. The conditions inside the white dwarf, its composition, its rotation, or the precise point where fusion ignites, must create a delicate balance that determines whether the explosion is a complete success or a partial failure. Finding and studying the predicted zombie remnants is the next crucial step in confirming this theory. Astronomers are actively searching for the hypervelocity, super-hot white dwarfs that should be the smoking guns left behind by Type Ix explosions. Each one they find provides a vital clue to the complex physics occurring in the heart of these strange stellar events. The zombie star phenomenon reveals a previously unknown pathway in stellar evolution, a dramatic testament to the fact that even in death, stars can defy our expectations in the most spectacular ways. While the hunt for WIMP has captivated physicists for decades, another dark matter candidate has been steadily gaining traction. A particle so light and ghostly it behaves less like a discrete bullet and more like a pervasive cosmic wave. This is the Action, a hypothetical particle born not from the dark matter problem itself, but from a seemingly unrelated puzzle deep within the nucleus of the atom. To understand why we would invent such a particle, we have to delve into one of the most exquisitely fine-tuned properties of the universe, the symmetry of the strong nuclear force. The strong force is what holds the protons and neutrons together in an atom's core, overcoming their tremendous electrical repulsion. For this force to work as we observe it, a particular symmetry known as charge parity or CP symmetry must be perfectly preserved. Yet, in the 1970s, physicists realized that the equations governing the strong force naturally allow for a violation of this symmetry, a violation that would have dramatic consequences, such as giving the neutron a much larger electric dipole moment than experiments could detect. The fact that we observe no such violation means that nature has somehow contrived to cancel this effect out with near-perfect precision. It's as if a fundamental dial in the universe's control panel has been set to zero for no apparent reason. This is the strong CP problem, and it begged for an elegant solution. The most compelling solution, proposed by physicists Roberto Pexi and Helen Quinn, was to introduce a new field that pervades all of space. The idea is that this field dynamically adjusts itself to cancel out the unwanted CP violation, naturally driving the offending dial to zero. Where there is a field in quantum mechanics, there must be a particle associated with it, and this particle is the Action. In solving the strong CP problem, theorists had inadvertently created a perfect dark matter candidate. Actions would be incredibly light, potentially billions of times lighter than an electron, and they would interact with normal matter only very weakly, making them essentially invisible. But their most remarkable property is their proposed production mechanism in the early universe. Unlike WIMP, which are thought to be thermal relics particles that froze out as the hot, dense universe-cooled actions would have been created in a different way. As the Peck-Quinn field settled into its minimum energy state, it would have begun to oscillate. These universe-spanning oscillations would not produce a stream of individual particles, but rather a coherent wave-like field. And according to Einstein's most famous equation, energy has mass. The immense energy stored in these oscillations would manifest as a colossal amount of mass, a mass that never interacts with light. This process could have produced exactly the right amount of cold, collisionless matter to account for the dark matter we observe today. The behavior of a universe filled with actions would be profoundly different from one filled with WIMP-like particles. Because actions are so light, quantum mechanics dictates that they would have an incredibly large wavelength. Instead of behaving like a swarm of individual bullets, a collection of actions would act more like a single, coherent fluid, a wave washing through the cosmos. This wave-like nature could even have observable consequences on the scale of individual galaxies. Some theories suggest that the ultra-light action field could condense into what are known as Bose-Einstein condensates, forming stable, macroscopic clumps that could influence the distribution of stars within a galaxy's core. This opens up the possibility that dark matter isn't just a featureless halo, but might have a rich, dynamic structure of its own on surprisingly small scales, a structure dictated by wave interference patterns on a galactic scale. The shift from hunting heavy WIMP to hunting ethereal actions requires a complete reimagining of detection technology. You cannot look for a rare nuclear recoil from a particle that barely interacts. Instead, action hunters rely on a clever prediction made by physicist Pierre Sicavy. In the presence of a strong magnetic field, an action should very rarely convert into a photon. This is the basis for modern action searches like the Action Dark Matter experiment, or ADMX. ADMX is essentially a high-tech radio receiver housed inside a powerful magnet. The experiment uses a tunable microwave cavity, a kind of resonant chamber, and cools it to near absolute zero to eliminate thermal noise. The idea is to shine a magnetic field through this cavity and slowly tune its resonant frequency. If the mass of the action corresponds to a frequency within the cavity's range, the actions passing through the magnetic field should convert into microwave photons, producing an extremely faint but detectable signal. It's like trying to find a single radio station broadcasting from across the galaxy by patiently turning a dial through the static, listening for a whisper of a signal. ADMX and its successors are now scanning through the possible mass ranges with increasing sensitivity, representing a bold and ingenious approach to uncovering the invisible majority of our universe. The action, a particle conceived to solve a deep mystery of nuclear physics, may ultimately be the key to unlocking the even grander mystery of the cosmos's dark architecture. We've explored dark matter candidates from the heavy, bullet-like WIMP to the wave-like, ultra-light actions. But our journey into the speculative frontiers of physics now takes us to a concept so abstract it challenges the very definition of what a particle is. Imagine a form of matter that doesn't come in discrete packets with a specific mass, but instead behaves as a continuous, scale-invariant substance. This is the mind-bending proposal of unparticle physics, a theory that suggests there could be an entire hidden sector of reality operating under rules completely different from those in our standard model. The idea was first proposed by physicist Howard Georgi in 2007. It springs from a fascinating possibility that our universe in its earliest, most energetic moments contained not just the fields and particles we know, but also a separate, hidden sector of particles interacting through their own unique forces. As the universe cooled and underwent phase transitions much like water freezing into ice, our familiar particles acquired mass through the Higgs mechanism. But Georgi suggested that this hidden sector might have undergone a very different kind of transition. Instead of ending up with particles of definite mass, it could have condensed into a scale invariant state. Scale invariance is a property where something looks the same no matter how much you zoom in or out. A classic example is a fractal pattern where the same intricate structure repeats at every level of magnification. Unparticle stuff would embody this principle in physical form. It wouldn't be made of distinct particles like electrons or quarks. It would be a continuous, smeared-out substance with properties that are strangely fuzzy and indeterminate. So what would this unparticle stuff actually look like in an experiment? Since it doesn't have a definite mass, it wouldn't show up as a sharp spike in a particle detector, which is how we normally identify new particles. Instead, its signature would be a continuous spectrum of energy, a smooth and featureless distribution that could mimic background noise. If unparticles interact very weakly with our familiar matter, these interactions might manifest as small, inexplicable irregularities in the energy and momentum of particles produced in high-energy collisions at places like the Large Hadron Collider. It would be like trying to hear a single, pure musical note being played, but instead detecting a subtle, dissonant hum underlying all the other sounds. Disentangling that hum from the cacophony of known physics is the monumental challenge. Unparticle physics predicts that this hidden sector could influence our world through very subtle residual forces, potentially causing deviations from the predictions of the standard model in the behavior of subatomic particles, or even in the precise measurements of gravitational forces at microscopic distances. The connection to other cosmic mysteries, particularly dark matter, is immediately tantalizing. Could this unparticle stuff be the elusive dark matter itself? It's a compelling thought. The continuous, fluid-like nature of unparticles could potentially explain why dark matter seems to form smooth halos around galaxies rather than clumping together as strongly as normal matter does. Its scale-invariant properties might also offer a new perspective on the hierarchy problem, the puzzling question of why the force of gravity is so weak compared to the other fundamental forces. If gravity were to leak into an unparticle sector, it could explain its apparent feebleness in our world. Furthermore, the gentle, pervasive influence of unparticles could provide an alternative explanation for the anomalous magnetic moments of particles like the muon, where experimental results have persistently shown a slight discrepancy from theoretical predictions, a possible hint of physics beyond the standard model. However, the sheer strangeness of unparticle physics also makes it incredibly difficult to test. Without a clear, sharp signature, any potential signal could be attributed to other effects or to systematic errors in the experiments. The theory is also highly speculative, residing in a domain of theoretical physics that is rich with mathematical elegance, but still awaits a decisive experimental confrontation. Yet, its value lies precisely in its ability to push our imagination. It forces us to consider that the fundamental building blocks of the universe might not be tiny, billiard ball-like points, but could be something far more nebulous and alien. The search for unparticles, while a long shot, encourages physicists to look for anomalies in their data with fresh eyes, to consider that the secrets of the cosmos might be hidden not in clear, distinct signals, but in the subtle, overlooked whispers of the quantum void. It represents the cutting edge of theoretical curiosity, a reminder that our quest to understand dark matter and the fabric of reality may require us to invent entirely new concepts of what matter itself can be. But if the concept of unparticles challenges the very definition of matter, our next mystery presents a device that seemed to challenge the most fundamental laws of motion themselves. We now turn from the ethereal realms of theoretical physics to a small, truncated cone that, for a brief and electrifying period, promised to rewrite the rules of spaceflight. This is the story of the M drive, or electromagnetic drive, an engine that became the center of a firestorm of controversy by claiming to achieve the impossible, generating thrust without expelling any propellant whatsoever. The idea immediately captured the public's imagination, offering a vision of spacecraft that could travel to Mars in weeks or to the outer solar system in months, unshackled from the need to carry enormous tanks of heavy fuel. But for physicists, it was a proposition that rang every possible alarm bell because it appeared to blatantly violate Newton's third law of motion. For every action, there is an equal and opposite reaction. Rockets work by throwing mass backward at high speed. The reaction to that action is the forward thrust. The M drive proposed a way to get the reaction without the action, a concept akin to pulling oneself up by one's bootstraps or trying to accelerate a car by pushing on the dashboard from the inside. The principle behind this seemingly miraculous device was deceptively simple. The M drive was essentially a sealed copper cavity shaped like a frustum, a cone with its tip lopped off. When researchers pumped microwave energy into this cavity using a magnetron, similar to the one in a household microwave oven, the microwaves would bounce around chaotically inside the enclosed space. The inventor, Roger Scheuer, proposed that the radiation pressure exerted by these microwaves would be greater on the larger, flat end of the cavity than on the smaller end. This difference in pressure, he argued, would result in a net force or thrust pushing the larger end forward. It was an idea rooted in the physics of cavity resonators, but applied in a way that was entirely novel and, according to established physics, fundamentally flawed. The core criticism was that within a closed system, the radiation pressure should balance out. The photons bouncing around have momentum, but when they reflect off a surface, they impart an equal and opposite momentum to it. In a perfectly sealed chamber, these forces should cancel each other out, resulting in zero net thrust. The M drive, critics argued, was essentially claiming it could create a force from nothing, a modern-day perpetual motion machine. Yet the controversy exploded because experimental results, however faint, refused to go away. The first major spark came when a team of Chinese researchers, led by Huan Yong at Northwestern Polytechnical University, claimed to have measured a small but persistent thrust in their own M drive experiments. But the real catalyst was the work of a group at NASA Eagleworks Laboratory, an advanced propulsion research group led by Harold "Sonny" White. In 2016, they published a peer-reviewed paper reporting that, under carefully controlled conditions in a vacuum chamber, their M drive prototype had produced a thrust of about 1.2 millinewtons per kilowatt of power. To put that in perspective, this is an incredibly tiny force, roughly equivalent to the weight of a single grain of sand. But in the context of space propulsion, where efficiency over long periods is key, even this minuscule thrust, if real and scalable, would be revolutionary. The key point was that the NASA team, a credible group within a respected institution, had seemingly confirmed an anomalous effect that defied conventional explanation. The scientific response to these claims was a masterclass in rigorous skepticism. The consensus among physicists was overwhelmingly that the measured thrust was not evidence of new physics, but almost certainly the result of subtle, unaccounted for experimental errors. The challenge of measuring such a tiny force is immense. Scientists proposed a litany of potential artifacts that could mimic the thrust signal. One of the most prominent explanations involved thermal effects. As the microwave energy resonates within the copper cavity, it heats the metal, causing it to expand. This thermal expansion could cause the entire device to shift minutely on its test stand, creating a false thrust reading. Another major suspect was the interaction of the device's power cables with Earth's magnetic field. Even in a vacuum, the electrical currents flowing into the M drive could generate Lorentz forces, the same principle that drives an electric motor. which would push against the terrestrial magnetic field and produce a measured force that had nothing to do with the cavity itself. The team's efforts to shield against these effects were deemed insufficient by many critics. The quest for a definitive answer reached its climax with one of the most thorough experimental investigations ever conducted into the M drive. A team at the Dresden University of Technology in Germany built an incredibly sensitive torsion balance, a device designed to measure infinitesimally small forces, and placed it inside a vacuum chamber on a foundation designed to dampen external vibrations. Their apparatus was a masterpiece of precision engineering, built specifically to eliminate the suspected sources of error. They ran tests with painstaking care, and their results were unequivocal. They did measure a thrust signal, but they also discovered its true source. When they replicated the experiment while deliberately introducing known sources of error, like asymmetric thermal effects, they reproduced the exact same thrust signature. Most tellingly, when they modified the experiment so that the microwaves could not possibly generate the proposed thrust, by using a different mode of resonance that should not work according to the M-drive theory, they still measured the same force. The thrust, they concluded, was not coming from some novel physics within the cavity. It was a systematic error caused by the interaction of the heated device with the test stand and the surrounding environment. The impossible thrust had a very possible and very ordinary explanation. The legacy of the M-drive is therefore not one of a revolutionary discovery, but a powerful lesson in the scientific process. It demonstrates how a compelling idea, combined with ambiguous but persistent data, can capture our hopes and drive further investigation. It showcases the importance of healthy skepticism and the relentless pursuit of experimental rigor to weed out error from breakthrough. While the dream of a propellant-less engine remains just that, a dream, the controversy pushed engineers to develop more sensitive measurement techniques and to think more creatively about the future of space propulsion. The M-drive serves as a reminder that in science, extraordinary claims require not just extraordinary evidence, but evidence that can withstand the most brutal and thorough scrutiny imaginable. It is a case where the process of debunking was, in its own way, as valuable as a confirmation would have been, reinforcing the self-correcting nature of scientific inquiry. Now, let's drill down from the vast scales of cosmic propulsion to the unimaginably small, to the very heart of matter itself. Deep within the atomic nucleus, where protons and neutrons are bound by the powerful, strong nuclear force, lies a prediction so fundamental it has become a cornerstone of modern physics. You cannot have a particle made solely of neutrons. The reasoning is elegantly simple. Neutrons left to their own devices are unstable. A free neutron will decay into a proton, an electron, and an antineutrino in about 15 minutes. But even inside a nucleus where they are stable, the powerful nuclear force that binds them requires a delicate balance. Protons, with their positive charge, introduce a repulsive force that the strong force must overcome. The stability of a nucleus is a tightrope walk between these competing interactions. For decades, physicists have been convinced that a cluster of neutrons alone, without any protons to help bind them, would fly apart instantaneously. The mutual repulsion and the lack of the specific binding magic provided by the proton-neutron interaction should make such a structure impossible. It's like trying to build a stable arch using only identical, smooth stones that repel each other. Without a keystone, the whole thing collapses. This is why the periodic table of elements starts with hydrogen, which has one proton, and why every known nucleus contains at least one proton to provide that essential stabilizing influence. The idea of a pure neutron droplet has been considered a fantasy, a theoretical impossibility. But what if our understanding of that nuclear tightrope is incomplete? This brings us to one of the most provocative and elusive targets in modern nuclear physics, the tetraneutron. As the name suggests, a tetraneutron would be a hypothetical particle consisting of 4 neutrons bound together into a single, fleeting entity. The very concept sends a shockwave through the established models. If such a thing could exist, even for a fraction of a second, it would force a dramatic revision of our theories for the strong force. The first tantalizing hints emerged in 2002 from a team of researchers in France. They were studying the nuclear reactions involving a stable isotope of lithium, lithium-6, and a beam of helium-8, a highly unstable isotope. When they fired the helium-8 nuclei at a target of lithium-6, they observed a signature that was startlingly simple. The reaction seemed to produce a helium-4 nucleus and nothing else. The implication was that the 4 neutrons that should have been ejected from the helium-8 instead briefly stuck together, forming a tetraneutron that then decayed almost immediately. The result was explosive but also highly controversial. The signal was weak, and the interpretation was not the only possible explanation for the data. Many in the nuclear physics community remained deeply skeptical, attributing the finding to a statistical fluke or an alternative reaction pathway that hadn't been fully considered. The hunt, however, was on. The challenge is immense. You cannot simply put 4 neutrons in a bottle and watch what happens. Creating and detecting a tetraneutron requires incredibly sophisticated, indirect methods. The most promising approach is to use a particle accelerator to create a beam of an unstable, neutron-rich nucleus like beryllium-13 and fire it at a target such as a proton-rich hydrogen nucleus. The idea is to trigger a reaction that neatly knocks out the protons, leaving the neutrons behind in a state where they just might, temporarily bind. Then you have to detect the aftermath with exquisite precision, measuring the energies and angles of all the particles involved to reconstruct what happened in that infinitesimal moment. It's a form of subatomic forensics. In 2016, a team in Japan conducted such an experiment and reported seeing a resonant state consistent with a tetraneutron. A resonance in particle physics is like a brief musical chord, a state where particles come together and interact strongly for a moment before flying apart. This was stronger evidence than the initial finding, but it still wasn't considered a definitive discovery. The resonance was incredibly short-lived, on the order of 10 to the power of -22 seconds, a timescale so brief it's almost a philosophical concept. The question remained, was this a true bound state or just a temporary, unbound quartet of neutrons passing near each other? The profound implications of confirming the tetraneutron's existence cannot be overstated. It would be akin to discovering a new law of gravity that allowed for a stable orbit that Newtonian physics deemed impossible. Our current best model for nuclear interactions, known as chiral effective field theory, struggles to accommodate a bound tetraneutron. Its existence would suggest that there are facets of the strong nuclear force that we have not yet accounted for, particularly when dealing with systems that have a large imbalance of neutrons over protons. It could imply that the force between neutrons becomes slightly more attractive under extreme, pure neutron conditions, a subtlety that is washed out in the more balanced nuclei we typically study. This wouldn't break physics, but it would bend it significantly, forcing a refinement of our most fundamental equations. Furthermore, the confirmation of a tetraneutron would open the door to the possibility of even larger neutron droplets. Could there be a hexaneutron or an octaneutron? This would have staggering consequences for our understanding of the most extreme objects in the universe, neutron stars. These city-sized corpses of dead stars are essentially gigantic atomic nuclei, held together by gravity and composed almost entirely of neutrons. If pure neutron matter can form stable or even metastable clusters on a small scale, it could reshape our models of the bizarre, superfluid interior of these cosmic giants. The search for the tetraneutron, therefore, is more than a quest for an exotic particle. It is a direct probe into the forces that shape the most mysterious states of matter in the cosmos. The ongoing experiments, using ever more powerful accelerators and sensitive detectors, continue to walk the fine line between a revolutionary discovery and a persistent, tantalizing mirage. Leaving behind the ghostly whispers of potential dark matter particles, we confront a mystery that arrives not with subtlety, but with a subatomic punch of almost unimaginable power. We are constantly being bombarded by cosmic rays, streams of high-energy particles, mostly protons, that race across the galaxy. Most of these are relatively low energy, but a tiny fraction of them are in a class of their own. These are the ultra-high-energy cosmic rays, and they carry so much energy that it borders on the absurd. Imagine a single proton, a fundamental particle smaller than an atom, traveling with the kinetic energy of a professionally thrown baseball. That is the scale we are talking about, a particle accelerated to energies exceeding 100 exaelectronvolts, millions of times more powerful than what we can create in our most advanced particle accelerators like the Large Hadron Collider. The existence of these particles presents physics with a monumental challenge, famously known as the GZK cutoff paradox, named for physicists Greisen, Zatsepin, and Kuzmin, who first described it. They realized that any proton traveling across the vast distances of the universe with such incredible energy should not be able to reach us at all. That's because the cosmos is not empty. It's filled with the faint afterglow of the Big Bang, the cosmic microwave background radiation. For a proton with ultra-high energy, these background photons are no longer harmless whispers. Due to the relativistic effects of its immense speed, the proton would perceive these low-energy microwaves as a relentless wall of high-energy gamma rays. When the proton smashes into one of these photons, the collision is so violent that it creates new particles like pions, which siphon off the proton's energy. Over a distance of about 150 million light-years, this process should sap the energy of any ultra-high-energy cosmic ray down below the extreme levels we detect. The fact that we see them at all means they cannot have come from too far away. They must be relatively local, cosmically speaking, originating from within our own cosmic backyard, a sphere of galaxies centered on the Milky Way. This, however, only deepens the mystery because it leads to the great cosmic ray detective story, the challenge of tracing their origin. Unlike light, which travels in a straight line, cosmic rays are charged particles. As they journey through space, they are whipped and spun by the Milky Way's tangled magnetic fields. It's as if you were trying to find the source of a downpour by studying a single raindrop that had been blown and tossed by a hurricane. By the time one of these particles slams into Earth's atmosphere, its path is completely scrambled. It provides no direct pointer back to its source. We can detect the particle, but we cannot simply look back along its trajectory to see where it came from. This forces astronomers to become forensic scientists, using indirect methods to hunt for the culprits capable of such immense acceleration. So what cosmic engines in our local universe could possibly be responsible for this? The suspects must be objects of almost unimaginable violence, capable of wielding energies that dwarf supernova. The prime candidate is a class of galaxies known as active galactic nuclei, or AN. At the heart of these galaxies lies a supermassive black hole that is actively feeding on surrounding gas, dust, and stars. As matter spirals into the black hole's gravitational well, it forms an incredibly hot, bright accretion disk, but in some AGN, not all the matter falls in. Powerful magnetic fields can funnel some of the infalling material into colossal jets that shoot out from the poles of the black hole at nearly the speed of light. These jets are nature's ultimate particle accelerators, stretching for thousands of light-years. It is within these relativistic jets that physicists believe protons could be accelerated to the energies we observe, surfing on colossal shockwaves like a surfer on an interstellar tidal wave. Another compelling suspect is the shockwaves from gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. These brief, cataclysmic events, thought to be caused by the collapse of massive stars or the merger of neutron stars, release more energy in a few seconds than our Sun will in its entire 10 billion-year lifetime. The expanding blast wave from such an explosion could easily serve as a particle accelerator on a cosmic scale. Other potential sources include violent processes in galaxy clusters, where the turbulent motion of million-degree gas could generate immense shock waves, or even the giant lobes of radio galaxies, where particles might be reaccelerated over vast distances. The hunt for proof involves a unique form of astronomy that doesn't use traditional telescopes. Instead, scientists use the Earth's own atmosphere as a detector. When an ultra-high-energy cosmic ray hits the atmosphere, it creates a cascade of secondary particles, an expanding shower that can cover dozens of square kilometers on the ground. Massive observatories like the Pierre Auger Observatory in Argentina consist of thousands of water tanks spread over an area the size of Rhode Island, waiting to detect the faint flash of light produced when these secondary particles zip through the water. By measuring the timing and intensity of the shower across this vast array, scientists can reconstruct the energy and, crucially, the rough incoming direction of the original cosmic ray. While the magnetic fields prevent a precise pinpoint, observing multiple events from the same general patch of sky can build a statistical case against a particular source. Indeed, the Auger collaboration has reported a correlation between the arrival directions of the highest energy cosmic rays and the locations of nearby active galactic nuclei, providing tantalizing, though not yet conclusive, evidence that these monstrous black holes are indeed the culprits. Yet, even with these correlations, puzzles remain. Not every ultra-high-energy cosmic ray points back to a known AGN, leaving room for other, perhaps even more exotic sources. Some theorists have proposed the decay of hypothetical super-heavy dark matter particles lurking in the halo of our galaxy. If such particles existed, their decay could produce protons with the requisite energy, and since they would originate within our own galaxy, they would easily avoid the GZK cutoff. This idea elegantly ties one cosmic mystery to another, suggesting that the most energetic particles in the universe might be a signature of its most elusive substance. The enigma of ultra-high-energy cosmic rays and the GZK paradox is a testament to the universe's capacity for violence on scales we are only beginning to comprehend. A constant, invisible rain of messengers from the most powerful engines in the cosmos, challenging us to decipher their origins and the fundamental laws they seem to defy. But if the zombie stars represent a strange failure to die, then the stars we turn to now represent a life lived on the very edge of stability, a constant, violent struggle against their own immense power. We arrive at a class of stellar behemoths so rare, so volatile, and so brilliantly luminous that they defy easy classification, the luminous blue variables. These are not merely large stars, they are the true titans of the cosmos, hypergiants with masses that can exceed 100 times that of our Sun, burning with a ferocious intensity that makes them millions of times brighter. They are the rock stars of the galaxy, living fast, dying young, and prone to spectacular, unpredictable outbursts that can tear them apart on a cosmic stage. And perhaps no star better exemplifies this chaotic existence than Eta Carinii, a ticking time bomb in our own galactic backyard. Situated about 7,500 light-years away in the southern constellation of Carina, Eta Carinii is a binary system, but its primary component is the star that commands all the attention. It is a monster with an estimated mass of between 100 and 200 solar masses, placing it perilously close to the theoretical upper limit for a star. For a star, mass is both a blessing and a curse. It provides the fuel for a spectacularly bright life, but it also creates an immense gravitational pull that tries to crush the star. The outpouring of radiation from the star's core is so powerful that it pushes outward with tremendous force, creating a delicate balance against the inward pull of gravity. In luminous blue variables, this balance is constantly on the verge of collapse. The outward radiation pressure is so extreme that it makes the star incredibly puffy and unstable, causing its outer layers to be gravitationally bound only very loosely. It's like trying to hold onto a vast, seething cloud of gas that is constantly trying to blow itself into space. This inherent instability leads to the most dramatic characteristic of these stars, their giant eruptions. Throughout recorded history, Eta Carinii has been a variable star, but in the 1840s it underwent an event that stunned astronomers. It became the second brightest star in the night sky, despite its vast distance, in an outburst known as the Great Eruption. For nearly 20 years, it shone with an incredible brilliance, ejecting an enormous amount of material, at least 10 times the mass of our Sun, into the surrounding space. This wasn't a slow, steady solar wind. It was a catastrophic, directed expulsion. The ejected material formed two vast lobes of gas and dust, known as the homunculus nebula, which now enshroud the star in a beautiful, bipolar structure that looks like a cosmic hourglass. What could possibly drive such a violent paroxysm? The mechanisms remain one of the greatest unsolved mysteries in stellar astrophysics. One leading theory suggests that the star's luminosity nears the Eddington limit, the point where the outward radiation pressure equals the inward gravitational force. At this threshold, the star becomes so unstable that even a small perturbation can cause it to blow off its outer layers in a series of violent convulsions. Another, more exotic idea involves the star's interior. In such massive stars, the sheer energy can create particle-antiparticle pairs, a process that saps energy from the core and can lead to a massive instability, effectively causing the star to tremble from the inside out until it erupts. The role of Eta Carinii's binary companion adds another layer of complexity to the drama. The two stars orbit each other in a highly elliptical 5.5-year-long dance. When they swing close together, their powerful stellar winds, streaming outward at millions of kilometers per hour, collide with the force of a continuous explosion. This collision creates intense shocks that produce X-rays, and it's possible that these periodic interactions perturb the already unstable primary star, triggering or amplifying its outburst. The binary interaction might be the match that lights the fuse on this cosmic powder keg, but the fundamental instability is baked into the star's own monstrous nature. Studying this system is like watching a cosmic ballet where the dancers are constantly on the verge of exploding, their movements dictating the rhythm of their inevitable demise. The ultimate fate of a luminous blue variable is as spectacular as its life. These stars are thought to be direct precursors to some of the most exotic and energetic explosions in the universe, pair instability supernova. In a star of sufficient mass, the core can become so hot that the radiation within it spontaneously begins to create electron-positron pairs. This process removes the radiation pressure that was supporting the core against collapse. Without that support, the core contracts rapidly, heating up even further and triggering a runaway fusion reaction that completely obliterates the star, leaving behind no remnant, no neutron star, no black hole. The entire star is converted into pure energy in an explosion that can outshine an entire galaxy. Eta Carinii is a prime candidate for such a fate. When it finally does go supernova, it will be a celestial event of unparalleled brilliance, visible from Earth even in broad daylight. It poses no threat to our planet, but it will offer astronomers a front-row seat to the death of a true stellar titan, an event that may only happen a handful of times per millennium in a galaxy the size of our own. The luminous blue variables, therefore, are more than just unstable oddities. They are cosmic crucibles, forging the elements that will seed future generations of stars and planets while teaching us about the ultimate limits of stellar existence. From the violent, unstable lives of stellar titans, we now turn our gaze to a motion so vast it encompasses the entire observable universe, a mysterious current that seems to pull clusters of galaxies in a direction that defies all conventional explanation. This is the phenomenon known as the dark flow, a discovery so controversial it suggests the influence of something truly unimaginable, a structure beyond the cosmic horizon. The story begins not with a single galaxy, but with the careful study of hundreds of galaxy clusters. When astronomers examine the cosmic microwave background radiation, the afterglow of the Big Bang, they see a nearly uniform temperature in every direction. However, there's a subtle effect at play when this ancient light passes through a massive galaxy cluster. As the photons travel through the cluster's gravitational field, they gain a tiny amount of energy, a phenomenon called the kinetic Sunyaev-Zeldovich effect. By measuring this minute spectral shift, scientists can calculate the cluster's velocity relative to the overall expansion of the universe. It's like being able to tell if a ship is drifting with a current or paddling against it by studying the wake it leaves in the water. When a team led by astronomer Alexander Kashlinsky analyzed data from the Wilkinson Microwave Anisotropy Probe and later the Planck satellite, they expected to find that these clusters were moving in random directions, their motion a result of the local gravitational tugs from neighboring structures. Instead, they found something profoundly unsettling. A significant number of clusters, stretching out to billions of light-years away, appeared to be sharing a common motion, streaming coherently toward a specific patch of the sky near the constellations Centaurus and Vela. This wasn't a small, local flow. It was a bulk motion on a scale that should be impossible according to our standard model of cosmology. The gravitational pull required to cause such a vast, coordinated movement would have to come from a concentration of mass so enormous it lies far beyond the limit of what we can see. The most shocking implication is that this gravitational source must be outside our observable universe. The term observable universe is key here, because the universe is only 13.8 billion years old, and because light travels at a finite speed, we can only see a finite volume of space. There is a cosmic horizon beyond which light has not had enough time to reach us. The dark flow suggests that enormous structures, perhaps other universe-sized domains or unimaginably dense concentrations of matter and energy, exist beyond this horizon. Their gravitational influence, unlike light, may not be bound by the same speed limit. While gravity is thought to travel at the speed of light, the fabric of space-time itself was stretched exponentially during the period of cosmic inflation immediately after the Big Bang. It's possible that regions of space that were once close to us were inflated far away, carrying with them immense mass concentrations. Though they are now beyond our visual horizon, their gravitational pull, imprinted on the fabric of space before inflation ended, could still be affecting the motion of galaxy clusters within our observable bubble. This is akin to feeling the tide pulled by a moon that has already dipped below the horizon. Naturally, a claim this extraordinary has been met with intense scrutiny. Critics argue that the detected signal could be an artifact of imperfect data processing. Subtle errors in subtracting the foreground glow of our own Milky Way galaxy from the cosmic microwave background data could potentially create a false pattern that mimics a bulk flow. Other researchers, using different analysis techniques or data sets, have failed to confirm the effect with the same statistical significance, keeping the dark flow firmly in the realm of a contested anomaly rather than an established fact. The debate hinges on exquisite precision, on being able to isolate an incredibly faint signal from an immense amount of cosmic noise. If the dark flow is real, its explanations are as mind-bending as the observation itself. The most dramatic possibility is that it is evidence for the multiverse. In the theory of eternal inflation, our universe is just one bubble in a vast, frothing meta-universe. The dark flow could be the gravitational tug from a neighboring cosmic bubble, a separate universe with its own physical laws and immense structures, residing in the greater multiverse beyond our horizon. Another, slightly less exotic explanation involves a pre-inflationary relic. Perhaps during the very first moments of the Big Bang, before inflation smoothed everything out, there existed a massive density fluctuation on a scale larger than our entire observable universe. As inflation stretched space, this fluctuation was pushed beyond our horizon, but its gravitational fingerprint remains, pulling matter in our universe in a specific direction. The dark flow, therefore, is more than just a curious motion. It is a potential window into the conditions that existed before the Big Bang itself, or a glimpse of a cosmic landscape far grander than we ever imagined. Its resolution awaits more precise data from future observatories, which will either confirm this profound mystery or reveal it to be a phantom in the data, a reminder of the challenges of mapping the ultimate frontiers of reality. But if the dark flow hints at a hidden architecture beyond the cosmic horizon, our next mystery brings us to the very fabric of reality itself, suggesting that the stage upon which the universe plays out may not be fundamental at all. We are about to explore a revolutionary idea that seeks to heal the greatest rift in modern physics: the century-long conflict between the rulebook of the very large, Einstein's general relativity, and the rulebook of the very small, quantum mechanics. This is the tantalizing proposal that space and time are not the smooth, continuous background we intuitively perceive, but are instead emergent properties, a kind of illusion generated by a Chinese letter, 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 Chinese letter for generations. Physicists have struggled to reconcile these two pillars of science. General relativity describes gravity as the elegant curvature of a smooth spacetime fabric, beautifully explaining the orbits of planets and the bending of light around massive galaxies. Quantum mechanics, on the other hand, paints a picture of a frantic, probabilistic world where particles can be in multiple places at once and interact in ways that defy classical intuition. The problem is that these two theories speak different languages and make contradictory predictions, especially under extreme conditions like the center of a black hole or the first moments of the Big Bang. To merge them into a single theory of quantum gravity, something has to give. The most profound possibility is that spacetime itself is not a primary ingredient of the universe, but a secondary collective behavior. Much like the concept of temperature emerges from the collective jiggling of countless atoms, even though no single atom has a temperature itself. This is where quantum entanglement, that spooky action at a distance that so troubled Einstein, enters the stage as a potential cosmic architect. Entanglement is a bizarre connection where two particles become linked in such a way that measuring the state of one instantly influences the state of the other, no matter how far apart they are. For decades, this was seen as a curious, almost inconvenient feature of the quantum world. But a series of groundbreaking insights have suggested that entanglement might be the very glue that holds space and time together. Imagine space not as a pre-existing container, but as a web of connections. The idea is that the degree of entanglement between the quantum bits or qubits of a system actually defines the distance between them. Where there is a high degree of entanglement, you have a short, well-defined spatial separation. Where there is little or no entanglement, points are effectively infinitely far apart. There is no spatial connection between them at all. In this view, the three-dimensional space we move through is a holographic projection of a vast network of entangled quantum relationships, perhaps living on a two-dimensional boundary. This radical concept leads directly to one of the most beautiful and provocative ideas in theoretical physics, the ER equals EPR conjecture, proposed by physicists Juan Maldeisner and Leonard Susskind. This principle connects two ideas that were previously thought to be completely separate. On one side, you have ER, which stands for the Einstein-Rosen bridge, the formal name for a wormhole, a tunnel through spacetime connecting two distant points. On the other side, you have EPR, named for Einstein, Podolsky, and Rosen, the physicists who first highlighted the paradox of quantum entanglement. Maldacena and Suskind's remarkable suggestion is that these are not two different phenomena, but two different descriptions of the same thing. An entangled pair of particles, like two electrons with correlated spins, might be connected by a microscopic wormhole, a Planck-scale bridge in the fabric of spacetime. This isn't a wormhole you could travel through. It's unimaginably tiny, but it provides a geometric picture for what entanglement is, a physical connection through the spacetime geometry itself. The implications of this are staggering. It suggests that the strange, non-local connectivity of quantum mechanics and the geometric structure of general relativity are fundamentally intertwined. When you entangle two particles, you are, in a sense, stitching together the fabric of spacetime between them. This perspective completely reframes the black hole information paradox. Instead of information being lost when it falls into a black hole, the ER equals EPR idea suggests that the Hawking radiation particles leaving the black hole are intricately entangled with the particles that fell inside. This entanglement could be represented by a wormhole connecting them, providing a geometric mechanism for information to be preserved without violating any laws of physics. The information isn't lost, it's simply stored in the complex, non-local connections woven by entanglement. While this is currently a theoretical framework without direct experimental proof, it is guiding physicists toward new ways of thinking about the universe's most fundamental level. It hints that locality, the idea that objects are directly influenced only by their immediate surroundings, may be an emergent property of a deeper, non-local quantum reality. The smooth, continuous spacetime of our everyday experience would then be a coarse-grained, approximate picture that arises from the frenetic quantum entanglement of countless fundamental constituents. Exploring this bridge between entanglement and spacetime is not just an academic exercise. It is a crucial step toward a unified theory of quantum gravity, a theory that would finally allow us to describe the birth of the universe and the heart of a black hole with a single, consistent set of rules. It suggests that the deepest foundations of reality are not particles and forces moving in a void, but a vast, interconnected network of relationships where the very notion of here and there is born from quantum connection. To comprehend the sheer improbability of our existence, we need to delve into the specific recipe that theorists believe was necessary to cook up a matter-dominated universe. This recipe is known as the Sakharov conditions, named after the brilliant Soviet physicist Andrei Sakharov, who first outlined them in 1967. He proposed that for baryogenesis, the genesis of baryons, the protons and neutrons that make up atomic nuclei, to occur, three essential ingredients had to be present in the primordial furnace of the Big Bang. The universe had to satisfy all three. Missing even one would have resulted in a perfect symmetry, a universe of pure light. The first condition is a fundamental break in symmetry, specifically the violation of baryon number conservation. In our everyday, low-energy world, the total number of baryons seems to be constant. You can't create a proton out of nothing in a lab experiment, but Sakharov realized that in the extreme energies of the early universe, this rule had to be broken. Processes must have existed that could change the net baryon number, effectively allowing the universe's matter account to go from zero to a positive balance. While the standard model of particle physics does conserve baryon number in its known interactions, many theories beyond it, such as grand unified theories, predict mechanisms where super-heavy particles decay in a way that preferentially produce more quarks, the building blocks of protons, than antiquarks. The second condition is a violation of both charge conjugation C and parity P symmetry combined. Let's break that down. Charge conjugation symmetry means that if you swap every particle with its antiparticle, the laws of physics should remain the same. A universe made of antimatter should behave identically to our own. Parity symmetry is the idea that physics is mirror-symmetric. A reaction seen in a mirror should look just as valid as the real thing. We know that the weak nuclear force responsible for radioactive decay violates parity maximally. It has a definite handedness like a screw. We also know that there is a small amount of CP violation where the combined operation of swapping particles for antiparticles and looking in a mirror is not perfectly symmetric. This was discovered in the decay of strange particles called kaons. The problem is, the amount of CP violation contained within the standard model is far too feeble to account for the overwhelming matter dominance we see. It's like having a coin that is ever so slightly weighted, but not nearly enough to explain how it landed on heads a billion times in a row. The early universe needed a much stronger bias, a much heavier thumb on the matter side of the cosmic scale. The third, and perhaps most subtle, condition is that the universe had to be out of thermal equilibrium. In a state of perfect thermal equilibrium, every process is balanced by its reverse process. It's a cosmic stalemate where nothing net can happen. For every reaction that creates a slight excess of matter, there's an equal and opposite reaction that destroys it. To break this deadlock, the universe needed to be expanding and cooling so rapidly that certain processes could not keep up. Imagine a pot of water boiling violently. If you cool it down incredibly fast, the steam doesn't have time to condense back into the water perfectly evenly. You might be left with an imbalance. In the early universe, this could have occurred during a phase transition, akin to water freezing into ice. As the cosmos cooled, it may have undergone a shift in the state of its fundamental fields. If this transition was a sudden, first-order phase transition, it could have created bubbles of the new phase expanding within the old. At the walls of these colliding bubbles, conditions would have been wildly out of equilibrium, providing the perfect environment for CP-violating interactions to produce a net surplus of matter over antimatter that was then frozen in place by the rapid expansion, forever preserving the cosmic ledger in favor of existence. The profound challenge is that while we have hints of these ingredients, no single theory currently provides a completely satisfactory and verified mechanism that combines them with the necessary power. The search for the source of this asymmetry is therefore a driving force in physics, pushing us to build more powerful particle colliders to recreate those first moments and to study the properties of elusive particles like neutrinos, which may hold the key to a new, more profound form of CP violation. The matter-antimatter asymmetry is not a settled mystery but an active frontier, a question that strikes at the very heart of why the universe is structured in a way that allows us to be here to ponder it at all. But even as we grapple with the profound implications of the Hubble tension, a discrepancy that threatens to rewrite our cosmic history, we now confront a mystery that strikes at the very heart of theoretical physics, a problem so severe it has been called the worst theoretical prediction in the entire history of science. This is the vacuum catastrophe, and it revolves around a number so unimaginably large it borders on the absurd, 10 to the power of 120. To even begin to comprehend the scale of this error, consider that the number of atoms in the entire observable universe is estimated to be around 10 to the power of 80. The vacuum catastrophe is off by a factor that is a 1 followed by 120 zeros, a number that is larger than the number of atoms in the universe multiplied by itself. This isn't just a small miscalculation. It is a chasm of misunderstanding so vast it suggests that something is fundamentally wrong with our most basic ideas about the nature of nothingness itself. The story begins with a seemingly simple question. What is the energy of empty space? Quantum field theory, our incredibly successful framework for describing the subatomic world, tells us that the vacuum is not truly empty. It is a seething, bubbling foam of virtual particles. Pairs of particles and antiparticles constantly pop into existence out of nothing, borrowing energy from the universe for an infinitesimally brief moment before they collide and annihilate each other, returning the energy loan. This frenetic activity, known as quantum fluctuations, is not just a theoretical curiosity. It has measurable effects such as the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a slight push because there are fewer quantum fluctuations between them than outside. According to quantum theory, the combined energy of all these fleeting fluctuations should contribute a certain energy density to the vacuum of space. This energy density should act exactly like Einstein's cosmological constant, a constant, unchanging force inherent to the fabric of space itself. So, physicists set out to calculate this number. They took the known quantum fields for every fundamental particle, electrons, quarks, photons, and all the rest, and summed up the contributions from all their possible quantum fluctuations, from the lowest energy scales up to the Planck scale, the ultra-high energy limit where gravity becomes as strong as the other forces. The result they arrived at is known as the theoretical prediction for the vacuum energy density, and it is enormous. This calculation suggests that empty space should be brimming with so much energy that the repulsive force it generates would have ripped the universe apart in the first fraction of a second after the Big Bang. Galaxies, stars, and planets could never have formed. The cosmos would be a featureless, accelerating void. Clearly, this is not our universe. Now, let's look at the other side of the equation, the observed value. This comes directly from our measurements of dark energy, the mysterious force causing the universe's expansion to accelerate. By studying the dimming of distant supernova and the detailed structure of the cosmic microwave background, astronomers have pinned down the actual energy density of the vacuum with remarkable precision. It is a tiny, gentle but persistent force, and here lies the catastrophe. When you compare the theoretical prediction from quantum field theory to the observed value from cosmology, they disagree not by a little, but by a factor of 10 to the 120th power. The theory predicts a number that is 120 orders of magnitude larger than what we actually see. It is as if you predicted a single grain of sand should have the mass of the entire observable universe. This is not just a failure, it is a profound and humbling contradiction between our two most powerful theories of reality, quantum mechanics and general relativity. Scientists have proposed several avenues to resolve this staggering discrepancy, but none offer an easy solution. One possibility is that we are making a fundamental error in how we perform the calculation. The straightforward summing of all quantum fluctuations might be too naive. Perhaps different fluctuations cancel each other out in a way we don't yet understand, leading to a near-perfect, but not quite perfect, cancellation that leaves behind the tiny residue we observe as dark energy. The problem is that achieving a cancellation of one part in 10 to the 120 would require a level of fine-tuning that seems miraculous. It would be like balancing a pencil on its tip for billions of years. The initial conditions would have to be set with unimaginable precision. This leads some to invoke the anthropic principle, suggesting that in a vast multiverse where every possible value of the cosmological constant exists, we naturally find ourselves in one of the rare universes where the value is small enough to allow for the formation of galaxies and life. While logically consistent, many physicists find this explanation unsatisfying, as it sidesteps a fundamental dynamical explanation. Another, more promising line of thinking is that our understanding of gravity is incomplete. The calculation of the vacuum energy density treats gravity according to general relativity, which assumes that gravity responds to all forms of energy in the same way. But what if this assumption breaks down when applied to the vacuum? A future theory of quantum gravity, such as string theory or loop quantum gravity, might naturally explain why the vacuum energy gravitates so much more weakly than our current theories predict. The vacuum catastrophe, therefore, is not just a numerical puzzle. It is a blazing signpost pointing toward the necessity of a deeper theory that can seamlessly unite the quantum world with the cosmic realm. It forces us to confront the possibility that the energy of empty space, the silent backdrop of the entire cosmos, holds the key to a revolution in physics as profound as those sparked by relativity and quantum mechanics themselves. Of all the forces that shape our universe, from the nuclear fires blazing within stars to the chemical bonds that build our very bodies, there is one that stands apart not for its strength, but for its profound, almost embarrassing weakness. This is gravity. We experience its pull every moment of our lives, but when we compare it to the other fundamental forces on the microscopic scale, a discrepancy of staggering proportions emerges, a puzzle so deep it is known as the hierarchy problem. To grasp the sheer scale of this imbalance, consider a simple magnet, the kind you might stick to your refrigerator. That tiny magnet, using the electromagnetic force, can overcome the gravitational pull of the entire Earth, a planet weighing over 6 sextillion tons, and leap up to stick on the door. The electromagnetic force is stronger than gravity by a factor of about 10 to the power of 36. That's a 1 followed by 36 zeros. This isn't just a small difference, it's a gulf so vast it dwarfs the difference in size between a single atom and the entire observable universe. This incredible weakness becomes a central problem when we try to unite gravity with the other forces within a single theoretical framework, a goal of modern physics. The issue lies with the Higgs boson, the particle responsible for giving other particles their mass. The mass of the Higgs is intimately tied to the energy scales of the other forces, like the strong and weak nuclear forces. However, according to quantum field theory, the Higgs mass should be extremely sensitive to any ultra-high energy phenomena that might exist, even if they are far beyond our current ability to detect. It should be pulled up or radiatively corrected to these immense scales like the Planck scale, which is the energy level where gravity becomes as strong as the other forces. If this were the case, the Higgs should be billions of times heavier than it actually is, which would prevent the formation of the atoms and structures that make up our world. The fact that the Higgs is relatively light and that gravity is so weak suggests that some mysterious, fine-tuned cancellation must be at work, a cosmic coincidence that keeps the scales of nature separated. This fine-tuning seems unnatural, a sign that our current theories are missing a crucial piece of the puzzle. One of the most elegant and celebrated proposals to solve this problem is a theory known as supersymmetry, often abbreviated as SUSY. This beautiful idea posits that for every known particle in the Standard Model, every electron, quark, and photon, there exists a hidden super-partner particle. An electron would have a selectron, a quark would have a squark, and so on. The magic of supersymmetry is that these superpartners would have a different quantum property called spin. This difference would cause their contributions to the Higgs mass to have opposite signs. In a perfectly supersymmetric world, the enormous quantum corrections from the known particles would be exactly cancelled out by the corrections from their superpartners, resulting in a naturally light Higgs boson without any need for miraculous fine-tuning. It would be a divine mathematical balance, a cosmic symmetry that protects the fragility of our world from the violent energies of the quantum realm. Furthermore, the lightest of these superpartners is a compelling candidate for the elusive dark matter, elegantly solving two major mysteries at once. However, nature has so far refused to cooperate with this elegant idea. If supersymmetry were an exact symmetry, these superpartner particles would have the same mass as their Standard Model counterparts, and we would have detected them long ago. This means that supersymmetry, if it exists, must be a broken symmetry. The superpartners must be much heavier, which explains why they have not yet been seen in our largest particle colliders, like the Large Hadron Collider. The problem is that for supersymmetry to neatly solve the hierarchy problem, these particles should have shown up at energy scales that the LHC has already thoroughly explored. Their continued absence has forced theorists to consider models where the superpartners are so heavy that the fine-tuning problem essentially creeps back in, diminishing the theory's appeal. While supersymmetry remains a mathematically beautiful framework, Its failure to appear where we most expected it has been a significant setback, pushing physicists to consider even more radical explanations. This leads us to a truly mind-bending alternative: the possibility that gravity's apparent weakness is not a fundamental property, but an illusion caused by the very geometry of the universe. This is the idea of large extra dimensions, most famously proposed in the Randall-Sundrum model. Imagine our four-dimensional universe, 3 of space plus 1 of time, as a membrane or brain floating within a higher dimensional space. In this model, the particles of the standard model, like electrons and quarks, are stuck to our brain like characters drawn on the surface of a page. Gravity, however, is different. It is a manifestation of the geometry of space-time itself, and as such, it can leak out into the full volume of these extra dimensions. If there are additional, compactified dimensions of space that are large enough, the gravitational force would be diluted across this much larger volume, explaining why it appears so weak from our perspective, trapped on our three-dimensional brain. It would be like comparing the force of a ripple on the two-dimensional surface of a pond to the gentle, dissipated spreading of a sound wave in the three-dimensional air above it. The same fundamental force, but perceived as vastly weaker because it is spread out. This model provides a compelling explanation for the hierarchy, suggesting that gravity is actually as strong as the other forces, but we are simply experiencing only a faint shadow of its true power. Each of these theories represents a breathtaking leap of imagination, attempting to reconcile the bizarre imbalance of nature's forces. Supersymmetry offers a solution through a hidden, symmetrical world of partner particles, while extra dimensions propose that our entire perception of the cosmos is limited to a thin slice of a much richer, higher-dimensional reality. The ongoing search for evidence, whether in the high-energy collisions of particle accelerators or in the subtle distortions of gravitational waves, is a direct assault on one of the most fundamental questions we can ask. Why is the universe structured in such a way that allows for the existence of stars, planets, and life itself? The hierarchy problem is more than a technical issue in theoretical physics. It is a profound clue that the laws of nature, as we currently understand them, are merely a fragment of a much deeper and more astonishing truth. But if the vacuum catastrophe reveals a stunning gap in our understanding of nothingness, our next mystery forces us to question the very stage upon which the entire cosmic drama unfolds. We now turn to a concept so familiar, so woven into the fabric of our every waking moment, that its true nature remains one of the greatest enigmas in all of physics: the nature of time itself. What is it? Why does it flow in one direction? And is our intimate experience of a flowing present moment a profound truth or a powerful illusion? The conflict begins with a fundamental clash between our two most successful theories of reality. On one hand, we have Einstein's theory of general relativity, which paints a picture of space and time as a single, four-dimensional entity called space-time. In this grand, geometric view, time is not a separate, universal river flowing for everyone. It is a dimension much like the three dimensions of space, but with a crucial difference: it can be stretched and warped by mass and energy. A clock ticks slower in a strong gravitational field, like near a black hole, than it does out in empty space. For an astronaut orbiting a massive planet, time literally passes more slowly than for someone on Earth. In relativity, the concept of a single, universal now simply evaporates. Your now and my now are relative. They depend on your motion and your position in a gravitational field. This leads to a profound and startling interpretation known as the block universe theory. In this view, the past, present, and future all exist simultaneously. The entire history of the cosmos, from the Big Bang to the final fate of the universe, is a single, static, four-dimensional block. We are like characters in a novel, experiencing the story one page at a time, but the entire book already exists complete and unchanging. From this God's eye perspective, nothing is happening, everything just is. The flow of time is an illusion, an artifact of our limited, conscious perception as we move along our particular world line through this frozen landscape. This cold, deterministic picture is violently at odds with our most basic human experience. We feel time passing. We remember the past, we act in the present, and we anticipate the future. We are certain that the past is fixed and unchangeable, while the future is open and undetermined. This subjective feeling is tied to a fundamental property of the universe called the arrow of time. Unlike the dimensions of space where we can move freely back and forth, time has a definite one-way direction. We see eggs splatter on the floor, but we never see them spontaneously reassemble. We grow older, never younger. This irreversible directionality is deeply connected to a concept in physics known as entropy, which is a measure of disorder or randomness. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. The universe as a whole started in a state of incredibly low entropy, a highly ordered, dense, and hot state at the Big Bang, and has been evolving toward a state of maximum entropy or disorder ever since. It is this increase in entropy that gives time its arrow. The reason we remember the past and not the future is because the past was a state of lower entropy, and our memories are formed by irreversible processes that increase disorder. The flow we feel may be our consciousness surfing the wave of increasing entropy from the universe's ordered beginning to its chaotic end. But this explanation, while powerful, only deepens the mystery. Why was the entropy of the early universe so impossibly low in the first place? This is perhaps the most profound question about time. A universe starting in a state of high entropy would have been a featureless, maximum disorder soup where no arrows of time could be defined, and no complex structures like galaxies or life could ever form. The fact that we have a clear arrow of time is therefore a direct consequence of a very special, finely tuned initial condition. Some physicists, like Sean Carroll, suggest that our Big Bang might not have been the absolute beginning, but rather a fluctuation within a larger, eternal multiverse. In this vast expanse, low-entropy bubbles like our universe could occasionally pop into existence, each with its own arrow of time. Others, like Lee Smolin, propose even more radical ideas, suggesting that the laws of physics themselves could evolve over time, and that time is the most fundamental reality, with space and matter emerging from it. The quest to unify general relativity with quantum mechanics only adds another layer of strangeness. In the quantum world, time is treated as a fixed background parameter, not a dynamic player. Trying to make it dynamic as required by relativity leads to severe mathematical problems. Some approaches to quantum gravity, like the Wheeler-DeWitt equation, famously yield a result that suggests the universe is completely static, with no time variable appearing at all. This problem of time is a central obstacle in theoretical physics. Could it be that time is not fundamental, but emerges from a more basic, timeless quantum reality, much like temperature emerges from the motion of atoms? If so, our experience of a flowing present may be a compelling cognitive illusion, a story our brains tell us to make sense of a reality that is far more alien and magnificent than we can possibly imagine. The nature of time, therefore, stands as the ultimate frontier, a mystery that connects the largest scales of the cosmos to the deepest workings of our own minds, challenging us to reconcile the timeless equations of physics with the undeniable reality of our lived experience. And so we come full circle, arriving at the question that has haunted humanity since we first gazed up at the stars, a question that synthesizes nearly every cosmic mystery we have explored. The nature of dark matter and dark energy set the stage for the universe itself. The matter-antimatter asymmetry made complex chemistry possible. The violent births of planets around pulsars and the silent wanderings of rogue worlds demonstrate the incredible diversity of cosmic habitats. The Great Filter hypothesis gives a terrifying weight to our own survival. all of these threads converge on one profound and ultimate enigma: are we alone? This is not merely a scientific inquiry, it is a deeply philosophical one that forces us to confront our place in the grand scheme of existence. To even begin to frame this question scientifically, we turn to a powerful, though speculative, tool conceived by astronomer Frank Drake in 1961, the Drake equation. This is not a formula with a single answer, but rather a structured way to think about the multitude of factors that would determine the number of communicative civilizations in our galaxy. It breaks down the vast question into a series of more manageable probabilities. The equation starts with the rate of star formation in the Milky Way, then multiplies that by the fraction of stars that have planets. This is a factor we now know to be enormous. Planets are not the exception, but the rule. The next terms consider the number of planets per star that orbit within the habitable zone, the so-called Goldilocks zone, where temperatures are just right for liquid water to exist. Our understanding of this has also expanded dramatically. We now know that habitable zones can exist not just around stars, but in the subsurface oceans of icy moons like Europa and Enceladus, vastly increasing the potential real estate for life. The equation then ventures into more uncertain territory, the fraction of those habitable worlds where life actually emerges. This is the leap from chemistry to biology, and we have no idea if this is an almost inevitable process given the right ingredients and enough time, or a fantastically rare fluke. Next comes the fraction of life that evolves to become intelligent, and then the fraction of intelligent life that develops the technology to communicate across interstellar distances. Each of these terms is a gateway to profound uncertainty. Finally, and perhaps most soberingly, is the average length of time such civilizations release detectable signals into space. This is the variable that encapsulates the great filter. Is it a billion years? Or is it, as our own fragile history might suggest, only a few centuries before a civilization succumbs to self-destruction or a natural catastrophe? Depending on whether you are an optimist or a pessimist when plugging in these numbers, the Drake equation can suggest a galaxy teeming with conversation partners, or it can yield a result of one, a silent galaxy with only us to ponder the silence. The discovery of thousands of exoplanets has transformed the first few factors of the Drake equation from philosophical guesswork into a field of active, data-driven science. We now know that rocky planets orbiting within the habitable zone of their stars are common. The next great leap is to search for biosignatures, chemical signs of life in the atmospheres of these distant worlds. The James Webb Space Telescope is already attempting this, analyzing the starlight that filters through an exoplanet's atmosphere to identify the chemical fingerprints of molecules like oxygen, methane, and water vapor. On Earth, the simultaneous presence of oxygen and methane is a powerful biosignature because these gases react with each other and would quickly disappear if they weren't being constantly replenished by living processes. Finding a similar imbalance on a distant world would be the most compelling hint of life we could imagine, but we must be cautious. Scientists are also working to identify false positives, abiotic geological processes that could mimic these biosignatures. The recent debate over phosphine on Venus is a perfect example of this challenge. The ultimate confirmation would likely require a more direct method, perhaps by analyzing the light reflected from a planet's surface for signs of chlorophyll or other pigments associated with photosynthesis, a technique known as searching for a red edge. This is the goal of next-generation telescopes, like the planned Habitable Worlds Observatory, which will be designed to directly image Earth-like planets and scrutinize their atmospheres with unprecedented precision. The search is no longer just about finding planets, it is about taking their cosmic vital signs. This immense scientific endeavor carries with it equally immense philosophical weight. The possible outcomes present us with two equally profound and equally unsettling futures. On one hand, if our searches over the coming decades conclusively find that we are alone, if every potentially habitable world is barren, and the great silence persists, then that silence itself becomes a deafening statement. It would suggest that the transition from non-life to life or from life to intelligence is an astronomically rare event. In such a universe, our planet and the life upon it would be an inconceivably precious jewel, a miracle of cosmic proportions. This reality would bestow upon humanity a staggering responsibility. We would be the universe's only means of knowing itself, the sole guardians of consciousness in a vast, unconscious cosmos. Our survival would carry a weight beyond our own species, becoming an imperative for the preservation of meaning itself. On the other hand, the discovery of even a single, simple microbe on another world would be arguably the most important discovery in human history. It would tell us that life is not a miracle, but a natural process, a cosmic imperative. The universe would shift from a collection of sterile rocks to a fertile garden filled with potential. If life arose independently twice within our own solar system, it would imply that it has arisen countless times across the galaxy. The great silence in that case would become even more mysterious. If life is common, then where is everyone? This would lend terrifying credence to the idea that the great filter lies not in our past, but in our future, that the challenge of achieving a stable, long-lasting technological civilization is one that very few, if any, ever overcome. Ultimately, the question, "Are we alone?" is the final frontier of human curiosity. It is a question that drives us to build ever larger telescopes, to send robotic emissaries to the farthest reaches of our solar system, and to listen patiently for a signal that may never come. It forces us to look inward as much as outward, to contemplate the nature of intelligence, technology, and the lifespan of civilizations. Whether the answer is a lonely one or a crowded one, it will fundamentally reshape our understanding of reality and our role within it. This search is perhaps the most ambitious project our species has ever undertaken, a quest to find our true place in a cosmos of unimaginable scale and mystery. And so we reach the end of our grand tour, a journey that has taken us from the ghostly grip of dark matter holding galaxies together to the repulsive push of dark energy tearing the cosmos apart. We have stood at the precipice of black holes where the laws of physics break down and wondered what happened before the Big Bang, or if the question itself is a trick of time. We have listened to the profound silence of the universe and pondered the Fermi Paradox, while also catching the fleeting, powerful screams of fast radio bursts. We have encountered celestial oddities, from the perfect geometry of the Red Rectangle Nebula to the diamond-rich hellscape of 55 Cancri E, and explored the possibility of rogue planets drifting alone in the eternal night. Each of these 50 mysteries is more than a simple question. It is a blazing frontier of human knowledge, a signpost pointing toward a deeper reality that we are only beginning to grasp. This incredible voyage reveals one overwhelming truth: the universe is far stranger, more chaotic, and more magnificently wonderful than our everyday experience could ever suggest. The serene night sky is an illusion, a quiet curtain hiding a cosmic arena of unimaginable violence, beauty, and complexity. The pursuit of these answers, the relentless drive to peel back the layers of reality, is what propels science forward. It is a humbling endeavor. Every time we solve one puzzle, like the Pioneer anomaly, two more profound questions emerge, like the nature of quantum singularities or the true identity of dark matter. This is not a sign of failure, but a testament to the boundless depth of the cosmos. The unknown is not a void to be filled, but an ocean to be explored, and we have only just dipped our toes in the water. The greatest takeaway from this journey is that the act of questioning is as important as finding the answers. To be curious, to look up at the stars and wonder what if, or how, or why, this is the engine of discovery. It connects us to every astronomer who ever charted the planets, every physicist who ever dreamed of a unified theory, and every human who has ever felt a sense of awe under a canopy of stars. The universe invites us to be explorers, not just with telescopes and spacecraft, but with our minds. So, the next time you find yourself under a clear night sky, take a moment. Remember that you are living on a pale blue dot, adrift in a cosmic ocean filled with mysteries beyond counting. Let that feeling of wonder fuel your own curiosity. We want to hear from you. Which of these 50 cosmic enigmas captured your imagination the most? Does the eerie silence of the Fermi Paradox unsettle you, or does the mind-bending possibility of wormholes fill you with excitement? Share your thoughts in the comments below, and let's continue this incredible conversation about our place in the universe. The greatest discoveries are still ahead.